Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of gravitational fields. So in today's lesson we're going to be looking at how to answer examination questions for AQA A-Level Physics Paper 2, in particular gravitational fields. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions for gravitational fields, assess our understanding on A-Level Physics gravitational fields, and then finally understand what topics we need to improve upon for AQA A-Level Physics Paper 2, in particular gravitational fields. So how should you prepare for this revision session? Well, when you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and your answers to the questions in this revision session. When you're doing this, try to make sure you're writing full sentences and show your full working out. Whilst on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, in terms of revising AQA A-Level Physics, what should you be doing? Well, the first step is learning the key facts, so use your revision guide, class workbook, student prep notes and the textbooks to learn the key ideas of the course, which might include writing mind maps or notes for yourself. The second step is to do retrieval, so test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this using your own cue cards. Then finally, you can do practice by practicing examination style questions. So use things like exam practice books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So the three steps of learn the key facts, then testing yourself, and then practicing your examination questions are how you should be revising for your A-Level Physics. Now, in this revision session, you'll find we have three types of questions. The first question is a general check question. So these are the basic questions designed to probe your understanding of the key concepts of the topic. The second type of question are the checkpoint questions, which are more challenging questions designed to place your knowledge and your understanding of the topics into different contexts and applications. Whilst the third type of question are the assessment point questions. So these are past paper examination questions which will mimic the type of questions which are found in public examinations. So let's now start having a look at the gravitational fields topic. So the first question says, describe what happens to the gravitational force between two objects A and B when the mass of A doubles, then the mass of both A and B double, then the distance between A and B halves, and then finally the mass of B doubles and the distance between A and B decrease by a factor of 4. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is a test of the Newton's law of gravitation, where F equals gmm over r squared. So this tells us that F is directly proportional to m, so therefore the relationship would hold that if m doubles, F doubles. Now we know again from Newton's law of gravitation that F is directly proportional to mm, where they're both the masses of the two objects. So if big M and small m double, well therefore both will double, so therefore be times by a factor of 4, so F will quadruple. We also know from the law of gravitation that F is directly proportional to 1 over r squared. So of r halves, F will therefore quadruple because it's half squared, so it's a quarter, then 1 over a quarter is times by 4, which is a quadrupling. Now if we link them all together, that F is directly proportional to m and F is directly proportional to 1 over r squared, well when m doubles, F doubles, and if r decreases by a factor of 4, F increases by a factor of 16, so that therefore means F will increase by a factor of 32. The next question says, calculate the gravitational force between two protons of mass 1.67 times 10 to the minus 27 are separated by a distance of 1 times 10 to the minus 14 meters. Two students of mass 65 kilograms and 70 kilograms standing 1.5 meters apart, and then Saturn and the Sun, where you got the mass of Saturn there, the mass of the Sun there, and their average separation in kilometers. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, this is using Newton's law of gravitation, where F is equal to gmm over r squared. So in this first one, you pop in all the values. Now again, remember it's r squared, and then you get out your answer to be 1.9 times 10 to the minus 36 newtons. Again, you pop in these values, F equals gmm over r squared. Again, remember to square r. So we get 1.3 times 10 to the minus 7 newtons. And then here in this question, remember that you're given the separation in kilometers, and we work in meters in A-level physics for this particular equation. So you've got to convert million kilometers into meters, so it's 1,400 times by 10 to the 9. So therefore the answer is 3.8 times 10 to the 22 newtons. The next question says, state the effect on the gravitational field strength at a point in a radial field around a point mass when, firstly, the mass of the point mass is creating the field is halved, the distance from the point mass increases by a factor of 3, and then the mass of the point mass decreases by a factor of 4, and the distance from the point mass halves. Then explain why when moving an object from a height of 100 meters to a height of 200 meters above the surface of the Earth, the gravitational field strength does not decrease by a factor of 4. So pause the video now, then unpause the video when you want to go through your answer. Right, so again we're looking at our equation for gravitational field strength. So gravitational field strength is equal to gm over r squared. So therefore g is directly proportional to m. So if m halves, g will halve. G is then proportional to 1 over r squared. So if r increases by a factor of 3, g will decrease by a factor of 9 because it's 3 squared. And then we link the two ideas together. So if g is directly proportional to m, if m decreases by a factor of 4, g will decrease by a factor of 4. And g is proportional to 1 over r squared. So if r decreases by a factor of 2, g will increase by a factor of 4, 2 squared. So the two things will cancel out, so there'll be no overall change in the gravitational field strength. Now we do know that g is directly proportional to 1 over r squared, but it's a very important idea to remember that r is measured from the center of mass of the object, not the surface of the object. So in fact, moving from 100 meters above the surface to 200 meters above the surface does not double r because it's not being taken from the center. So that's why it doesn't decrease by a factor of 4. The next question says, the Sun has a mass of 1.99 times 10 to the 30 kilograms and a diameter of 1.39 million kilometers. Calculate the gravitational field at its surface. Then calculate the gravitational field strength 1.2 times 10 to the 8 meters from a point mass of 2.6 times 10 to the 23 kilograms. Then Mars has a mass of 6.42 times 10 to the 23 kilograms and a surface gravitational field strength of 3.72 newtons per kilogram. Calculate the radius of Mars. Then the surface gravitational field strength of Venus is 8.77 newtons per kilogram, and it has a radius of 6.09 megameters. Calculate the mass of Venus. So pause the video now, and then unpause the video when you want to go through your answer. Right, so this is using the gravitational field strength equation where G equals big G, big M over R squared. So you pop in all the values there, remembering we're going to square R. And second, remember it's million kilometers, so we're going to convert that into meters, so that'll be 10 to the 6. So therefore you would work it through, okay, to be, work it through there to be 679 newtons per kilogram. Now notice, by the way, we've been given the diameter, so we're going to have to half that to work out what the radius is. The next question, again, we're doing G, big G, M over R squared. Pop in all the values, work it through. Remember, it's R squared, so you get 1.2 times 10 to the minus 3 newtons per kilogram. This next one, we're going to rearrange it to make R, the radius, the subject. So R is going to be equal to the square root of gm over small g. So therefore you pop in all the values, work it through, and get 3.4 times 10 to the 6 meters. And then the next one, we're going to make an m the subject. So m is equal to gravitational field strength times by r squared over the gravitational constant. Pop in all the numbers. Remember it's r squared. And remember we were given the radius in megameters. So mega is times 10 to the 6. So we get 4.88 times 10 to the 24 kilograms. The next question says, determine the gravitational potential at firstly the Earth's surface, then secondly at a height of 650 kilometers above the Earth's surface. Then a small space probe of mass 510 kilograms has been landed on the surface of a small asteroid. Determine the output energy of the probe's onboard rockets for the probe to escape the gravitational field of the asteroid, given that the gravitational potential at the surface of the asteroid is minus 40 kilojoules per kilogram. Then the gravitational potential at the surface of a planet of radius r is v. What would the gravitational potential at a height of r above the planet's surface be? So pause the video now, then unpause the video when you want to go through your answer. Right, again, so we've got to remember what our gravitational potential equation is. So the gravitational potential is equal to negative big G big M over the radius of the object. So therefore we pop it all through. Remember, you're given the radius of the Earth on the equation sheet. It's 6.37 times 10 to the 6 meters. Pop in all the values through and it's negative 6.25 times 10 to the 7 joules per kilogram. The next one, we're going to have to add 650 times 10 to the 3, because we converted kilometers into meters, to the radius of the Earth's surface, because we take r from the center of mass of the object. So we've got to add the radius of the planet to the distance above the surface. We then pop in all the values and we get minus 5.67 times 10 to the 7 joules per kilogram. This next one, we've got to remember that here the change in gravitational potential, okay, is going to have to be 40 times 10 to the 3 joules per kilogram. Now work done is equal to mass times by the change in potential. That again is another equation which you're given in the exam, but you've also got to be able to use. So the mass of the object that's being moved, not the mass of the object making the field. Remember, if it's small m, it's the mass of the object that's moving in the field. So it's 510 times by 40 times by 10 to the 3. So we get our answer out to be 20 times 10 to the 6 joules. The next question is, we know V is directly proportional to 1 over R. We can tell that from the equation V minus Gm over R. So G and M are constant, V is directly proportional to 1 over R. So therefore, if the height is doubled above the if height is doubled, we can therefore say that it's going to be halved for the potential, because they're inversely proportional. The next question says, draw lines to show the shape and direction of the gravitational field of the Earth. Then the gravitational field strength G is uniform close to the Earth's surface. Describe the pattern of the gravitational field lines close to the surface of the Earth. Then the planet Saturn has a mass of 5.7 times 10 to the 6 kilograms and a radius of 6 times 10 to the 7 meters. Calculate the gravitational field strength at Saturn's surface. Then Saturn's second largest moon, Rhea, has an orbital radius of 5.3 times 10 to the 8 meters and a mass of 2.3 times 10 to 21 kilograms. Calculate Rhea's orbital speed, then calculate Rhea's kinetic energy. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one, you've got to be able to understand what a gravitational field looks like for a planet. So you're going to have radial lines coming out of the Earth, indicating they appear to meet at the center of the Earth. However, they would just stop at the surface of the Earth, but they would appear to actually meet at the center. And you got the direct towards the Earth, because the field lines show the direction in which a mass would move. Gravity is always attractive, so the field line should be going towards the planet or the object. And this next one, you would notice that if it's a uniform field, well, we can tell that gravitational field strength is shown by how close the field lines are together. So if it's a uniform strength, the field lines are staying the same distance apart from each other, so therefore they're parallel to each other and perpendicular to the surface of the Earth itself. Now, to calculate the gravitational field strength, we'll do G equals big G big M over R squared. Pop in all the values. Remember, it's R squared, and we get 11 newtons per kilogram. Now, this next one, we can work out the orbital speed, because we can say that the equation for the orbital speed is V equals the square root of Gm over R. Again, that's worked through by looking at the energies, okay, of the particular of the object. So we can say V is equal to square root 2 Gm over R. You can pop that all through and you work it out to be 8.5 times 10 to the 3 meters per second. Now, in terms of calculating kinetic energy, we can work out that with our equation, kinetic energy is a half mv squared. The very famous equation still works in this context. So it's a half mv squared. We've just worked out V before, so therefore it's 8.2 times 10 to the 28 joules. The next question says, determine the mass of the Sun given that the time of orbit of the Earth is 365 days and the radius of the Earth's orbit is 1.5 times 10 to the 11 meters. The radius and time of the orbit of Io, one of Jupiter's moons, are 5 times 10 to the 20, 4.22 times 10 to the 8 meters in 42 hours respectively. So determine the mass of Jupiter. Then it's estimated that the solar system completes an orbit around the galactic center of the Milky Way in 250 million years with a radius of orbit of 27,000 light years. Determine the effective mass within the orbit that has its center of mass at its galactic center. 1 light year is 9.46 times 10 to the 15 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one, we've got to use the concept you've covered in circular motion because the orbit will be considered to be carrying out a circular path. So we can say that the angular velocity is equal to 2 pi over t. So it's the angular change in one complete revolution, 2 pi radians, divided by the time taken for one complete revolution. That time must be given in seconds. You're going to have to convert the value of 1 year into seconds because that is how long it takes for the Earth to orbit the Sun once. So you get out to be 1.99 times 10 to the minus 7 radians per second. We can then use our equation to work out the mass because what we can do is we can link it in with the law of orbits that comes through where we say that mass is equal to r cubed omega squared over g. We can pop in all the values and we get 2 times 10 to the 30 kilograms. That comes again from Kepler's law of orbits. The next one again, it's the same principle once again. We can work out the angular velocity by doing 2 pi over t. Work out our angular velocity in radians per second to be 4.16 times 10 to the minus 5. Pop in the values into the equation to work out mass and we get 1.9 times 10 to the 27 kilograms. And then again, same logic, omega is equal to 2 pi over t. Work it all through and we get 8.3 times 10 to the minus 16 radians per second. Where you can work out the mass with our equation r cubed omega squared over g. Pop in all the values and we get 1.7 times 10 to the 41 kilograms. The next question says, calculate the orbital speed of the Hubble Space Telescope given that it orbits at a height of 547 kilometers above the Earth's surface, and then determine the radius of orbit and the altitude of a GPS satellite which orbits the Earth twice a day. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to be able to work out orbital speed. So we're using our equation which we talked about before, where v is equal to the square root of gm over r. That's the equation for orbital speed. We can pop in all the values. Now again, remember that it's the r is the distance we have from the center of the Earth to the actual satellite. So you've got to add the distance above the surface to the radius of the Earth. Once again, is given to you on the equation sheet. We work out our answer and then 7.59 times 10 to the 3 meters per second. Now this next one again, we've got to work out our angular velocity by doing 2 pi over t. Again, we know that it orbits twice a day, so therefore we can do 12 times by 3,600 for the orbital time because there's 3,600 hours in 1 second and it orbits once every 12 hours. So we get our answer to be 1.54 times 10 to the minus 4 radians per second. We can therefore work out r from the equation we looked at before, and we can get our r out to be 2.66 times 10 to the 7 meters. So that's the total separation from the center of mass to the actual satellite. We subtract then the radius of the planet, 6.37 times 10 to the 6, to get the actual height above the surface to be 2.02 times 10 to the 7 meters. The next question says, determine the kinetic energy of the SMAP satellite which has a mass of 1,123 kilograms and orbits the Earth at a height of 685 kilometers. Then determine the kinetic energy of the Earth in its orbit around the Sun. Then determine the escape velocity of an object at the Earth's surface, and then determine the escape velocity of an object at the Moon's surface. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to remember is how can you work out the kinetic energy? Well, the energy is going to be working through because it's actually going to be equal to the change in potential energy. So you can say E is equal to G big M small m over 2R. So we can pop those all in. Now again, we do know that kinetic energy equals a half mv squared, but we don't have enough information to work out V in this particular situation. So we can use G m over 2R, which is the change in potential energy. Remember, R is is the distance from the centre of the Earth to the object. So we've got to add the radius of the Earth to the height above the surface of the Earth to work out our answer to be 3.17 times 10 to the 10 joules. The next question, again, we're using that same equation. The change in potential is equal to the kinetic energy, which is gmm over 2r. So therefore, we can pop in all the values. Once again, remember, we're going to be able to work out it's the distance it is from the Earth to the Sun, which was given before to be 1.50 times 10 to the 11 meters. Again, that's given to you on the equation sheet. So it's 2.64 times 10 to the 33 joules. The escape velocity, now again, this is an equation which you'd have to memorize. Again, it comes from the energy transfers that go on. The kinetic energy equals potential energy. So the escape velocity is going to equal to be the square root of 2gm over r. So whilst the orbital velocity is square root gm over r, the escape velocity is square root 2gm over r. So you pop in all the values that we've got. Remember, r is going to be the radius of the Earth because we're at the surface of the Earth. We pop in all the values and we get 1.12 times 10 to the 4 meters per second. Then we can use the same equation to work out the moon's escape velocity by doing square root 2gm over r, pop in all the values given to you in the question, and we get 2.37 times 10 to the 3 meters per second. The next question says, calculate the gravitational force of attraction between two objects separated by a distance of 1 centimeter, each having a mass of 100 grams, two asteroids separated by a distance of 4 times 10 to the 9 meters and each having a mass of 5 times 10 to the 10 kilograms, a satellite of mass 1.4 times 10 to the 4 kilograms orbiting the Earth at a distance of 6,800 kilometers from the Earth's center, and then estimate the gravitational force of attraction between two people sitting side by side on a park bench. How does this force compare with the gravitational force exerted on each of them by the Earth? So pause the video now, then unpause the video when you want to go through your answer. Right, so this one again, we're using Newton's law of gravitation. So F equals gmm over r squared. Remember, we don't work in centimeters, we work in meters. Okay, so you work it through to be 6.67 times 10 to the minus 9 newtons. Next again, we use the gravitational law of attraction. So we can then do gmm over r squared, pop in all the numbers, remember it's r squared, and we get 1 times 10 to the minus 8 newtons. The next question, again, we're using gmm over r squared. Now again, remember that we're going to be not working in kilometers, we're working in fact in meters, so it's 6.8 times 10 to the 6, okay, and it's r squared, and we get our answer to be 1.2 times 10 to the 5 newtons. Now it's very important that you can estimate values in A-level physics. So people are sitting side by side with each other, we say they're about 0.5 meters apart. We say they've each got a mass of about 70 kilograms, so you can pop that into the equation, and we get out about 10 to the minus 6 newtons. So a human with a mass of 70 kilograms will have a weight of about 700 newtons because it's mass times by gravitational field strength, which is 9.81. So we can say that their weight is greater than the mutual attraction by about a factor of like 10 to the 9. So it's very, very a much bigger idea of weight than it is gravitational attraction. The next question says, calculate the gravitational force between two pi-0 particles in deep space if they are 8 meters apart. The mass of this pi-0 or neutral pion is 2.4 times 10 to the minus 28 kilograms. Then calculate the gravitational force between the Earth and the Moon if the Moon's mass is 7.35 times 10 to the 22 kilograms. The distance from the Earth to the Moon is 384,400 kilometers. Then calculate the average distance of the Earth from the Sun if the Sun's mass is 2 times 10 to the 30 kilograms. The gravitational attraction between the Earth and the Sun is 3.57 times 10 to 22 newtons. So pause the video now, then unpause the video when you want to go through your answer. So again, in this question, we're going to be using Newton's law of gravitation. F equals gmm over r squared. So you pop in all the values, you work it through, and we get 6.0 times 10 to the minus 68 newtons. This next one again, we'll be using that same law of gravitational attraction. F is equal to gmm over r squared, pop in all the numbers, and we get 2 times 10 to the 20 newtons. Always remember to be squaring the r value in that equation. And once again, we're now going to work the other way around. So we're using Newton's law of gravitational attraction, but we're now making r the subject. So r is equal to the square root of gmm, GMM divided by M there, so you work it through and you get 1.5 times 10 to the 11 meters by working all those values through. So it's square root of GMM over F. My apologies. The next question says figure 18.14 shows the Earth's gravitational field. Copy the diagram and add arrows to show the direction of the field. Explain why the formula for potential energy gained mg delta H cannot be used to find the increase in potential energy when an aircraft climbs to a height of 10,000 meters, but cannot be used to calculate the increase in potential energy when a spacecraft travels from the Earth's surface to a height of 10,000 kilometers. Then Mercury, the smallest of the 8 recognized planets, has a diameter of 4.88 times 10 to the 6 meters and a mean density of 5.4 times 10 to the 3 kilograms per meter cubed. Calculate the gravitational field at its surface. Then a man has a weight of 700 newtons on the Earth's surface. What would his weight be on the surface of Mercury? So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one again, you're going to have arrows directed towards the Earth because the gravitational field goes in the direction that a point mass would move in. Gravity is always attractive, so it points towards the centre of the planet. Now you can't use the equation E equals mg delta H because for a rise of 10,000 meters, G, the Earth's gravitational field strength, can be considered to be uniform, so we can use that equation, but for a greater change in distance, G will change, so therefore that equation it cannot be used because G is no longer constant. Now, how can we work through the gravitational field? Well, we know that the mass of Mercury is going to be equal to density times by volume. We know the volume is going to be 4 over 3 pi r cubed because it's a sphere. So we can work out the mass by it'd be 3.28, 6 times 10 to the 23 kilograms. We know G equals big G big M over r squared. We've just worked out M, so therefore we can work it through to be 3.7 newtons per kilogram. Now the next question is what would the weight be on the surface of Mercury? Well, we've just worked out what small g would be, 3.7 newtons per kilogram. So weight is mass times by gravity, so it's 700 times by 3.68, so it's 340 newtons. The next question says, what is the gravitational potential and what are its units? What is the significance of the negative sign in the gravitational potential equation? Sketch a graph of gravitational potential against distance for an object in the Earth's gravitational field. What does the gradient of a graph of V against R tell you? And find the gravitational potential at the surface of the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, so definition of gravitational potential is it is the gravitational potential energy that a unit mass would have at that point in the gravitational field, and it's measured in joules per kilogram. The significance of the negative sign is that because gravitational fields are inherently attractive, so therefore we say that at infinity, or when you're out of the field, that the gravitational potential is 0. Now you've got to put energy in to get out of that attractive field, so if you put an energy in to get to 0, well therefore it must start off at a negative value because work is having to be done to move it out of the field. So the gravitational potential against distance graph would look something like the following. It's proportional to 1 over r, and it's in a negative, so it'll go through as a curve like so. Now the gradient of V against R, well we know V against R is going to be GM over R again, so it's going to be GM over R squared, which we know is the gravitational field strength, so therefore the gradient will be the negative G at that point. And then to work out this gravitational potential, well it's minus GM over R. Pop in all the values. We've got the radius of the Earth given to us on the equation sheet. We can pop it through to be minus 6.26 times 10 to the 7 joules per kilogram. The next question says, state in words Newton's law of gravitation. By considering the centripetal force which acts on a planet in circular motion, show that t squared is directly proportional to r cubed, where t is the time taken for one orbit around the sun and r is the radius of the orbit. Now the Earth's orbit is of a mean radius 1.50 times 10 to the 11 meters, and the Earth's year is 365 days long. The mean radius of the orbit of Mercury is 5.79 times 10 to the 10 meters. Calculate the length of Mercury's year. Then Neptune orbits the Sun once every 165 Earth years. Calculate the distance from the Sun to Neptune divided by the distance from the Earth to Neptune. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this particular question, you've got to know what the Newton's law of gravitation is. That gravitation is going to be attractive between point masses. The force of the attraction is going to be proportional to the product of the two masses, but inversely proportional to the square of the separation of those two masses. Now, in this next question, we know we can link that the centripetal force in this context is the gravitational force of attraction. So the general equation for the gravitational force is gmm over r squared, and the general equation for centripetal force is m omega squared r. And we know T is going to be equal to 2 pi over omega, so therefore omega we can then link into is going to be 2 pi over T. We can pop all those values into that equation, and then we can substitute that down. So we can say 4 pi squared over T squared equals gm over r cubed. We know that 4 pi squared, and we know that gm in these contexts are constant, so therefore tells us that proportionally T squared is directly proportional to r cubed. Now we can therefore use that to work out the length of the year. So if we know T squared is directly proportional to r cubed, well, we can say that T squared of Earth over T squared of Mercury T squared of Earth over r cubed of the Earth equals T squared of Mercury over r cubed of Mercury. Now we know throughout the four of them, we know the time of the Earth year, we know the distance between the Earth and the Sun, we know the distance between the Earth and between Mercury and the Sun. Now you don't have to convert the time into seconds because it's a ratio, so it would work out a value in days, so it's 87.5 days. Now again, we can use this ratio idea to work out the distance between the Earth and Neptune ratio to the distance between Neptune and the Sun. So we can say that the T squared for the Earth over r cubed for the Earth is equal to T squared for Neptune over r cubed for Neptune. Now we just need to work out r cubed for Neptune, so we can work that out by popping in all the values. Remember that the Earth's orbital time period is 1 Earth year. Again, we don't need to change the units for time because it's a ratio. So we work out that the radius of Neptune to the Sun is 4.51 times 10 to the 12 meters. So we can therefore work out that the ratio between the two of them is equal to 30. The next question says, a student believes it's possible for a satellite to be in a geostationary orbit above London. Firstly, explain why a satellite could not be in a geostationary orbit above London. Then the height of a geostationary orbit is 36 times 10 to the 6 meters. Show that the speed of a satellite in a geostationary orbit is about 3 kilometers per second. And then calculate the total energy in joules of a geostationary satellite of mass 282 kilograms in this orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, why can't it be in a geostationary orbit above London? Well, to remain in orbit, there must be a force perpendicular to the direction of motion. Now, this satellite could not maintain this orbit without an engine or other force or engine input. Now, you can only really maintain a geostationary orbit when you're in a plane above the equator. Now, in the next one, we can work out what r is going to be, because it's the distance from the surface to the object plus the radius of the planet, which we are given on the equation sheet. We can then work out what the time is going to be by working out the time for by 24 times by 60 times by 60. That is going to be the number of seconds in one day. And then we'll say v is equal to the distance, which is going to be 2 pi r from the radius of circular orbit, divided by the time, so we get 3081 meters per second, or 3 kilometers per second as well. Now, how can we work out total energy? Well, we know that the total energy for an orbit is the kinetic energy plus the potential energy store. We know that the kinetic energy is a half mv squared, but in this context it's going to be gmm over 2r when we work it through. We know that the potential is going to be equal to negative gmm over r, because we can't use mgh, so therefore we can work through our value to be minus gmm over 2r. Pop in all the numbers. We know r is the distance from the center of mass, not the distance from the surface. We can pop in all the numbers and we work it out to be minus 1.3 times 10 to the 9 joules. The next question says, define the gravitational field strength, and then the table shows in modern units information that was known to physicists at the time of Isaac Newton. Firstly, state the relationship between the gravitational field strength G and the distance r and verify this relationship. Show that the mass of the Earth is about 6 times 10 to 24 kilograms and determine the mean density of the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, so the gravitational field strength we know is the force per unit mass at a point in a gravitational field. That's a definition you've just got to be able to recall. Now, how can you verify a relationship? Well, we know that the relationship should be G is directly proportional to 1 over r squared. So we can therefore say G is equal to K over r squared, where K is just the proportionality constant. Now, if it's a verified relationship, that proportionality constant should be the same for each particular object that you know. So therefore K will be equal to G r squared. So you do G r squared for each of the values. Now you don't have to convert units because we're just looking for a same value at this point. So as long as it's in the same units, it should be fine. So you work it through. They are roughly the same number. One is 4 times 10 to the 8. The other is 3.9 times 10 to the 8. So therefore they're close enough to be correct. Now for the next question, where we're looking at the mass of the Earth, well, we know that G is going to be equal to gm over r squared, so therefore we can work through that it's going to be m is equal to gr squared over g, so we can say it's going to be 9.81 times by 6.4 times 10 to the 6 squared over 6.67 times 10 to the minus 11, so it's 6.024 times 10 to the 24 kilograms. Now we can work out the mean density, because density is going to be mass over volume. The Earth is a sphere, so it's 4 over 3 pi r cubed, so you can work it through that way, and then you pop in the mass you've just calculated before divided by the volume, which is worked out by 4 over 3 pi r cubed, so you get 5,500 kilograms per meter cubed. Now the next question says, state the name given to the satellites that orbit the Earth with a period of 1 day above the equator. Explain why these satellites orbit above the equator. Then, for companies who provide a satellite TV service, suggest the main advantage of using this type of satellite. Now, the mass of the Earth is 6 times 10 to the 24 kilograms. Show that the radius of the orbit of a satellite with an orbital period of 1 day is about 4 times 10 to the 7 meters. And then state Kepler's third law. And then the Moon orbits the Earth with a period of 27.3 days. Use the information to calculate the ratio of the distance of the Moon from the Earth center divided by the distance of the satellite from the Earth center. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is just a fact. We know that it's a geostationary orbit or a synchronous orbit. That's just a fact you've got to learn. Now, they have to be above the equator, so they can stay at the same point at all times above that part of the Earth, which can only take place if it's at the equator, because that's the point which will stay stationary to that rotation when you're doing 1 day. Now, again, the advantage of using geostationary orbits is that the dish can be fixed to just one point in the sky, because it's always at that point, so the dish doesn't have to track the satellite as it moves across the sky from the perspective of the Earth, so it's easier for them to sort that out. Now, the next one, we're using this equation of t squared is equal to 4 pi squared over gm r cubed. So therefore you can make r cubed the subject, pop in all the values, and remember you can work it through to get r out, which is 4.2 times 10 to the 7 meters. Now, in the next question, how can we work out what's Kepler's third law? Well, it's that t squared is directly proportional to r cubed, so the cube of a planet's distance from the Sun divided by the square of the orbital time period is the same. It's a constant, and we can use that idea of that ratio, that the rate that r cubed is equal to t squared or proportional to t squared, by looking it through. Now, again, we know the time it takes for the Earth to orbit the Earth, so the Moon to orbit the Earth. We know it's 27.3 days. We can then work out how long it takes for the Earth to orbit again, to go around itself once, which is 1 day. So therefore we can go 27.3 over 1. Okay, that's all squared, so you can work through that ratio to be 9.1. The next question says, planets outside our solar system are called exoplanets. An exoplanet of mass 5.69 times 10 to 27 kilograms orbits a star of mass 3.83 times 10 to 30 kilograms. Compare the mass of the star with the mass of the exoplanet in terms of orders of magnitude, and then the distance between the exoplanet and the star is 3.14 times 10 to the 11 meters. Calculate the gravitational force between the star and the exoplanet. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what you've got to do is you've just got to divide the two masses by each other. So it's 3.38 times 10 to the 30 over 5.69 times 10 to the 27. So that equals 200. So equals 673. So therefore, you can say it's about 3 orders of magnitude greater when you work it through. So therefore, you can say that's about 3 orders, because it's going to be about 10 to the 3. So 10 to the 30 divided by 10 to the 27 is going to be 10 to the 3. So it's 3 orders of magnitude greater. We can then use our equation for the Newton's law of gravitational attraction to put in all the values. Remember, it's r squared, so we get F is equal to 1.47 times 10 to the 25 newtons. The next question says, a space vehicle has a mass of 16,800 kilograms as in an orbit 900 kilometers above the surface of the Earth. Then we give the mass of the Earth, the radius of the Earth, so show the orbital speed of a vehicle is approximately 7,400 meters per second. Now the space vehicle moves from the orbit of 900 kilometers above the Earth's surface to an orbit 400 kilometers above the Earth's surface, where the orbital speed is 7,700 meters per second. Calculate the total change that occurs in the energy of the space vehicle. Assume that the vehicle remains outside the atmosphere after the change of orbit, and use the value of 7,400 meters per second for the speed in the initial orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we've got to say that the gravitational force of attraction is equal to the centripetal mass, so therefore we can work that then through to work out what v is. The orbital speed is going to be square root of gm over r, so as a result we can pop in all the values. Now again, remember, r is from the centre of the planet to the object, so we add the radius of the planet in there, so we get it out to be 5.4 times 10 to the 7 meters per second, sorry, 5.4 times 10 to the 7, so therefore square rooted is 7,396 meters per second. Now again, in this next one, we know that potential energy is gmm over r, and we also kinetic energy in this case is a half mv squared. So we can work out the change in potential by doing it at 900 kilometers and doing it at 400 kilometers. But again, remember, we've got to work from the center of mass of the Earth to the actual object. So we've got to work it through from the actual center of mass of the object. And that can work out that the potential energy is equal to minus 6.8 times 10 to the 10 joules. Now we then know kinetic energy is a half mv squared. Now we can work it through in terms of what the speed was at the start compared to the speeds at the end by doing your v squared like so. So we get our change in kinetic to be 3.81 times 10 to the 10 joules. We then subtract one from the other to find the change. So therefore we get minus 2.99 times 10 to the 10 joules. The next question says, the NASA space probe Dawn has travelled to and orbited large asteroids in the solar system. Dawn has a mass of 1,240 kilograms. The table gives information about 2 large asteroids orbited by Dawn. Both asteroids can be considered to be spherical and remote from other large objects. Dawn began orbiting Vesta in a circular orbit at a height of 680 kilometers above the surface of the asteroid. The gravitational force acting on Dawn at this altitude was 24.1 newtons. Show that the tangential velocity of Dawn in this orbit is 135 meters per second. Calculate the orbital period of Dawn. Then later in its mission, Dawn entered the orbit around Ceres. It then moved from a high orbit to a lower orbit around the asteroid. State what is meant by the gravitational potential of a point in space. Then Dawn has a gravitational potential of minus 1.29 times 10 to the 4 joules per kilogram in the high orbit, and then a gravitational potential of minus 3.22 times 10 to the 4 joules per kilogram in the lower orbit. Determine the change in potential energy of Dawn as a result of this change in orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we can then work out what the value of the tangential velocity is going to be, because you know it's a circular orbit, so therefore it'll be a centripetal force acting on the object. So F equals mv squared over r. We've got all the values except for v. Remember, r is from the center of mass of the planet, so we've got to include the radius of the planet in that. So r works through to be 135 meters per second. The orbital period is going to be v equals to be distance over time, which is 2 pi r over t. Again, we've got r, we know 2 pi, we've just worked out v to be 135, so therefore t equals 4.39 times 10 to the 4 seconds. Gravitational potential we know is the work done in moving a unit mass from infinity to that point in the gravitational field. That's a fact you've just got to remember. And then the change in potential energy is going to be equal to, when you're working it through, the change in potential, which you can work out to be minus 1.93 times 10 to the 4. Then the work done is the mass times by this change in potential. You've got the mass of the thing that's moving, which is Dawn in this case. So it's minus 2.39 times 10 to the 7 joules. The next question said Galileo was the first person to observe Jupiter's larger moons. Ganymede is Jupiter's largest moon. The distance between the centre of Ganymede and the centre of Jupiter is 1.07 times 10 to the 6 kilometres. Ganymede takes 171 hours to complete an orbit around Jupiter. Calculate the mass of Jupiter. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this through? Well, the first thing is you can work out what the orbital time is by doing 171 times by 60 times by 60, so it's 615,600 seconds. You can use the idea of the centripetal force is equal to the gravitational force of attraction to then get out an equation for gm equals 4 pi squared r cubed over t squared. That's Kepler's law of orbits. So therefore we can rearrange that and make m the subject, pop in all the values that we've got, so we get 1.91 times 10 to the 27 kilograms. The next question says Makey is a dwarf planet in the solar system. Makey has a mass of 3.1 times 10 to 21 kilograms and a radius of 715 kilometers. Calculate the gravitational field strength at the surface of Makey, and then the distance of Makey from the sun is similar to the average distance of the dwarf planet Pluto from the sun. A website states the time taken by Makey to complete one orbit of the sun is 20% greater than the time taken by Pluto to complete one orbit of the sun. Assess the accuracy of the website statement. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one, gravitational field strength, how do you work that through? It's gm over r squared. Pop in all the numbers, you've got the values given to you. Remember, we don't work in kilometers, we work in meters. Remember to square the value for r and we get 0.404 newtons per kilogram. Now the next question, we can work out what the angular speed is going to be by doing angular speed is equal to the square root of gm over r cubed, and we can work that through to be 6.5 times 10 to the minus 10 radians per second. We can then work out therefore the orbital time by doing t equals 2 pi over omega, and therefore we can work it out to be 9.67 times 10 to the 9 seconds, which is 307 years. So now we've got the time period for Makey, and we already had the time period for Pluto, both in years, because we're going to ratio them, it doesn't make a difference. So therefore we can ratio the two of them. 307 divided by 248 is 1.24. So the orbital time of Makey isn't actually 20% greater, it's 24% greater than that of Pluto. So it's not as accurate as we would like it to be. So that brings an end. Have a look at some questions on electrical fields. So the first question says, sketch the electrical field lines near a positive charge of plus Q, sketch the electrical field lines near a charge of negative Q, and then sketch the electrical field lines near a larger negative point charge. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important that you can be able to sketch electrical field lines correctly. So this first one, because it's a point charge, all the electrical field lines will meet at that point charge. Now you'll also note that it's going to be a radial field because it's a point charge. And then finally as well, the arrows should be pointing outwards because they will follow the field lines follow the direction a positively charged particle would take at that point in the field. So because positive repels positive, the field lines would be outwards because the positive charge would move outwards. Now for this next one, it's going to be the same pattern except the field lines are pointing inwards now because your negative point charge would attract your positive charge, which is the test in this instance, so therefore they'll be pointing inwards. Now if you've got a larger negative point charge, well, it tells you you've got a stronger force of attraction, so it's still an arrow pointing inwards, but to show field strength in this context, you would have to have your field lines closer together because the density of the field line indicates the field strength, so you'd have more field lines per unit area. The next question says, draw the electrical fields between the following charged objects. You've got 5 different pictures there. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to remember that the field lines will always go from a positive to a negative, because that's the direction in which the objects will move in, because that's the direction the test charge would move in. So you'll see here that you've got parallel lines in the plate, because between two charged plates you get a parallel field lines, so you get a uniform field between two parallel plates. They'll also curve slightly outwards once you pass the plate boundaries. The next one, again, you've got the field lines going from the positive to the negative, like so. Again, here you've got the radial field going outwards, meeting that plate there to go through like that. Again, the opposite direction in terms of the arrows for the negative charge, because you obviously got because obviously the field lines will move in the direction that the test positive charge will be in. And then finally here you've got your radial field all pointing outwards, because it is a positive charge. The next question says, 2-point charges of 2 nanocoulombs are separated by a distance of 1 centimetre. Calculate the electrostatic force experienced by each charge. Then, without detailed calculation, state and explain how your answer to the first question would change when the same charge is separated by 3 centimetres. Now, the electrical field at a distance of 5 centimetres from the centre of a charged dome is 3 times 10 to the 4 newtons per coulomb. Calculate the charge on the dome, and then calculate the force between a helium nucleus and a gold nucleus at a distance of 2 times 10 to the minus 14 meters. A gold nucleus has 79 protons and a helium nucleus has 2 protons. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is using Coulomb's law, which is F is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Again, this equation is given to you in your equation sheet, and epsilon 0 is a constant given to you on your equation sheet as well. You pop in all the numbers. Now remember, nano means 10 to the minus 9, and then remember we'll turn centimeters into meters, so it'll be 0.010, and remember it's r squared. So you pop in the values and it's 3.6 times 10 to the minus 4 newtons. Now you'll see from this equation F is directly proportional to 1 over r squared. So when r increases by a factor of 3, when distance or separation increases by a factor of 3, well, then the force will decrease by a factor of 3 squared, which is 9. So you divide your previous answer by 9, so it's 4 times 10 to the minus 5 newtons. The next one, again, we're using the equation to work it through. Now, in this case, we're actually using the electrical field strength equation, which is electrical field strength is equal to Q over 4 pi epsilon 0 r squared, which is the electrical field strength for a radial field, which it will be. It's a charged dome. So you can work it through, make Q the subject, pop in all the values. Remember, centimeters turns into meters. It's a squared for r as well, so it's 8.3 times 10 to the minus 9 coulombs. Then this last one, we are using Coulomb's law again. F equals Q1 Q2 over 4 pi epsilon 0 r squared. Pop in all the numbers. Remember, the proton has a charge of 1.6 times 10 to the minus 19 coulombs. That's a bit of revision from the particles topic. Pop in all the values. Remember, it's r squared, and we get 91 newtons as our force between them. The next question says, calculate the electrostatic force and then the gravitational force of attraction between 2 protons at a separation of 2 femtometers inside a nucleus. Compare the magnitudes of the 2 forces and whether they're attractive or repulsive. And then in Ernest Rutherford's alpha particle scattering experiment, helium nuclei were fired at a gold nucleus. Calculate the repulsive force between the helium nucleus and a gold nucleus when they've got a separation of 50 femtometers. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in this first one, we're using the Coulomb's law for the electrostatic force, and we're using the gravitational force. We're using the Newton's law of gravitation for the gravitational force. So we use F equals Q1 Q2 over 4 pi epsilon 0 r squared. Pop in all the values. Remember that you are given the charges there of both of them, okay, and you can work that through. It should be 1.6 times 10 to the minus 19. Okay, so they will work through. Okay, and you can work it out like that, and you get 57 newtons. Now again, remember, because they are both the same charge, there'll be repulsive force. You do the same for the gravitational force, which is F equals G m1 m2 over r squared. Pop in all the values. Again, you're given the masses of the protons and neutrons on the equation sheet. You can get that through to be 4.7 times 10 to the minus 35 newtons, and gravity is always an attractive force. So you can do so what you can do is you can find the ratio between the two of them, because one is under the ratio of 10 to the 1, because it's in the tens orders of magnitude. One is 10 to the minus 35, so therefore the electrostatic force is 10 to the 36 times larger than the gravitational force. Again, in this next one, we're using Coulomb's law, popping in all the values, working it through, and we get our answer to be 15 newtons out. The next question says, an electrical engineering technician has been asked to carry out an investigation into two charged particles. The technician has carried out some investigation and has found that the charge on the first particle is measured as 0.3 coulombs, which has a repellent force of 172 newtons on a second particle. The second particle is 1.2 meters away from the first particle. Calculate the charge on the second particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one again we're using Coulomb's law, so we're saying F equals Q1 Q2 over 4 pi epsilon 0 r squared. Now we're going to use that equation and rearrange it to work out Q2, the charge on the second particle. So you can say Q2 is equal to F times by 4 pi epsilon 0 r squared over Q1. Pop in all the values, then work it through, and we get 9.17 times 10 to the minus 8 coulombs. Now it's important to note that this is a positive charge. How do we know that? Well, because it is producing a repellent force with another positively charged particle, so therefore it itself must be positively charged. The next question says, for the point charges of plus 25 microcoulombs and plus 100 microcoulombs separated by a distance of 60 millimeters, calculate the magnitude of forces exerted on the plus 25 microcoulomb charge by the 100 microcoulomb charge. Then 2 point charges plus 4.0 nanocoulombs and minus 80 nanocoulombs are placed 80 millimeters apart. Calculate the magnitude of the force exerted on the plus 4 nanocoulombs by the minus 8 nanocoulombs charge. State the nature of the force. And then 2 point charges are placed a distance apart. The force in each charge at this distance is 40 newtons. The distance between the charges is doubled. Determine the new force that each charge experiences. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we're using Coulomb's law. F equals Q1 Q2 over 4 pi epsilon 0 r squared. You can pop in all the values and you can work it through in case you know that we're going to be turning our microcoulombs into coulombs. Pop in all the values through and we get our answer out to be 5.5 times 10 to the 4 newtons. Again, we're using Coulomb's law here to work it through, and we work it all out by popping in the numbers. We know nanocoulombs means 10 to the minus 9, and we're doing r squared. Remember, millimeters turns into meters. So that's 10 to the minus 3. So we get our answer out to be minus 4.5 times 10 to the minus 5 newtons. Now it's an important idea to note that when you've got a negative force, in this particular instance it's an attractive force, and if you get a positive force in this instance it's a repulsive force. So because it's a negative value, you know the nature of the force is attractive. Now in this next one we know the relationship that F is directly proportional to 1 over r squared. So therefore if the distance doubles, the force will decrease by a factor of 2 squared, so it's 1 over 4. So therefore if it was 40 newtons, it'll now be 10 newtons because the force has decreased by a factor of 4. The next question says, two parallel plates are 4 centimeters apart and have a potential difference of 2.5 kilovolts between them. Calculate the electrical field strength between the plates. A small piece of dust carried a charge of plus 2.4 nanocoulombs moving to the space between the plates. Calculate the force on the dust particle. Then the mass of the dust particle is 4.2 micrograms. Calculate the acceleration of the particle towards the negative plate. And then a small sphere carries a charge of 2.4 times 10 to the minus 9 coulombs. Calculate the electrical field strength at a distance of 2 centimeters from the center of the sphere and 4 centimeters from the center of the sphere. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we're using the electrical field strength equation. Now, because it's between two parallel plates, it's a uniform field, so we can use the equation E is equal to V over D, where V is the potential difference and D is the separation of the two plates. Remember, we convert kilovolts into volts, and we convert centimeters into meters, so we get our answer out to be 6.25 times 10 to the 4 volts per meter. Now in this next question again, we can use the general equation now for the electrical field strength equation, which is E equals F over Q. So therefore F equals EQ. We've just worked out what E is in the previous question, the electrical field strength. Multiply it now by the charge. Remember, nanocoulombs must turn into coulombs, so you work it through to be 1.5 times 10 to the minus 4 newtons. Now again, you're given the mass here and has to work out the acceleration. Now because you've got a uniform field, it tells you you'll have a constant constant acceleration, so it can actually help and use the equation A equals F over M, or F equals ma. We've got our value for F from the previous question. We know it's 1.5 times 10 to the minus 4 divided by the mass. Now again, we turn micrograms into grams, but so it's 4.2 times 10 to the minus 6, so it's 3.6 times 10 to the 4 meters per second squared. In this next question, we're now, because it's a sphere, have to use the radial field strength equation. So that is E equals Q over 4 pi epsilon 0 r squared. So you pop in all the values. Remember, it says 2 centimeters, but we don't work in centimeters in physics, we work in meters. So you've got to pop it through to be 0.02. Remember, it's r squared, so it's a squared value, so we get 5.4 times 10 to the 4 volts per meter. Now in this next one, you can work it through by either doing E equals Q over 4 pi epsilon 0 r squared, or you could say the relationship is E is directly proportional to 1 over r squared. So therefore, if r is doubled from 2 to 4, well therefore E is going to quarter, because it's proportional to 1 over r squared. So therefore you quarter the previous value, and it's 1.4 times 10 to the 4 volts per meter. The next question says, the electrical field strength is constant close to a conductor. State the field pattern produced by the electrical field lines. Then below shows the field pattern correctly drawn by a student, but with the charges on the sphere and the plate omitted. State the charges on the sphere and the plate, and then suggest how the field pattern below would change if the sphere shown below had a greater charge. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, you've got to understand, what does a uniform field look like? So a uniform field will look like the lines being parallel and equally spaced, because the density of the field line shows the field strength. So if you've got a uniform field strength, you've got a uniform field line density. Now in this next one, you can note that the arrows are pointing away from the sphere. Now the arrows point in the direction that a positive test charge would move in. So if they're pointing away from it, it must be getting repelled. So it must be from another positive charge. Now they're going towards the plate, so it must be attracted to the plate, so that will be a negative charge. Now again, how can we indicate what the field would look like? Well, it would still be radial, because it's still going to actually be a sphere, but there would be more field lines at the sphere in that particular area, because the density of the field line shows the strength of the field. The greater the charge, the stronger the field, the more field lines there are per centimetre squared. So the next question says, in a simple model of a hydrogen atom, an electron orbits a proton. The average distance between an electron and a proton in a hydrogen atom is 5.3 times 10 to the minus 11 meters. Firstly, calculate the electrical force on the electron at this distance. Secondly, state the electrical force on the proton. And thirdly, calculate the acceleration of the electron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we need to work out the force, so we're using Coulomb's law, so F equals Q1, Q2 over 4 pi epsilon 0 r squared. We know the charge of the electron and the proton is given to you on the equation sheet, but you should memorise from the particles topic, 1.6 times 10 to the minus 19. You pop in all the values, remember we're squaring r, so we get 8.2 times 10 to the minus 8 newtons. Now this question is very interesting, because it probes your understanding of what you're working out. Now in the Coulomb's law, you're working out the force on both of the charged objects. So both the electron and the proton have this 8.2 times 10 to the minus 8 newtons of force acting upon it. Then finally, we know the acceleration is F equals ma, so A equals F over m. So you do F, which you've just worked out, over the mass of the electron. Once again, it's given to you on the equation sheet, 9.11 times 10 to the minus 31 kilograms. So you get 9.0 times 10 to 22 meters per second squared. The next question says, an alpha particle travelling through a partial vacuum is 1 centimeter from an electron. What force acts between them? Is it attractive or repulsive? Then two spheres with identical charges experience a repulsive force of 2.8 micronewtons when they are 12 centimeters apart. What is the value of this charge? So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we're trying to work out the force. Coulomb's law, F equals Q1, Q2 over 4 pi epsilon 0 r squared. You can then work through the values there. Now you'll actually notice that the values from the electron, so the charge there for one of them should be negative 1.6 times 10 to the minus 19. So you pop it through like that, you would actually get a minus 2.3 times 10 to the minus 24 newtons, so the force will be attractive. Again, here we're trying to work out the charge. Now it's important to know you've got two identical charges. So even though we know F equals Q1, Q2 Q2 over 4 pi epsilon 0 r squared. We can say Q1, Q2 are the same value, so therefore it's just Q squared. You can pop in all the numbers. Remember, 2.8 micronewtons becomes 2.8 times 10 to the minus 6. Remember, 12 centimeters becomes 0.12 meters. It's r squared. You pop it in, so you get our Q squared to be plus or minus 4.484 times 10 to the minus 18. Square root that, and we get plus or minus 2.12 times 10 to the minus 19 coulombs. It could be both positive or it could be both negative, okay, to get that repulsive force. The next question says, figure 23.22 shows a conducting sphere of a radius 0.80 centimeters carrying a charge of plus 6 times 10 to the minus 8 coulombs resting on the balance. Firstly, calculate the electrical field strength at the surface of the sphere. Then an identical sphere carrying a charge of minus 4.5 times 10 to the minus 8 coulombs is held so that at its centre it's 5 centimeters vertically above the centre of the first sphere. Calculate the electrical force between the two spheres, then calculate the new reading on the balance. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're working out electrical field strength and it's on the sphere. So we've got to use the radial field strength equation. So E is going to equal to Q over 4 pi epsilon 0 r squared. Pop in all the values. Remember, 0.80 centimeters becomes 0.8 times 10 to the minus 2 meters. Pop in all the values. You remember r squared, so you get 8.4 times 10 to the 6 volts per meter. Now we're trying to, in the second one, work out the electrical force. So we've got to use Coulomb's law. So we're going to say F equals Q1, Q2 over 4 pi epsilon 0. Pop in all the numbers. Again, now remember, 5 centimeters becomes 5 into meters, so it's 5 times 10 to the minus 2 meters. It's a squared value, so you work it through and you get 9.72 times 10 to the minus 3 newtons. Now it's also important to know what's the new reading on the balance. Well, you have the original reading is 0.0482, but now you've got this electrical force that is acting in the opposite direction to the force of gravity pushing down on the balance. So therefore you've got to subtract it from there, so you get 0.0384 newtons. The next question says, in a simple model of a hydrogen atom, an electron orbits a proton. The average distance between an electron and a proton in a hydrogen atom is 5.3 times 10 to the minus 11 meters. Firstly, calculate the electrical force on the electron at this distance. Secondly, state the electrical force on the proton. Third, calculate the acceleration in meters per second squared of the electron, and then show that the total energy of the electron is 13.6 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, so we're working out the electrical force. So once again, we're doing Coulomb's law. So we can say F equals Q1, Q2 over R squared. Pop in all the values. Remember, it's R squared. Pop it in there, 8.2 times 10 to the minus 8 newtons. That's the same force on both the electron and the proton, as we discussed earlier. And we can say F equals MA. So A equals F over M. Once again, you're given M on the equation sheet. So you can pop that through to be 9.0 times 10 to the 22 meters per second squared. Now, how to work out the total energy of the electron? Well, it's orbiting, and if you remember, we have the idea that in the total energy of an orbit, it's the kinetic energy plus that potential energy. We also know that the work done is going to be the charge times by the potential difference. So therefore, what we can say is that the energy is going to be equal to the kinetic energy, a half mv squared, minus E squared over 4 pi epsilon 0 r, because that's going to be our electrical potential energy, because it's going to be your field strength multiplied by another charge to work it through there. You can then rearrange that and you can work it all the way through, as you can see on the screen, until E equals minus E squared over 8 pi epsilon 0 r. Pop in all the values. Now remember, E in this context is actually the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs. Pop it all through and you get your answer out to be 2.2 times 10 to the minus 18 joules. You've also got to be aware of how to convert from joules into EV, and you can do that by dividing by the charge of one electron, which is 1.6 times 10 to the minus 19 coulombs. So you get our answer out to be 13.57 EV. The next question says, determine whether or not the electron initially at rest will reach point R, shown in the diagram below. Both positive charges are 0.60 meters from R, and explain your reasoning. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this one through? Well, it's all about energies again. So you can work out your new potential energy when you're working through from these values. So you can say it's going to be 2 times by minus 5.76 times 10 to the minus 18 plus 2.88 times 10 to the minus 18. So therefore it's going to equal minus 8.64 times 10 to the minus 18 joules. So therefore when we work it backwards, because we can say that, well, potential is going to be this energy over charge. So we divide it then by the charge of the electron, 1.6 times 10 to the minus 19, and we get our answer to be 54 volts. Now the potential energy has to be lower because the negative values are the same, but the positive is a smaller value. So therefore the new potential is higher than the original, but because the positive potentials are the same, but that negative potential is got smaller. It's gone from 36 volts to 54. So it can either travel to a lower potential energy, or gain kinetic energy, or travel to a higher potential because that electron is negative. The next question says, below shows two parallel plates 10 centimeters apart. So calculate the electrical field strength between the plates. The potential difference across the plates is 40 volts. And then you calculate the work done on an electron as it moves from plate A to plate B. And then an electron with a kinetic energy of 20 eV is injected into a field at point X. Describe and explain its motion in the space between A and B. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, electrical field strength is between two plates, so therefore it's a uniform field. We can use that uniform equation, E equals V over D, but remember we don't use centimeters, we use meters, so it's 40 over 0.01 meters, 400 volts per meter. Work done is going to be the charge times by the potential difference. You'll see the potential difference from the diagram is 40 volts, because we go from 0 to 40, multiplied by the charge of the electron, and we get 6.4 times 10 to the minus 18 joules. So the next question, well, you'll notice that the electron is going to be attracted by B, if you look on the picture, and it's going to be repelled by A. You can tell that because it's going to want to go to the positive charge, which is on the positively charged part of the plate, which is the 40 volts one, so it'll go towards the right. So what will happen is, as it's injected in, the electron will decelerate. It'll not go all the way to the 0 volts, to the A plate. What it'll do is it'll stop at the halfway point, okay, and then it'll return. The next question says, a maintenance engineer services power coating equipment that works on the principle of electrostatic attraction. The charges on two particles have been recorded. The force between the two particles is 8.2 times 10 to the minus 8 newtons. Calculate distance r between the two charged particles. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we're trying to work out a value when we've been given a force. So we can use Coulomb's law. So we can say F equals Q1 Q2 over 4 pi epsilon 0 r squared. We can therefore make r the subject, but it's going to be r squared. So you work out what r squared is going to be, popping in all the numbers. Now you're given the charges in the diagram, and you're given the distance and you're given the force in the question. So you get r squared to be 2.24 times 10 to the minus 15. Square root that to get your value of r, which is 4.7 times 10 to the minus 8 meters. The next question says, a student is investigating the electrical potential around a point charge Q. Point P is at a distance of 0.65 plus or minus 0.2 meters from Q as shown in the diagram. The potential at point P is 2.1 plus or minus 0.1 volts. Firstly, calculate the value of the point charge. Then secondly, calculate the absolute uncertainty in the point charge. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know what the potential is. We want to work out the charge. So the equation for potential is V is equal to Q over 4 pi epsilon 0 r. You're given that equation on your equation sheet. Rearrange that, make Q the subject, pop in the values, and we get our answer out to be 1.5 times 10 to the minus 10 coulombs. Now you'll notice for Q, it's going to work through to be V times by 4 pi epsilon 0 r. So that tells us we work out firstly the percentage uncertainty in r, which is 0.02 over 0.65. It's the absolute uncertainty divided by the value times by 100, so we get 3%. We do the same for the percentage uncertainty in the potential, which is 0.1 over 2.1 times by 100 is 4.8%. Because you're multiplying the two values in your equation for Q, you'll add the two percentage uncertainty, so that gets you 7.8%. So therefore you work out 7.8% of the answer, which is 1.5 times 10 to the minus 10. So you get 1.17 times 10 to the minus 11 coulombs. The next question says protons are accelerated by an electrical field between the metal plates A and B in a vacuum. Part of the apparatus used is shown. Firstly, explain why the protons are accelerated by the electrical field. Then, a proton is travelling at a speed of 3.8 times 10 to the 5 meters per second at plate A. Show that the kinetic energy of the proton at plate A is 1.2 times 10 to the minus 16 joules. The potential difference between plates A and B is 2.8 kilovolts. Calculate the work done on the proton as it accelerates from plate A to plate B. Then determine the speed of the proton at plate B. Then the distance between A and B is now doubled. The potential difference between A and B is unchanged. Another proton with the same initial speed at plate A is accelerated between the plates. State what effect, if any, this has on the speed of the proton at plate B. You must justify your answer. So pause the video now, then unpause the video when you want to go through your answers. Right, so why is it accelerated? Well, the protons are positively charged, so therefore, because they're charged, they'll experience a force in an electrical field, that's the definition of a field, that will cause acceleration. The kinetic energy, it's a half mv squared, so it's a half times by the mass of the proton given to you on the equation sheet, multiplied by its speed squared, pop it all through, and you get 1.2 times 10 to the minus 16 joules. Then this next question, the work done, is going to be the charge times by the potential difference. So you've got your charge of your proton, you know that, it's given to you on the equation sheet, 1.6 times 10 to the 19, times by the potential difference, 2.8 times 10 to the 3, because we don't work in kilars, we just work in volts. So therefore you get 4.5 times 10 to the minus 16 joules. So how can you work out the speed? Well, we know that the kinetic energy is going to be the initial kinetic energy, which you worked out in the second part, plus this work done, because work is being done on the object as it's accelerated in the plates, in between the plates, sorry, when it's in the field. So now we've got a new kinetic energy, and then we can say it equals a half mv squared. So we know what that value is, we know the mass, we know that we want to work out the velocity, so we rearrange it, we make v the subject, and we get 8.3 times 10 to the 5 meters per second. Now what effect will this have on the speed of the proton? It'll have no effect, because the work done on the proton is the same, because the distance is not a factor in how much work is done. And if it's another proton that goes in at the same initial speed, it'll have its same starting kinetic energy. So therefore the only work done on it is q times by v. It has the same charge, it has the same potential difference of the plates between it, so therefore the work done is the same. The next question says, firstly, define what is meant by the electrical field strength at a point. Then in a particle accelerator, a proton initially at rest is accelerated between two metal plates as shown in the diagram below. Firstly, calculate the force on the proton due to the electrical field. Then calculate the work done on the proton by the electrical field when it moves from plate A to plate B. Then state the energy gained by the proton, and then assuming that all this energy is converted to kinetic energy of the proton, calculate the speed of the proton when it reaches plate B. So pause the video now, then unpause the video when you want to go through your answer. Right, definition of electrical field strength, you've just got to learn it. It is the force per unit positive charge. Remember, we always define electrical field strength quantities in terms of test positive charges. Everything is done in terms of positive charges. The force will be equal to, well, it'll be equal to EQ, the electrical field strength, times by the charge. So, but first we've got to work out what the electrical field strength is. Now it's between two metal plates, that tells you it's a uniform field, so we can use that uniform field strength equation of E equals V over D. So we can pop in all the values, we got those from the diagram, so you can work that through, multiply them by the charge to work out the force to be 1 times 10 to the minus 11 newtons. Work done, we've just done this before, work done is going to be F times by it's going to be times by the displacement. That's an equation you've looked at when you've done mechanics. So work done is going to be force times by displacement in the direction of the resultant force it acts in. So you've got that force, you know the distance it's moved there, so the work done is 8 times 10 to the minus 13 joules. That's the work done on the proton, so that's how much energy is gained by the proton, because work done means either energy gained by the object or lost by the object. And then to work out the speed, you can say kinetic energy is a half mv squared. Okay, you know the work done is 8 times 10 to the minus 13, which in this instance is the kinetic energy gain. So you can work out V. You know the mass of the proton before, because it's given to you in the equation sheet. You pop it all through and you get 3.1 times 10 to the 7 meters per second. So that brings the end to our look at some capacitance questions. The first question says a 470 microfarad capacitor is connected across the terminals of a battery of EMF 9 volts. Calculate the charge on the plate of the capacitor. Secondly, they calculate the potential difference across the terminals of a 2200 microfarad capacitor when it has a charge of 0.033 coulombs on its plates. And then finally calculate the capacitance of a capacitor if it stores a charge of 2 coulombs when there is a potential difference of 5000 volts across its plates. So pause the video now, then unpause the video when you want to go through your answers. Right, so this is using that key equation that capacitance is equal to charge over potential difference. So if we have a look at this particular equation, we can rearrange it and we can make charge the subject. So we can say Q equals CV. We turn micro into farads, so it'll be times 10 to the minus 6. So we get 4.2 times 10 to the minus 3 coulombs. We rearrange this one to make V the subject. V is Q over C. Once again, we turn micro into the normal farads by times 10 to the minus 6, and we get 15 volts out. Then finally we say capacitance is charge over potential difference, so we work it through and we get 4 times 10 to the minus 4, which is 400 microfarads. The next question says a student inserts 2 bare copper wires into a lump of wet clay. The clay is dried out. The student suggests that he has made a capacitor. Explain whether this is correct. The next question says the charge stored by a capacitor connected to a 12 volt battery is 2.4 times 10 to the minus 5 coulombs. Calculate its capacitance in farads and then microfarads. A capacitor stores a charge of 30 picocoulombs when the potential difference across is 3.2 volts. Calculate the charge stored in picocoulombs when the PD is increased to 8.7 volts. Then the capacitor of capacitance 200 microfarads is connected to a 10 volt supply. Calculate the number of electrons removed from the positive plate of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one you've got to understand what the definition of a capacitor is. Yes, it is a capacitor because it consists of 2 metal electrodes separated by an insulator, which is what we define our capacitor to be. The next one, once again, we use the equation capacitance equals charge over potential difference, pop in the values and we get 2 microfarads. In this next one we then say, well, looking at the equation, if we've got a constant capacitance, we can say that Q is directly proportional to V. So when we work it through in the terms of ratios, we can say it's 81.6 picofarads. And then the last one here, what you can do is use Q equals CV, work it out to be 2 times 10 to the minus 3 coulombs. Remember, microfarads turns into farads by times 10 to the minus 6. We then work out how many electrons we've got by taking our overall charge, dividing by the charge of an electron, 1.6 times 10 to the minus 19 coulombs, and we get 1.3 times 10 to the 16 electrons. The next question says a capacitor of capacitance 0.010 farads is connected to a 1.5 volt cell. Calculate the number of electrons delivered by the cell to the capacitor. Then an uncharged capacitor of capacitance 1500 microfarads is connected in a circuit. The current in the circuit has a constant value of 80 microamps. The capacitor is charged for a time of 60 seconds. Firstly, calculate the charge and the PD across the capacitor after a time of 60 seconds, and then sketch a graph of PD across the capacitor against the time over a period of 60 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, once again, Q equals CV, work it through, divided by the charge of an electron, 1.6 times 10 to the minus 19, we get 9.4 times 10 to the 16 electrons out. In this next one, we've got to use an equation from electricity. Charge is equal to current times by time. So we turn micro into amps by times by 10 to the minus 6. So we work out our charge to be 4.8 times 10 to the minus 3 coulombs. We can then say V equals Q over C to get 3.2 volts. Now if you look on here, how will the potential difference go against the time? Well, you'll notice that it'll be a straight line graph through the origin, and you'll get a value of V equals 3.2. It's 60 seconds because from the answer to our previous question. The next question says a 22 microfarad capacitor is charged by using a constant current of 2.5 microamps to a PD of 12 volts. Calculate the charge stored on the capacitor at 12 volts, the time taken. A capacitor is then charged by a constant current of 0.5 microamps to a PD of 5.0 volts in 55 seconds. Calculate firstly the charge stored and then secondly the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one again we're using Q equals CV, so we will put them in. Remember, micro turns into the farads by times 10 to the minus 6, so we get 2.64 times 10 to the minus 4 coulombs. Again, we can say Q equals IT, so therefore T equals Q over I. We've already got Q from the question, okay, and we've got I from the question, so we can work it through. Remember, we worked out Q in our previous answer, so we can pop it through and we get 105.6 seconds. In this second question, once again, Q equals IT. So we know I, because we can work it through, be 0.5 times 10 to the minus 6, times by the time in seconds, 55, so you get 2.75 times 10 to the minus 5 coulombs. And then we can work out the capacitance by saying C equals Q over V. We worked out Q in our previous question. We know the value of V from the information given, it's 5, so you get 5.5 times 10 to the minus 6 farads. The next question says, a capacitor is made from a plastic bin bag sandwiched between two sheets of aluminium foil 60 centimeters times by 30 centimeters in size. The bin bag is 0.080 millimeters thick. Plastic has a relative permittivity of 4.0. Calculate the capacitance of this capacitor. Then the capacitance of a parallel plate capacitor is 8 picofarads. State and explains capacitance when the separation between the plates is doubled, then the area of overlap between the plates is halved and their separation is also halved. Then a capacitor is made from two circular plates of diameter 20 centimeters. That are separated by an insulator. The insulator has a relative permittivity of 4.0 and a thickness of 1.2 millimeters. The capacitor is connected to a 6-volt battery. Calculate the maximum charge stored by the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one you've got to use the parallel plate capacitor equation. So that is C equals the area times by ER E0 over D, where ER is our relative permittivity and E0 is the permittivity of free space, which is a constant given to you on the equation sheet. You pop in all the values given to you in the question. Now remember, you have to turn centimeters into meters and you have to convert millimeters into meters as well. So you can pop those through as shown in the working out on the screen. Pop in our values and we get 80 nanofarads. The next one, you can see from the equation above that C is directly proportional to 1 over D. So therefore if D is doubled, well, C will then half. So it's gone from 8 picofarads to 4 picofarads. Once again, we can see from the equation above that C is directly proportional to A, but C is directly proportional to 1 over D. Now, because A and D will both change by the same magnitude, the same factor, they'll cancel each other through, so we get 8 picofarads. This next question again, we're going to have to use our equation from above, the parallel plate capacitor equation, but this time we're going to have to work out our area. Now we can see that the area is going to be just for one of the plates, so we do pi r squared. Now we've got the diameter in centimeters, so we convert that to a radius, which is 10 centimeters, and then convert it into meters, so 0.10 meters, pop in all the values, work it through, and we get 9.2 times 10 to the minus 10 farads. We can then work out our charge stored by saying Q equals C times by V. We've just worked out the capacitance, we know the voltage because it's given in the question, we get 5.6 nanocoulombs. The next question says, the diagram shows a capacitor constructed from two plates separated by glass. Firstly, calculate the area of one of the capacitor plates, state your answers in meters and then in standard form, and then the relative permittivity of glass is 3.7, calculate the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the trick you're going to have to do is to work out the area is to times the length by the breadth, but these values are given in millimeters and you've got to put them into meters. So you pop them into meters, multiply them together, and we get 1.1 times 10 to the minus 3 meters squared. Then the second one, we'll once again use our equation here. So we can see it's going to be the parallel plate capacitor's equation. So it's 3.7 times by the permittivity of free space times by the area we just worked out, divided by the separation in meters, which is 0.002, so you get 18.4 picofarads. The next question says, a 120 microfarad capacitor is charged through a 1 mega ohm resistor using a power supply of a constant output of 3.0 volts. The initial PD across the capacitor is 0. After a time equal to 1 time constant, calculate the PD across the capacitor. Then for the circuit in this previous question, calculate the PD across the capacitor at a time of 3 minutes. Then an uncharged capacitor of capacitance C is charged through a resistor of resistance R using a battery of EMF V0. Derive an equation for the time taken t for the PD across the capacitor and the resistor to be the same. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to use our equation for a charging capacitor. So we say that V equals V0, which is the starting, which is the EMF, sorry, or the power, the output of the power supply. Okay, multiplied by 1 minus e to the power minus t over RC. Now remember, RC is a time constant, so after one time constant, t is going to equal RC. So it's going to be RC over RC, which is going to cancel through to be 1. So therefore what we're going to get is we're going to say it's going to be 3 times by 1 minus e to the power minus 1. Pop that through and we get 1.9 volts. This next question, we can see what our time constant is because we've got R and we've got C, so we can work out the time constant to be 120 times 10 to the 6. Okay, so minus 6, my apologies, because it's microfarads times by 1 times 10 to the 6 because it's mega ohms, so we get 120 seconds. So again, we're using our equation here where we know RC to be 120, we know the time to be 180 because we don't work in minutes in physics, we work in seconds. We then pop in all the values and we get 2.3 volts. And then here we're using this equation, we can work it through here. Now it's important to note that we can say that when you work it through with the laws of logs, you'll see a half equals e to the power minus t over RC. Pop in all the values through. Now remember, to get rid of an exponential from e, we do natural log, so therefore log of a half will equal log e to the power minus t over RC, so that will cancel through. Bring that power term down to be just a normal term, so it's minus t over RC. We work it through, so t therefore equals log 2 or 0.69 RC. The next question says, a trainee electrical engineer has constructed a flat plate capacitor. The dielectric between the plates has a permittivity of 40 times 10 to the minus 12 farads per meter. The capacitor is connected to a 6 volt DC supply. Calculate the charge stored on the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question there's a lot of different equations we're going to have to use. Firstly, we're going to use the parallel plate equation because we're being given the relative permittivity and the separation and the areas. Remember the dimensions for the area. Now remember, they're given all in millimeters, so you have to convert them. So we use our equation C equals ERE0 over D. We work it all the way through and we get the capacitance out to be 14.4 times 10 to the minus 12 farads. We then say Q equals CV, and we want to work out the value of Q. So we pop in all the values, we know V is equal to 6, so it's 86.4 times 10 to the minus 12 coulombs. The next question says, a 220 microfarad capacitor is charged to 2.0 volts, then discharged through a 100 ohm resistor. Calculate the maximum current in the circuit and the maximum charge stored by the capacitor. Then calculate the time constants for these circuits. C equals 0.010 farads and R equals 1.0 kilo ohms. And then capacitance is equal to 4,700 microfarads and resistance is equal to 1.5 mega ohms. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how to work out the current? Well, again, use your equations from electricity. I is equal to V over R, so therefore it's going to be 2 over 100, so it's 2.0 times 10 to the minus 2 amps. Therefore, charge Q equals CV. Well, we know the capacitance because it's given in the question, so we're going to convert 220 microfarads to 220 times 10 to the minus 6, multiply it by our value for the potential difference there, 2, so we get 4.4 times 10 to the minus 4 coulombs. Now in this next one, what can we do? We can therefore say T equals RC. That's our equation for a time constant. So T equals RC, so it's 0.01 times by 1,000 because kilo turns into ohms by times it by 10 to the 3, so it's 10 seconds. And this next one, we turn micro into farads by times 10 and 10 to the minus 6. We turn mega into just ohms by times it by 10 to the 6. The 2 will cancel through and we'll get 7.05 times 10 to the 3 seconds. The next question says, a fully charged capacitor is discharged through a resistor when the switch is closed. Firstly, calculate the time constant for the capacitor. Secondly, when the switch is closed, the capacitor begins to discharge. When T equals 0, the voltage across the capacitor is 12 volts. Calculate the voltage across the capacitor after 20 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know T equals RC. So we pop in all the values. You've got R from the question. Remember, kilo turns into ohms by 10 to the 3. You got given capacitance in the question. Micro turns into farads by times 10 to the minus 6. So you pop it through to get 7.26 seconds. Then in this next question we can say, right, well, V equals V0 e to the power minus T over RC. We know RC is the time constant, so it's 7.26. We know that V0 is the EMF, or the power source voltage, so therefore that is going to be 12, because V0 is the maximum possible voltage the capacitor could have, so therefore that is 12. So therefore you pop in all the values. T is 20 seconds, so you get 0.763 volts. The next question says, in the 18th century, a scientist called Gordon made the first device that used electrostatic forces to produce continuous motion. A demonstration of the principle of Gordon's device is shown. A light conducting sphere of radius r is suspended from an insulating thread between two parallel metal plates. A large potential difference V is applied between the plates. There is an electrostatic force on the sphere when the sphere is charged. The capacitance C of the sphere is given by C equals 4 pi epsilon 0 r, where r is the radius of the conducting sphere. The sphere is charged by touching it onto one of the plates. The plates are a distance d apart. Calculate the electrostatic force exerted on the sphere. V equals 4,500 volts, D equals 5.0 centimeters, and R equals 3.5 centimeters as well. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question you're going to have to use all the equations given to you. So you're given the equation for capacitance, and you know that you've got R, and you know 4 pi epsilon 0. So how do you work it through? So you say, right, in this first one, 4 pi epsilon 0 times by R. In this instance R is 3.5 times 10 to the minus 2, because it's centimeters into meters. So we get our answer to be 3.89 times 10 to the minus 12 farads. We can then say Q equals CV, so therefore we can work out Q. We've just worked out C. We know V is 4,500 volts, so you get 1.75 times 10 to the minus 8 coulombs. We then know from the electrical fields module that a capacitor is a uniform electrical field, so its uniform electrical field strength is V over D. Pop in those values. We know D to be 5 times 10 to the minus 2 meters, so it's 9 times 10 to the 4 volts per meter, and therefore F equals E times by Q. That is the electrostatic force equation. So you pop in those values and you get 1.58 times 10 to the minus 3 newtons. The next one says a 1000 microfarad capacitor is connected in series with a 6 volt battery, a switch, and a 22 kilo ohm resistor. Calculate the charge of the capacitor after 10 seconds and the potential difference across the capacitor after 10 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we're looking at how much, because it's charging up because it's connected with the battery, so we're going to use the charging equation, that Q equals Q0 times by 1 minus e to the minus t over RC. Now we can work out what Q0 is, because it's the maximum possible charge, therefore its capacitance times by the maximum possible potential voltage or potential difference, which is that of the power source. So you can pop in those values. We've got the capacitance of the capacitor, we've got the EMF of the power source or the potential difference of the voltage, work it all through, pop in all the values, okay, in the equation. Now remember, we can work out what our time constant is, because we can say time constant equals RC, and therefore we can pop in all the values, we get them through, we get 2.2 times 10 to the minus 3 coulombs. This next question, we can just use the equation V equals Q over C. We've got the capacitance in the question, you've just worked out Q, so therefore you can work it all through and we get 2.2 volts. The next question says a 1000 farad capacitor is charged by connected in series with a 9 volt battery and an 18 kilo ohm resistor. Calculate firstly the maximum current, then calculate the time for the charging current to half, then calculate the time constant of the circuit, and then estimate the time for the capacitor to be fully charged. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question it's all about thinking what information you're given. So the maximum current is going to be equal to V over R. So therefore, what is V? Well, it's the maximum current, so therefore it's the maximum potential difference, which is going to be the EMF of the power source. You divide it by the resistance of the circuit. It's 9 over 18 times 10 to the 3, because kilo turns into ohms by that method. So you get 5 times 10 to the minus 4 amps. The next one, you've got to remember the equation. The time taken to halve is going to be 0.69 times times by RC. So therefore it's 0.69 times by the time constant, which is going to be R, which is 18 times 10 to the 3, times by 1000 times 10 to the minus 6. So therefore it's 12 seconds. Whilst the time constant itself is just RC, so you'll work it through to be 18 seconds. Now you've also got to remember the fact that we assume a capacitor to be fully charged or discharged after 5 time constants. So you multiply your time constant by 5, so it's 90 seconds. The next question says, a 1000 microfarad capacitor is charged by connecting it in series with a 4.5 volt battery and a 47 kilo ohm resistor. Calculate firstly the maximum PD across the capacitor, then calculate the charge on the capacitor 10 seconds after the circuit is completed, and then calculate the time for the charge stored to reach 63% of its maximum value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the maximum PD across the capacitor is going to be the EMF of the power source, which is 4.5 volts. Now, to work out the charge on the capacitor 10 seconds after it's been completed, we've got to use our charging equation. Q equals Q0 times by 1 minus e to the power minus t over RC. Popping all the values through. Remember, Q0 is CV0, so you know V0 is the EMF, 4.5 volts. You know C is the capacitance in farads, so you convert microfarads to farads. Pop in all the values, and we get 8.6 times 10 to the minus 4 coulombs. Now, this idea of to reach 63% of its maximum charge, that's the definition of a time constant. It's the time it takes to reach 63% of its maximum charge during charging, or to 37% of its starting value during discharge. So you just work out the time constant by doing RC, so you get 47 seconds. The next question says, state what is meant by a capacitance of 37 millifarads. Then a capacitor is made up of 2 parallel plates which are separated in air by a distance d. A cell of negligible internal resistance is connected across the capacitor as shown. Switch S is closed and the capacitor becomes fully charged. While S is still closed, the plate separation is reduced to d over 2. State and explain what happens to the magnitude of the charge stored by the capacitor. Then explain how the charge is conserved when the plate separation is reduced. Then S is now open. The plate separation is increased to D. State and explain how the energy stored in the capacitor changes during this process. Then explain how energy is conserved when the plate separation is increased as described in question 1.4. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to learn what the definition of capacitance is. It's how much charge is stored per unit volt. So this would be 37 millicoulombs stored per unit volt. In this next question, we know our equation to be C equals AE0 ER over D. So therefore capacitance doubles in voltage because of the fact that the separation has been reduced to D over 2. So therefore it's an inversely proportional, so capacitance will double. We know voltage stays the same in this question, so Q equals CV. So if C is doubling, Q is doubling. Now charge will be conserved because an equal number of electrons is removed from the positive plate as is added onto the negative plate, so therefore overall the capacitor is uncharged. Now in our next question here, okay, you know that the charge will stay the same because the capacitor is isolated, so the charge can't flow. So therefore, if the capacitance halves and we use our energy stored in the capacitor equation, the energy will therefore double. And then how will this energy be conserved? Because the gain in stored energy is provided by work being done into actually pulling the plates into a further separation away from each other. The next question says, show that the capacitance of an isolated conducting sphere of radius r is given by the formula C equals 4 pi epsilon 0 r. Then figure 24.22 shows 2 identical conducting brass spheres of radius 10 centimeters mounted on insulating stands. Sphere A has a charge of plus 5.0 times 10 to the minus 8 coulombs, and sphere B is uncharged. Calculate the potential at the surface of sphere A, then calculate the energy stored on sphere A. Sphere B is brought up to sphere A and is touched so that the charge is shared between the 2 spheres before being taken back to its original position. Calculate the energy stored in each sphere and then suggest why there is a change in the total energy of the system. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know the following. We know that V, okay, is going to be equal to Q over 4 pi epsilon 0 R, where V is our potential. That's an equation from the electrical fields module, which you can use because the sphere is going to produce a radial field. We then also know that Q is going to be equal to this 4 pi epsilon 0 times by V times by R. We know therefore C is Q over V, so what we can do is we can work it all through. The V's cancel through, so it's 4 pi epsilon 0 epsilon 0 times by R. To work out our potential, again, we're using that electrical potential for a radial field. V equals Q over 4 pi epsilon 0 R. So you can pop in all those values and you get 4,500 volts. Therefore, the energy stored is going to be the work done is equal to a half QV. Again, that's an equation from the electrical fields module. They're very closely linked. Pop in all the values and we get 1.1 times 10 to the minus 4 joules. In this next one, we know that the new charge on each sphere, because they're being touched, so therefore they will share that particular charge, it will equally, so it'll be 2.5 times 10 to the minus 8 coulombs. Our new potential is therefore going to be 2,250 volts because we're sharing the voltage originally, so therefore it halves. So therefore the new energy found on each of them is a half times by QV. We've got a new value of Q, we've got a new value of V, so we can work it through and we get 2.8 times 10 to the minus 5 joules. Our next question says, okay, why is there a change in the total energy of the system? Because energy will be lost or dissipated to the surroundings to heat the spheres, and that'll happen as the charge moves from one area to another area. The next question says, define the term capacitance of a capacitor. Then figure 24.23 shows a circuit which can be used to measure the capacitance of a capacitor. The reed switch vibrates backwards and forwards at a frequency of 50 Hz. Each time it makes contact with A, the capacitor is charged by the battery so that there's a PD of 12 volts across it. Each time it makes contact with B, it is fully discharged through the resistor. Calculate the charge that is stored on the capacitor when there's a PD of 12 volts across it. Then calculate the average current in the resistor, and then calculate the average power dissipated in the resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, learn the definition of capacitance. It's the charge stored per unit volt across the capacitor plate, or per unit potential difference. In this next one, we use our old capacitor equation. Q equals CV. You've got a value for V, 12. You've got the capacitance, worked it through. So therefore, you can say to be 67 times 10 to the minus 6, working it through. So it's 800 microcoulombs. We then say I equals Q over T. In the question for Q, we've just worked out what previous question, we've worked out what Q is. We know the value for time given before because the time for one oscillation is 1 over the frequency, so it's 1 over 50, so you get 0.04 amps. And then we can work out the power dissipated because P equals V over I, where V is the average potential difference. So you work it through, so it's going to be half of 12 because it's the average, so therefore it's 12 times by 0.04, so it's 0.24 watts. Our next question says a 0.10 farad capacitor is used in a circuit as a backup in case of a short interruption in the mains power supply. The PD supplied at the circuit is 230 volts. How much charge can the capacitor store? Explain why a capacitor would not be a good source for powering a portable media player. Then a 12 volt potential difference is applied to a capacitor. The capacitor stores 144 microcoulombs of charge in each plate. What is the capacitance of the capacitor? So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, once again, use that capacitor equation. Q equals CV, so it's 0.1 times by 230 is 23 coulombs. Then it wouldn't be a good source because you're going to have to think about the media player would have to be very large to have enough power so it wouldn't be able to be portable, or alternatively you could say you could only power the device for a short period of time, but you've also got to remember that the capacitor loses charge and therefore loses current it can apply to the circuit over time, so you wouldn't have a constant power output. Now in this next one, you can say capacitance is equal to charge over potential difference. We know what the charge is. It's 144 times 10 to the minus 6. We divide it by the potential difference of 12 to get 12 microfarads out. The next question says, for the airspace parallel plate capacitor shown, calculate the PD when it stores 25.5 microjoules of energy. Then explain why the capacitor stores energy when a PD is applied across to the plates. And then finally, a group of scientists claim that they've developed a new dielectric that enables the above capacitor to store 1 million times more charge and energy for a given PD. Explain what further steps must be taken by the scientific community and the industry before this new dielectric can be used in devices and sold to the public. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, again, you've got to be able to work through, okay, what your value is going to be, okay, and you can work it through here. Sorry, I'll put the wrong there, force acting per unit charge. So how you'd work it through is you would work out the value of Q by doing C. By working out the value of C by doing C is equal to AE0 ER over D. Now remember, convert the values given from centimeters into meters or millimeters into meters. So you can work out your area by doing 8 centimeters times by 8 centimeters, but into meters, and then you can work through your capacitance overall. You can then use that to then work out what the energy is by using your equation of E equals a half CV squared. So therefore, what you can do is rearrange, make V the subject, and then you can pop in the values to work it out. Now, explain why a capacitor stores energy when the PD is applied across its plates. Well, the PD leads to a charge imbalance between the plates, so therefore there'll be electrostatic energy or electrical potential energy between those two plates. And then how can you ensure that devices must be safe and sold to the public? So you're going to repeat the experiment, do it very reliably, repeat by other research groups, other people to make sure the results are reproducible, test for safety, test for the lifetime, look at the cost effectiveness, look at the environmental impact, and check for a big issue with capacitors, which is the idea of charge leakage, charge going between those two plates of the capacitor. The next question says, a physics student wishes to construct a capacitor that will store 31 nanocoulombs of charge when connected to an 8-volt power supply. He carries out some calculations and determines that placing 2 square aluminium plates of side length 21 centimeters at a distance of 0.10 millimeters from each other will be suitable. Determine whether this capacitor setup will store the required charge. Then state how the student could increase the charge stored without changing any of the dimensions of the capacitor or the power supply to it. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you're using the parallel plate capacitor equation. So you use that parallel plate capacitor equation, convert centimeters and millimeters into meters, and work the capacitance through. So it's 3.9 times 10 to the 9 farads. You can then say charge is equal to CV. You know what V is going to be because it's an 8-volt supply. So it's 31.2 nanocoulombs. You then write a statement concluding your findings, which is that it would store the required charge. Now in this next one, what would happen? How could you increase the charge without changing the dimensions? Well, place a dielectric between the two plates, as that will automatically increase any charge. The next question says, when a 470 microfarad capacitor is discharged through a fixed resistor R, the PD across it decreases by 80% in 45 seconds. Calculate the time constant of the capacitor resistor circuit. Then a 680 microfarad capacitor is charged fully from a 12-volt battery. At time t equals 0, the capacitor begins to discharge through a resistor. When t equals 25 seconds, the PD across the capacitor is 6 volts, so that the time constant of discharge is 36 seconds. Then a capacitor of capacitance 330 microfarads is charged to a potential difference of 9 volts. It is then discharged through a resistor of resistance 470 kiloohms. Calculate the potential difference across the capacitor 60 seconds after the discharge has begun. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using V equals V0 e to the minus t over RC, and then we're going to work out what R is. Now, the trick is that you can see that you can link in V0 in V by saying, well, V is equal to 0.2 V0 because it's lost 80% of its charge by that point of V, so therefore it's lost 80% of its voltage, so therefore it's 0.2 V0. It's 0.2, it's 20% of its voltage of what it was at the start. pop in all the values, rearrange, make RC the subject, use your maths to convert the exponential power there into a normal term by using a natural log, so we get 28 seconds out. In this next question, very similar again, we use V equals V0 e to the minus t over RC because it's a discharging circuit. We then say V, which is the voltage at the time, is 6. The maximum voltage is 12, so we can pop all those values in. We know t equals 25, pop in the values through, work out the maths, get rid of that exponential term, and then we get RC equals 36.1 seconds. And then in this next one, what I would do for this one is V equals V0 e to the minus t over RC again, because we've got our potential difference at the start, which we know to be 9. We can pop in all the values and work it through, converting kilo and micro into those actual values, and we get our answer to be 6.11 V. Now, the next question says, a 250 microfarad capacitor is fully charged from a 6-volt battery and then discharged through a 1 kilo ohm resistor. Calculate the time taken for the charge on the capacitor to fall to 37% of its original value. Then calculate the percentage of the total charge remaining on the capacitor after the 0.7 seconds. Then the charging voltage is increased to 12 volts. Explain the effect that this has on the total charge stored in the capacitor, the capacitance of the capacitor, and the time taken to fully charge the capacitor. Then a fully charged 320 microfarad capacitor is discharged through a 1.6 kilo ohm resistor. Calculate the time taken for its voltage to drop to half of its value when it was fully charged. So pause the video now, then unpause the video when you want to go through your answer. Hopefully in that first question you've realised that the time taken to fall to 37% of its starting value is a time constant when it's discharging, so T equals RC. Remember, micro turns into farads by times 10, working it through that way, okay, times 10 to the minus 6, okay, so and kilo goes into ohms by times it by 10 to the 3, so we get 0.25 seconds. This next question, we can say Q equals Q0 e to the minus t over RC. We're working out our percentage, so we're basically going to find Q over Q0. Our percentage work through. We know RC because we've just worked it through to be 0.25 seconds. We know T to be 0.7 seconds. Pop in all the values, work Q over Q0, so we get it to be 0.06, so therefore 6% of the initial charge left on here. Now you should be able to be aware that the total charge doubles because Q is directly proportional, so V is directly proportional to Q. The capacitance would not change because it's a fixed property of a capacitor. That's a very important principle. If you don't change the dimension of the capacitor, the capacitance stays fixed, and then the time taken to charge doesn't change, because what does that depend upon? It depends upon the time constant, which is RC. R hasn't changed, C hasn't changed, so therefore T cannot change either. Now the time taken to fall to half of the value, we've learned this before, is 0.69 RC, so you can work it through here, pop in all the values, and you get 0.35 seconds. The next question says, in recent years supercapacitors have been developed. These components charge and discharge in a similar manner to standard capacitors but have a capacitance of more than 10,000 farads. They can be used as backup supplies in many circumstances. A 120 farad supercapacitor has an internal resistance of 30 milliohms. At time t equals 0, it stores 30 joules. Calculate the minimum time taken for the capacitor to transfer 250 joules through discharging. Suggest why this is a minimum value. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you would do is you say PD across the capacitor when E equals 30 joules. Well, V is going to equal the square root of 2E over C, because we've just rearranged an equation of the energy stored in the capacitor. So rearrange that, I've made V the subject. So we can pop in all those numbers and we get out the value that for that energy is going to have 2.24 volts. So what about when it's at 50 joules? Well, we can work out V again with the same equation, but this time it's going to equal 0.91 volts. So therefore we can work out the time, okay, and therefore we can work that there through, so you can pop in all the values. So when you work it through, you know what V0 is, it's the maximum value, so it's going to be 2.24. We know what V is at that time, 0.91. We can then use the equation V equals V0 e to the minus t over RC. We're going to make T the subject. We know what RC is, okay, when we work it through, okay, so when we can work it out we get 3.2 seconds, and this is a minimum value because this is when it has the least amount of resistance, because we're not considering any external resistance, just that input resistance there. The next question says, This question is about charging a capacitor in a circuit with two resistors in series. Firstly, show that the time constant of a circuit is about 15 seconds. Then the graph in figure 2.3 shows how the PD across the capacitor varies with time up to 5 RCs. Add a line to the graph to show how the PD across the 4.7 kilo ohm resistor varies with time. Then add another line to show how the PD across the 2 kilo ohm resistor varies with time. And then calculate the time it takes from the start of the charging for the PD across the capacitor to reach 5 volts. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, time constant equals RC. We know R is going to be the sum of the two resistors in series. We times that therefore by C. C goes from microfarads to farads by times 10 to the minus 6. So RC equals 14.7 seconds. Now you'll see that what happens for the line for the resistor, well, it's going to be exponentially decreasing because it's in series with the capacitor, so it's going to invert what the capacitor does, because as the PD in the capacitor goes up, the PD in the resistor will go down, and it's the same idea for the 2 kilo ohm resistor as well. And then remember, they'll take their potential differences in proportion to their resistances, because that is Kirchhoff's laws, which will still be obeyed because this is a series circuit, so you can work it through like so. Then in terms of the time it takes for the charge to work through, well, we're going to have to use our equation that is going to be Q equals Q0 1 minus e to the minus t over RC. We then rearrange it and work it through, okay, and then you can actually, not use the Q version, not the V version of that to work it through. We know that it's going to be starting off at a value of 6, because that is the EMF supply. It goes to 5, so therefore V is equal to 5. We can rearrange it, make T the subject, work it through, and we get 27 seconds out. So let's now have a look at some questions for magnetic fields. So the first question says, explain why a current carrying wire experiences a force when placed close to a magnet. Then a current carrying conductor in a uniform field is shown. Use Fleming's left-hand rule to determine the direction of the force experienced by the conductor in each example. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it's the idea that the current carrying wire itself produces a magnetic field because it is moving, or it has charged particles moving in the same direction. Therefore, this magnetic field of the current carrying wire interacts with the magnetic field of the magnet and produces a force on the wire and on the magnet. Now you've got to use your left-hand rule with your thumb showing the direction of the motion or the direction of the force. The first finger showing the direction of the magnetic field from north to south, and the second finger showing the direction of the current as shown on the diagrams. So you orientate your finger in the first one and it goes into the board or into the screen. The second one, your thumb will be pointed upwards, the force is upwards, and then finally the force will be downwards because that's the direction your thumb will be pointing in. So in the next question, it shows 3 examples of current carrying conductors in magnetic fields. For each example, whether there will be a magnetic force on the conductor, and if there is a force, in which direction will it act in. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, there is no force. Why is that? Well, it's because the magnetic field and the current are parallel to each other, and when that's the case, no force is exerted on the current carrying wire. Now in the second one, because the current is perpendicular, there will be a force, and therefore you can use your Fleming's left-hand rule to work it out, and the force is into the plane of the paper or into the screen or into the board. And then the last one, once again you work it through, and the force is acting downwards on the page. The next question says, calculate the force per centimetre length on a straight wire placed perpendicular to a magnetic field of flux density 120 milliteslas carrying a current of 5 amps. Then a current carrying wire is placed perpendicularly to a uniform magnetic field and it experiences a force of 5 millinewtons. Determine the force on the wire when separately the current on the wire is quadrupled, the magnetic field density is doubled, and then the length of the wire in the field is reduced to 30% of its original length. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, we're using our equation F equals BIL, but because we're working out the force per centimetre, we've then got to set that length L to be a centimetre, which is 0.01 metres. So you pop in all the values, milliteslas turns into teslas, 10 to the by times 10 to the minus 3, so you work it out to be 6.0 times 10 to the minus 3 newtons. In this next one, we know F equals BIL, so if I is quadrupled, F will be quadrupled, so it goes from 5 millinewtons to 20 millinewtons. Again, in this next one, F equals BIL, B is doubled, so F will double, so therefore it equals 10 millinewtons, and again, L is proportional to F, so therefore F decreases by a factor by 30% of its initial value, so therefore it's 1.5 millinewtons. The next question says, a conductor of length 0.20 meters lies at an angle of 25 degrees to a magnetic field of flux density 0.050 teslas. Calculate the force on the conductor when it carries a current of 400 milliamps. Then secondly, underneath you'll see a picture. What force will be exerted on each of the currents shown below, and in what direction will each of the forces act in? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've now got to include the angle in our F equals BIL equation. So F equals BIL sine theta, pop in all the values, milliamps turns into amps by times 10 to the minus 3, so it's 1.7 times 10 to the minus 3 newtons. And then we know for the first one that F equals BIL sine theta, so therefore we can work it through, pop in all the values, we know it's going to be equal to 0.38 newtons. Okay, in the second one, we know F equals BIL sine theta, again sine 45 from looking at the particular values, so it's 0.27 newtons. But C, because the current is parallel to the magnetic field, sine 0 equals 0, so therefore F equals 0, so there's your answer. Now for A and B, because they've both got a force, we can work out the direction, use the left hand rule to work it through. They're both in the direction of the plane of the screen, so they're going inwards. The next question says, find the force acting on each of these particular particles. A helium nucleus travelling at 15,000 kilometers per second when the field strength is 2.2 milliteslas. An electron in a magnetic field strength 1.3 teslas travels at 320,000 meters per second. Then a sulfate ion SO2 minus travels at 75 meters per second in a field strength of 0.14 teslas. So pause the video now, then unpause the video when you want to go through your answers. Right, for this one, what's the force on a charged particle? F equals BQV. Popping all the values working through. Helium nucleus has a charge of 2 plus because it's 2 protons in there, so you can work it through to be 2 times 1.6 times 10 to the minus 19 for its charge. Popping all the other values, kilometers per second turn into meters per second by times of 10 to the 3. Milliteslas turn into teslas by times by 10 to the minus 3, so we get 1.056 times 10 to the minus 14 newtons. Same equation next time, bit easier in terms of the charge, it's just 1.6 times 10 to the minus 19. Popping all the values through, 6.56 times 10 to the minus 14 newtons. This one, remember the charge is 2 minus, so it's 2 times by 1.6 times 10 to the minus 19. Popping all the values, 3.36 times 10 to the minus 18 newtons. The next one says, each of these cases describes circular motion due to the effect of a magnetic field on a moving charged particle. The track of an electron has a radius of 2.5 micrometers in a field of 3.3 teslas. How fast is it moving? Then a particle is moving at 1.57 times 10 to the 6 meters per second in a magnetic field of 0.39 teslas. The radius of motion is 42 millimeters. Find the charge to mass ratio. Then an electron is traveling in 0.1 C in an experimental solenoid with a magnetic flux of density of 24 teslas. What will the radius of rotation be? So pause the video now, then unpause the video when you want to go through your answers. Right, in terms of a moving charged particle, you've got to remember that for a moving charged particle, R is equal to mv over bq. That equation is not given to you in your exam. It's the idea that the centripetal force, mv squared over R, is equal to the magnetic force, bqv, so you can work it through to work out R. So you can pop in all the values, rearrange, make V the subject, micro turns into just a meters by times and 10 to the minus 6. Pop in all the values, you know the charge of an electron, 1.6 times 10 to the minus 19. You know the mass of an electron given to you on the equation sheet, 9.11 times 10 to the minus 31 kilograms. So you get out 1.54 times 10 to the 6 meters per second. Once again, here you need to find the charge to mass ratio. So when you have R equals mv over bq, you want q over m. That's charge to mass. So you can work it all through, and we get 9.58 times 10 to the 7 coulombs per kilogram. Now this next one, again working out R, so R equals mb over bq. We know the mass of an electron, like we said before. Remember it's at 0.1 c, so that's 0.1 times by 3 times 10 to the 8. We know the charge of an electron, 1.6 times 10 to the minus 19, so it's 7.12 times 10 to the minus 6 meters. The next question says, if a bar magnet causes a magnetic field with a flux density of 20 milliteslas perpendicular to the plane of area A, how much flux will be contained by this area if it's 10 centimeters squared? Then a uniform magnetic field has a flux density of 5 times 10 to the minus 5 teslas and is at an angle of 75 degrees to the region of area A. How much flux will be contained by this area if it is 1 centimeter squared? Then Zora takes a wire and winds it into a coil of 10 circular turns with a radius of 5 centimeters and then holds this in a magnetic field with a strength of 20 milliteslas. What is its flux linkage? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's our equation for flux? Flux is equal to BA. It's the magnetic flux density times by the area. So it's 20 milliteslas into teslas times 10 to the minus 3. Work out your area now, centimeters squared into meters squared is times 10 to the minus 4, because there's 2 times 10 to the minus 2 because it's centimeters squared. So we get 2.0 times 10 to the minus 5 Webers. This next one now, because we've got an angle, it's actually flux is equal to BA cos theta. Pop in all the values, convert centimeters squared into meters squared again, and we get 1.29 times 10 to the minus 9 Webers. And then this last one, now we've got to consider what the flux linkage is. So flux linkage is going to be equal to n phi or n flux, so therefore it's nba cos theta. So you pop in all the values. Now remember, area in this instance is going to be pi r squared, so it's going to be 5 times 10 to the minus 2 because you go from centimeters into meters. So you can pi times by 5 times 10 to the minus 2 squared. We know in this instance cos theta equals 0, so it's going to equal 1. Pop in all the values and we get 1.6 times 10 to the minus 3 Weber turns. The next question says, in Britain the magnetic flux density is 50,000 nanoteslas with the field approximately at the horizontal. Firstly, estimate the flux passing through your body if you are standing vertically and facing north. Then a typical smartphone compass uses a small magnetometer chip to determine which way the phone is facing. Such chips are typically 2mm by 2mm squares. If you held a smartphone so that the magnetometer chip was at an angle of 20 degrees to the horizontal, what would the flux passing through the chip in the phone be? Then in an electrical motor, a permanent magnet of flux density 18.4 milliteslas has its field placed perpendicular to a coil of 250 turns of copper wire. The diameter of the coil is 8.50 centimeters. What is the flux linkage between the field and the coil? So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So the first one, you're going to have to estimate the area of a human's body. So if let's say roughly that a human is 2 meters tall and 0.5 meters wide, so roughly we're looking at 1 meter squared. So therefore we say theta equals BA, pop in all the values, nano turns it into teslas by times and 10 to the minus 9, so it's 5 times 10 to the minus 5 times 10 to the minus 5 Webers. Now this next one, we know that the flux is equal to BA cos theta. We pop in all the values. Now again, remember it is a square, but it's in millimeters, so it's 2 times 10 to the minus 3 times by 2 times 10 to the minus 3. Pop in our angle there 20 degrees, so we get 6.8 times 10 to the minus 11 Webers. Again, same equation now for flux linkage, except it's n phi, so therefore it's nba cos theta. So we pop in now 250 turns, we work out area because it's pi r squared, so you give the diameter, half to get the radius, turn that into meters, then you work it through, so we get 0.0261 Weber turns. The next question says, a straight wire of length 0.20 meters moves at a steady speed of 3.0 meters per second at right angles to a magnetic field of flux density 0.10 teslas. Use Faraday's law to determine the EMF induced across the ends of a wire. Then a search coil of wire having 2,500 turns and an area of 1.2 centimeters squared is placed between the poles of a magnet so that the magnetic flux passes perpendicularly through the coil. The flux density of the field is 0.50 teslas. The coil is pulled rapidly out of the field in a time of 0.10 seconds. What is the average EMF is induced across the ends of the coil? So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work it through? So Faraday's law states that the EMF induced is equal to the rate of change of flux linkage. So the first thing to do is work out the change in flux. So what you can say is B times by the change in area. So you work that through, so you get it to be 6 times 10 to the minus 2 Webers. So therefore EMF is going to be the change in flux linkage. So that's going to be 6 times 10 to the minus 2 divided by the time, which in this instant, if you're working at 3 meters per second, and you've worked out that the area is 3 meters times by 0.2 meters, therefore we say the time is 1 second. So you pop that through to be 0.06 volts. Now this next one again, flux linkage is equal to nth I, so it's BAN. So you work out the magnetic flux linkage by doing 0.5 times by 1.2 times 10 to the minus 4 centimeters squared into meters squared times by 2,500. That gets you 0.15 Webers. Now you'll notice when you're out the field, the flux linkage will be 0 Webers. So therefore the change in flux linkage will be 0.15 Weber turns, because it's 0.15 minus 0. You then divide it by the time, 0.10, so it's 1.5 volts. The next question says, determine the peak voltage if the RMS voltage is 10 volts, 40 millivolts, 25 microvolts. Then determine the RMS voltage if the peak voltage is 45 volts, 7 millivolts, and 100 microvolts. So pause the video now, then unpause the video when you want to go through your answer. Right, this is just using our equation that the peak voltage is equal to the root mean square voltage times by square root 2. That's an equation given to you on your exam. So it's 10 times by square root 2, 14.1 volts. Next one, it's going to be 56.6 times 10 to the minus 3 volts. And then finally, it's going to be equal to 35.4 times 10 to the minus 6 volts. We rearrange it for the RMS voltage. So VRMS equals V0, the peak voltage, over square root 2. So it's 45 over square root 2, 31.8 volts. This next one, millivolts turns into volts by times 10 to the minus 3. So it's 4.9 times 10 to the minus 3 volts. And then here, it's going to be 70.7 times 10 to the minus 6 volts. This next question says, for each of the images determine the peak voltage, the RMS voltage, and the frequency of the signal. So pause the video now, then unpause the video when you want to look through your answers. Right, so in this question, how do you work it through? So in the first one, how can you work out what the peak voltage is? Well, you look on the screen, you see that you're given the Y gain and it's set to be 5 volts. So therefore there's three squares between the equilibrium and the peak. So therefore 3 squares, each of 5 volts, it's 15 volts. Now in terms of the RMS, we know that VRMS is that V0, the peak voltage, over square root 2, so it's 10.6 volts. And therefore in this next one, we know that frequency is 1 over time period. Now you'll see that the time base is equal to 2 milliseconds for each square. Now you'll see that one entire wave is equal to 4 squares, each of 2 milliseconds. So the entire period of the wave is 8 milliseconds. So the frequency is 1 over 8 milliseconds. It's 125 hertz. So we do these next 3 examples are all the same principle. 4.5 squares, okay, each of 0.5 volts. So the peak is 2.25 volts. VRMS is going to be 1.59 volts. So therefore the time period is 8 squares, each of 1 milliseconds. The time period is 8 milliseconds. Frequency is 1 over 8 times 10 to the minus 3, 125 hertz. C is going to be equal to a peak of 0.5 volts, a VRMS of 0.32 volts, and then a time period of 25 hertz. And then this last one, they're 4 squares, each of 0.2 volts, so the peak is 0.80 volts. The VRMS is 0.57 volts. And then finally, you can work out that the time period in total is 200 milliseconds. So therefore, the frequency is 1 over 200 times 10 to the minus 3. It's 10 hertz. The next question says, a step-down transformer changes 230 volts mains voltage to 5 volts. The transformer has 920 turns on its primary coil. Calculate the number of turns on its secondary coil. Then an old mobile phone charger has an inbuilt transformer that produces an output voltage of 5.2 volts. The input voltage is 230 volts and the primary coil has 500 turns. Calculate the number of turns on the secondary coil. Then an electronic device uses a transformer with a turns ratio of 20:1 to step down the mains voltage from 230 volts. Calculate the output voltage from the transformer. Then a transformer is used to step down the 230 volts mains voltage to 12 volts. A 60-watt lamp connected to a secondary coil is lit normally. The primary coil has 1000 turns. Calculate firstly the number of turns on the secondary coil, and then secondly the number of the current in the primary coil. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using our transformer equation, which is Ns over Mp equals Vs over Vp. N is directly proportional to V in a transformer. Pop in all the values so you get out 20 turns. This next one again, we're using Ns equals Mp times by Vs over Vp. Again, the transformer equation, the equation given to you in your exam, we get 11 turns. That feels right because the secondary voltage is lower, so therefore the number of turns should be lower as well. This next one, again, we can see that it's a ratio there of 20 to 1, so therefore you can work it all through and you get your value out to be 12 volts. This next one again, we are working it through again and we're popping all the values, work it through and we get 52 turns. Again, that feels right because the number of turns on the secondary is much lower, than the primary, but also the voltage is much lower. It's gone from 230 to 12, so therefore the number of turns will also decrease by a great amount as well. And then finally, what's the current going to be? Well, it's going to be current is equal to power over potential difference. It still works because it is the same. It's the same principles of electricity. So you get out 0.26 amps. The next question says an iron core has a square cross section with each side being 4 centimeters. The primary produces a magnetic field with a strength of 0.5 teslas. This takes 60 milliseconds to generate and die away when the primary circuit is switched on or off. The secondary coil has 120 turns when the EMF will be induced in the secondary at the moment of switch on or switch off of the primary circuit. So there should be what EMF should be induced. Then secondly, a local substation of the national grid changes the voltage down from 11 kilovolts to 415 volts. If the primary coil in this transformer has 8,000 turns, how many will be needed on the secondary coil to give the correct output voltage? So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how do you work out EMF? EMF is the change in flux linkage divided by the change in time. Flux linkage is going to be BAN, so you can work out what A is going to be because it's a coil, so therefore, it's a square cross section, my apologies, so it's 4 centimeters, which is 0.04 meters, times by itself, so it's 0.04 squared. Okay, we know the number of turns, 120, we know what B is, it's going to be 0.5, we then divide it by the time, which is 60 milliseconds, so it's 60 times 10 to the minus 3, so therefore it's equal to 1.6 volts. This next question here, we say Ns equals Mp times by Vs over Vp. It's that transformer equation again. We work it through. Remember, kilovolts turns into volts by doing times by 1,000 or 10 to the 3. So we get our 302 turns. That feels right because we've gone down by volts a lot, so we're going to go down by turns a lot as well. The next question says, explain why a stationary charged particle in a magnetic field does not experience a force. Then calculate the maximum magnetic force experienced by an electron travelling at a speed of 6 times 10 to the 5 meters per second in a uniform field of flux density 0.20 teslas. Then a particle of charge plus 2e describes a circle of radius 2.5 centimeters in a uniform magnetic field of flux density 300 milliteslas. Calculate its momentum. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to have the understanding that the force given on a moving charged particle is F equals BQV. So V is 0, F is 0. Again, we're using F equals BQV, pop in all the values, work it through, we get 1.92 times 10 to the minus 14 newtons. Look at the equation sheet for that equation. Now, because it's going in circular motion, we can say, remember, R equals mv over bq, because the centripetal force is the magnetic force. Pop it out. Now we know mv is momentum, because momentum equals mass times velocity, so therefore it equals BQR. Pop in all the values. Remember, centimeters turn into meters, milliteslas turn into teslas by times 10 to the minus 3, and remember it's a charge of 2e, so it's 2 times 1.6 times 10 to the minus 19. So we get 1.04 times 10 to the minus 21 kilogram meters per second. The next question says, electrons ejected from an electron gun at a speed of 1.4 times 10 to the 7 meters per second enter a magnetic field of flux density 2.4 milliteslas acting 90 degrees to the beam. Determine the radius of curvature of the path followed by the electron beam, given that the specific charge of an electron is 1.76 times 10 to the 11 coulombs per kilogram. Then calculate the speed of an antiproton created in a high energy collision if the radius of the curvature of the track is 0.11 meters and the detector's magnetic field strength width is 3.0 teslas, then a charged particle moving at right angles to a constant magnetic field follows a circular path, so that the radius of curvature of the particle's path is directly proportional to its momentum, and then particles of mass m and charge q travel in a circular path of radius r and speed v in a magnetic flux density b. How many of these quantities m, q, v, r and b, if increased one at a time, would increase the radius of the path? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, remember, circular path, r equals mv over bq, so therefore we can work out what these values are going to be. Now remember, specific charge, specific means per mass, per kilogram. So specific charge is charge per mass. So we can rewrite it out as is r equals v over b times by q over m, or the specific charge. Pop in all the numbers, work it through. Remember, milliteslas turn into teslas, so you get 0.033 meters. This next one again, you go v equals bqr over m. Now remember, the magnitude of an antiproton's charge is the same as a proton, so it's 1.6 times 10 to the minus 19. We work it through and it's 3.2 times 10 to the 7 meters per second. How do we show it's directly proportional? Like we said, we say that the centripetal force is equal to mv squared over r, but the centripetal force in this context is the magnetic force, which is equal to bqv. So therefore, mv squared over r equals bqv. Rearrange that to be r equals mv over bq. For a particle that's moving, q and b are going to be constants, so therefore r is directly proportional to mv, the momentum. Now, like we said, r equals mv over bq, so if you increase m or you increase v, you would increase r, but increasing b or increasing q would decrease r because of where it is on the equation. The next question says, calculate the magnetic flux passing through a small circular coil of diameter 1.5 centimeters positioned between the poles of two slab magnets, given that the magnetic flux density between the magnetic poles is 300 milliteslas. Then calculate the magnetic flux passing through a circular coil of diameter 2.0 centimeters if the magnetic flux density is 150 milliteslas and the angle between the normal to the plane of the coil and the direction of the magnetic field is 40 degrees. Then calculate the magnetic flux linkage through a 20-turn circular coil, given that the magnetic flux density is 150 milliteslas, the angle between the normal to the plane of the coil and the direction of the magnetic field is 16 degrees, and the radius of the coil is 5.0 millimeters. Then determine the magnetic flux and the magnetic flux linkage through a rectangular coil of dimensions 5.0 centimeters times by 3.0 centimeters, given that the coil has 100 turns, the magnetic flux density is 120 milliteslas, and the angle between the coil and the magnetic field direction is 30 degrees. So pause the video now, then unpause the video when you want to go through your answers. Right, in this one, remember how to work out magnetic flux. Flux is equal to B times by A. So you work out your area, you convert your 1.5 centimeters into meters by times 10 to the minus 2, and you half it because you want the radius. So you do B, so milliteslas into teslas, times by your pi r squared to work out your area. You get 5.3 times 10 to the minus 5 vebers. Now again, we've got an angle, so it's BA cos theta now. So therefore it's 150 times by 10 to the minus 3 times by cos 40 times by pi r squared. Remember, we're given the diameter, turn it into meters, half it, so you can work it through to be 3.6 times 10 to the minus 5 vebers. This next one again, we're now working out the magnetic flux linkage, so therefore it's n phi or BAN cos theta. So we're now going to times it by the number of turns that we've got. So we do 20 times by 150 times 10 to the minus 3 because it's milliteslas into teslas, times by cos 16 times by pi r squared again, so millimeters into meters, so it's 5 times 10 to the minus 3, so it's 2.3 times 10 to the minus 4 vapor turns. And here again, flux is equal to BA cos theta, work it all through and you get 1.6 times 10 to the minus 4 vapors. Flux linkage is n times that value, so you times that then by 100, so it's 1.6 times 10 to the minus 2 vapor turns. Remember, the difference in use between flux and flux linkage is vebers and then vapor turns. So even though the SI unit of both of them is the same, we use the differential there to differentiate between the two values. The next question says, a rectangular coil rotates at a constant angular velocity within a uniform magnetic field of 0.121 teslas. The coil has 70 turns and a cross-sectional area of 49 centimeters squared. The diagram below shows the coil looking along the axis of rotation. Calculate the flux linkage of the coil when the angle is 23 degrees. Then as the coil rotates, explain what values of theta provide the maximum and minimum values of induced EMF. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's flux linkage? BAN cos theta. Pop in all the values through. Now remember, you got 70 turns, so that's going to help you with that one. Okay, now that's going to help you when you work it through. Now remember, cross-sectional area, we go in centimeters squared to meters squared, so it's times 10 to the minus 4. You work that all through, and we get 0.046 Weber turns. Now you're going to get a maximum induced EMF at theta equals 90 degrees when you work it through, because even though the flux linkage is the lowest value, the rate of change of the flux linkage, which is what causes induced EMF, is at its largest, and when theta equals 0, there'll be no EMF, because even though the flux value is a maximum, the rate of change in flux is actually the 0 value. So therefore, because it's instantaneously stopped at that point, if you think about it, okay, so therefore you're going to get no EMF. The next question says, a student thinks that electrical current passes through the core in a transformer to the secondary coil. Describe how you might demonstrate that this is not true and explain how electrical current is actually induced in the secondary coil. Use Faraday's law in your explanation. Then a square coil of 100 turns of wire has sides of length 5.0 centimeters. It is placed in a magnetic field of flux density 20 milliteslas so that the flux is perpendicular to the plane of the coil. Calculate the magnetic flux through the coil, and the coil is now pulled from the magnetic field in a time of 0.10 seconds. Calculate the average EMF induced in it. Then an aircraft of wingspan 40 meters flies horizontally at a speed of 300 meters per second in an area where the vertical component of the Earth's magnetic field is 5.0 times 10 to the minus 5 teslas. Calculate the EMF generated between the aircraft's wingtips. So pause the video now, then unpause the video when you want to go through your answer. Now, the most obvious demonstration is to show that the secondary coil is made from insulated wire, so is the primary coil, so therefore no current can flow from the core to the secondary coil from the primary coil because it can't flow through an insulator. Now, an electrical current is induced in the secondary coil of a transformer because there's a change in magnetic flux linkage in that secondary coil, and when you've got a change in magnetic flux linkage, that will induce an EMF. When that's part of a complete circuit, that will produce a current. Now this next question, flux is going to equal BA. Pop in your values. Remember, we turn centimeters into meters. We go milliteslas into teslas. So we get 5.0 times 10 to the minus 5 Webers. EMF is equal to the change in flux linkage divided by the time. Now again, when it's out the field, the flux linkage is 0. So it's 5 times 10 to the minus 5 minus 0 when it works through. 100 because you're converting the flux into flux linkage. So you multiply that by the number of turns, but then it's minus and 0. So therefore, it's going to be equal to the value then you divide it by 0.1. It's 5.0 times 10 to the minus 2 volts. Now this last one, another trick you can use, because another equation which isn't given on your exam sheet, but you can learn it to work out your average induced EMF, is BLV, where V is the velocity. So you can pop in all the values, work it through, and you get 0.60 volts. The next question says, a single phase AC power supply has an RMS voltage of 230 volts. Calculate the peak value of the power supply, and then calculate the average value for the power supply. So pause the video now, and then unpause the video when you want to go through your answer. So, how to answer this particular question? Well, remember, the equation is that V peak is equal to V RMS times by square root 2. So if you work that through, you can see that values out to be 325.27 volts. Now the average value is therefore going to be V average is going to be 2 times by V peak over pi, working it through, thinking about it as if it was a complete circle, working it through, so you get 207.1 volts. Okay, now this next question says, a conductor with a length of 250 millimeters is moving at a right angle through a magnetic field of flux 2.2 teslas. The conductor is moving at a velocity of 8 meters per second. Calculate the induced EMF. So pause the video now, then unpause the video when you want to go through your answer. Right, like we said before, there's a bit of a shortcut equation when you're given the velocity and you want to work out the average induced EMF. So EMF is equal to BLV. Now we know L is given in millimeters, so it needs to be into meters, so it's 0.25 meters. Pop in all the values and you get 4.4 volts. The next question says, what is the value of current I when time equals 5 milliseconds, and in which direction is it flowing? Then at what time does the current next have a value but negative? What is the time for one complete circuit? And then what is the frequency of the alternating current, given the information below? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, for alternating current, we know that at 5 milliseconds you look on the graph and the value is going to be equal to 2 amps, and it's a positive value, so it's moving in a positive direction. At what time we'll have the next value but negative, so look for -2 on the graph, so therefore it'll be at 15 milliseconds, so I'm looking at this information. Now if you look on here, the time for one complete cycle is one whole wave, so therefore you're going to be equal to 20 milliseconds is the information given on the graph. So the frequency is going to be, frequency is 1 over time period, so it's 1 over 20 milliseconds, which is 20 times 10 to the minus 3, so it equals 50 hertz. The next question says, what is the average power dissipated when a sinusoidal alternating current with a peak value of 3 amps flows through a 100 ohm resistor? Then a sinusoidal voltage of peak value of 325 volts is connected across a 1 kilo ohm resistor. What is the RMS value of this voltage? Use V equals IR to calculate the RMS current which flows through the resistor. Then what is the average power dissipated in the resistor? And then what is the peak power dissipated in the resistor? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we can use our equation that P equals I squared R, but because we're using alternating current, we need to use RMS values, average values, okay, which is RMS values. So therefore we say P IRMS squared times by R. We can work out what the RMS value is by doing the peak divided by square root 2. So therefore you would do 3 divided by square root 2. You would then square it to then get your value. You then multiply that by the resistance, which is 100 ohms, to get 450 watts. Here we know VRMS is the peak voltage over square root 2, so it's 230 volts. We can then work out IRMS, because we can say, well, if V equals IR, I equals V over R, but again remember resistance is a scalar, so it doesn't need to be considered with an RMS, but V has to be, because it will need an RMS consideration, so therefore use VRMS, not V peak, so it's 230 over 1000 is 0.23 amps. Then the average power dissipated, well, you'll do P equals I squared R, but the average when you've got an alternating supply is RMS, so it's IRMS you're going to be using, so you get it through to be 53 watts. When you want to work out the peak dissipation, you'll use the peak current, the peak potential difference I should say, or the peak voltage, so therefore it's going to be equal to 325 squared over R over 1000, which is 110 watts. The next question says, figure 4 shows the trace of an oscilloscope connected across a 20 ohm resistor. The oscilloscope grid is marked in centimeters and the time base is set to 0.2 milliseconds per centimeter. The Y amplifier sensitivity is set to 0.5 volts per centimeter. When the oscilloscope was first connected, the whole wave could not be seen on the screen. Describe how you adjust an oscilloscope to achieve a screen that's easy to take readings from. Then determine the frequency in hertz of the signal. Then determine the RMS voltage in V, and then calculate the mean power in watts transferred into the 20 ohm resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how would you get easy readings from it? Well, the first thing is adjust the time base, so you've got a complete wave seen on the screen. You then move the wave either left or right, so then you can have the start of the cycle on a grid line, because it's very important. You always have key marking points on key graduations or key lines on your screen. You then adjust the Y amplification, so you've got the peak to peak as at a maximum, and then move the wave up and down, so once again the peak is on the line, so then it's easy to read. Now the frequency is 1 over the time period. You'll see the time period on the screen was equal to 6 centimeters, which was 0.2 times 10, times each one by 0.2 times 10 to the minus 3, because that was the scalar factor. So that therefore is equal to 1.2 times 10 to the minus 3 seconds. So therefore F is 1 over that value, so it's 830 hertz. Again, you can work out the peak to peak. So the peak to peak is 6 squares, so therefore the peak voltage is 3 squares. It's better to do the peak to peak because you'll have a low percentage uncertainty than half it. Therefore you work out the voltage is 1.5 volts, but using your scaling factor. VRMS is V0 over square root 2, so therefore it's 1.1 volts. Then the mean power transferred, well, P equals V squared over R. Now it's VRMS because we want an average value, so or mean value, so therefore VRMS is 1.1 volts, so you work it through to be 0.056 watts. The next question says, consider the following jumping ring experiment. What would happen to the aluminium ring if the primary coil current was increased? Then, a student suggested that the ring is placed in liquid nitrogen before being slotted over the iron core. Suggest what effect this would have when the AC power supply is switched on. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, you can see that if the primary coil current was increased, well then the induced current in the ring will be greater, because you'll see that there'll be a greater flux linkage from the primary coil, so therefore there'll be a greater change in flux linkage in the secondary coil because it's alternating plus or minus plus or minus. So therefore the magnetic force on the ring would therefore be greater, so be pushed higher, so therefore the ring will be pushed to a greater height before it reaches an equilibrium with the forces acting down, so therefore it starts to, quote, float. Okay, now what would happen if you put the liquid nitrogen in? Well, if you put the liquid nitrogen in, well then the resistance in the ring itself will be reduced because it's a lot lower, colder temperature, so therefore a much larger induced current will flow in the ring, so therefore the magnetic force pushing the ring upwards will be even greater, so therefore it might even go up and hit the ceiling because you've got such an upwards magnetic force, because the resistance will be so low in that particular aluminium ring. The next question says, a power station is connected to towns by a cable of total resistance 10 ohms delivering 50 megawatts. Calculate the power losses in the cable if the power supplied to the town is directly from the generator of 25 kilovolts or after being stepped up to 400 kilovolts. Then a power cable of total resistance 20 ohms is used to deliver 2.0 megawatts at 33 kilovolts to a heavy industrial plant. Determine the power wasted in the cable. Then, a portable diesel power generator is capable of producing 4 kilowatts of electrical power at a voltage of 240 volts for use on a remote farm that is not connected to the national grid. If cables of total resistance 1.2 ohms deliver the electricity to the farmhouse, determine the power loss as heat in the cables when the generator is running at 4 kilowatts, and then the minimum size of the voltage available in the farmhouse. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the equation I equals P over V. So we can work out what I is going to be, because it's going to be 50 times 10 to the 6 megawatts into watts, divided by 25 times 10 to the 3 kilovolts into volts. So we get 2000 amps. We then say P equals I squared R. That's the equation to work out the power dissipated in electrical cables. You're given that on your equation sheet. So it's 2000 squared times by 10 is 40 megawatts. You can do the same equation when it's been stepped up to 400 kilovolts, and you get 0.16 megawatts, which actually proves you mathematically why we step up the voltage in the step-up transformer. Again, we can use the same equation again here in question 2. We say I equals P over V, work out I to be 60.6 amps. We therefore say power lost is equal to I squared R, pop in all those values, and we get 7.3 times 10 to the 4 watts. Next question, again, we're using that same principle. I equals P over V. 4,000 divided by 240, remember 4 kilowatts turns into watts, so 16.7 amps. We then say P equals I squared R, pop in all the values, and we get 335 watts. So what's the minimum voltage available? Well, at this point, the voltage drop across the cables at full power is 20 volts, because we know V equals IR. We know I from the question is going to be equal to the previous question is 16.7 amps. Times it by the value you can work it through for R, which you know is 1.2 ohms from the information given in the question. So therefore, the voltage available at the farmhouse must be 220 volts, because it starts at 240. We lose 20 volts of lost volts in the wire, so therefore we're left with 220 volts left behind. The next question says, state 2 situations in which a charged particle will experience no magnetic force when placed in the magnetic field. Then a charged particle moves in a circular path when travelling perpendicular to a uniform magnetic field. By considering the forces acting on the charged particle, show that the radius of the path is proportional to the momentum of the particle. Then a cyclotron is a circular particle accelerator. In a particular cyclotron, the flux density of the uniform magnetic field is 0.48 teslas. Calculate the speed of a proton when the radius of its path inside the D is 190 millimeters. Then calculate the time taken for this proton to travel at a constant speed in a semicircular path of radius 190 millimeters inside the cyclotron. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to just learn when a charged particle experiences no magnetic force inside a magnetic field. A, when it's moving parallel to the magnetic field, and B, when it's not moving relative to the magnetic field. The next one, we've done this before. We've said that the centripetal force equals the magnetic force, so BQV equals mv squared over r. We can rearrange it. We can make r the subject. R equals mv over bq. B and q are constant, so r is proportional to mv. We can then rearrange this equation and say V equals BQR over M. Pop in all the numbers. Now remember, 90 millimeters turns into meters. We pop that through. Remember, we know the mass of a proton is given to you on the equation sheet, 1.67 times 10 to the minus 27. We know the charge of a proton is 1.60 times 10 to the minus 19, given to you on the equation sheet. So the values give you 8.7 times 10 to the 6 meters per second. Now, just be very careful in this next question, because it's asking for the length of a semicircle. So the length of a semicircle, okay, not the area, but the length is half of the circumference. So it's pi r. So therefore, the time taken is the length which you travel, which is the circumference of a semicircle, which is pi r, over the velocity. Pop in all the values, we get 6.8 times 10 to the minus 8 seconds. The next question says, a circular coil of diameter 140 millimeters has 850 turns. It is placed at its plane is perpendicular to a horizontal magnetic field of uniform flux density 45 milliteslas, as shown in figure 1. Calculate the magnetic flux passing through the coil when it's in this position. Then the coil is rotated through 90 degrees about the vertical axis in a time of 120 milliseconds. Calculate the change in magnetic flux linkage produced by this rotation, and then the average EMF induced in the coil when it's rotated. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say that phi equals magnetic flux is BA. So you work it through. Remember, it's a circle, so you're going to do pi r squared, where r is half the diameter, given the diameter in millimeters, converted to meters, and half it to get the radius. Pop those all through, so we get 6.9 times 10 to the minus 4 Webers. Then this next one, the change in magnetic flux linkage. Well, we know that if it's rotated 90 degrees, it'll go to 0, but what does it start at? Well, we know that it starts at MBA, so therefore we know it's the value we just worked out, which was going to be BA, multiplied by N, which was 850, so it's 0.59 minus 0 is still 0.59 Weber turns. Now the average induced EMF is this value divided by the time, so therefore you divide this value by 0.12, so it's 4.9 volts. The next question says, a simple loudspeaker consists of a cone, a coil of wire and a magnet. The cone and the coil are attached to each other and are free to move. An alternating current in the coil causes the cone to oscillate. The loudspeaker is mounted in a wooden box. A cross-section through the loudspeaker is shown. The student made the following observations. When alternating PD is applied to the cone oscillates. The frequency of the oscillation is the same as the frequency of the PD, and at particular frequencies the box vibrates with a large amplitude. Explain these observations. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first question, you should be aware that you know that an alternating potential difference will cause an alternating current in the coil. Now, because it's a current carrying conductor and it's inside a magnetic field, those two fields will interact and therefore it will experience a force. So the current is alternating, so the force will change direction as the current changes direction. So therefore, this will cause the cone or the box to go into an oscillation, so therefore the frequency of the oscillation will then equal the natural frequency of the oscillation of air in the box. Now therefore that gives you a maximum energy transferred and the amplitude of the vibration increases. That's resonance. Now what this question is doing to you is actually recalling you understand from periodic motion. It can do that because in paper 2 they can ask on any concept from paper 1. The next question says, the diagram shows below an AC waveform that is displayed on an oscilloscope screen. The time base of the oscilloscope is set at 1.5 milliseconds per division and the Y gain at 1.5 volts per division. Firstly, calculate the frequency. Secondly, calculate the peak voltage. Third, calculate the RMS voltage, and then state and explain the effect on the oscilloscope trace if the time base is switched off. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, the trick is you're going to have to use all of the wave because that will lower your percentage uncertainty. So to work out the frequency, well, you know the time period for 1.5 waves because that's the entire thing on the screen. So for 1.5 waves, you're going to get 15 milliseconds because it's 10 squares, each with a division of 1.5 milliseconds. So therefore, you can work out what the frequency is going to be because the time period therefore for one cycle is going to be 10 milliseconds. So therefore, it's 1 over 10 milliseconds in seconds. So therefore, it is 100 hertz. Now again, you can look on the screen and work out the peak voltage to be 2 times by 1.5 volts because that's how much each square is worth, so it's 3 volts. The RMS is going to be the peak divided by square root 2, so it's 2.12 volts. Now, if you turned off the time base, a very common question, you would no longer get a wave pattern, rather you would get a vertical line, which would be twice the length of the peak voltage, because it's peak to peak, so it's positive and negative, okay, and then the trace will no longer move horizontally, so therefore it would just be creating that vertical line. The next question says, a technician is designing a transformer. Calculate the number of turns needed in the transformer and then state 2 methods of reducing power losses from a transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we're using the transformer equation. Vp over Vs equals Np over Ns. Remember, V is directly proportional to N. Pop it all through, we get 300 turns. That feels right because the potential difference has gone down from 240 to 90, so therefore the number of turns will go down as well from 800. Now, you've got to know all the ways we make a transformer efficient. So that could be use a wire with a greater diameter, because that will reduce resistance. Use a wire with a low resistance. Use laminations in the core to prevent eddy currents. Use an insulated laminate, the same thing, okay, use materials with a low hysteresis in the coil to stop heat energy loss when you've got an alternating magnetic field, okay, and you can also reduce the heat in the circuit by cooling it down. The next question says, the national grid is a network of cables and transformers connecting power stations to consumers. A 1,500 megawatt power station has a series of transformers that step up the output PD from 25 kilovolts to 400 kilovolts. Calculate the ratio of turns from the first primary to the last secondary coil in the power station. Assume the transformers are ideal, that means it doesn't lose any energy to the surroundings. The resistance in the transformer cables is 30 ohms. Determine the power loss in the transmission cables. Then calculate the efficiency of the transmission system. Then the student asks why the electricity is stepped up for electrical transmission since power loss is equal to V squared over R. Explain why high PD is used for electrical transmission and correct the misconception. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, once again, we're using the transformer equation. So NS over NP equals Vs over Vp, so therefore we can work it through to be 400,000 over 25,000. Remember, it's kilovolts and kilovolts, so we turn those into volts, so we get our ratio of 16 to 1. Now, what's the power loss? Well, we know current is equal to power divided by potential difference. We've got our power, okay, to be 1,500 times by 10 to the 6. We divide it by the potential difference of 400 kilovolts, because that's what it's going to be in the transmission cables, because it's gone to 400 kilovolts. So it's 3,750 amps. We know the equation for power loss in a cable is I squared R. Pop in all the values, we get 4.2 times 10 to the 8 watts. The efficiency, therefore, is the useful output over the total input. We know that the useful output is going to be the 1,000, so the useful output is 1,500 times 10 to the 6 minus the power loss in the cable. We then divide it by the 1,500 times 10 to the 6, because that's our total input, so it's 0.72%. Now, why is this a misconception? Well, if you step up the potential difference, the current decreases by a factor of 16, so because it's, it links through in that particular logic. So therefore the power loss in the cable is due to the heating effect of the current, so we don't tend to use P equals V squared over R. It's more due to the current and this heating effect, so we can use P equals I squared R. So therefore you could possibly use P equals V squared over R, but that's not the potential difference. That's not the potential difference of one instance. It's from the start to the end, so it's not 400,000. Okay, so therefore it's easy to use the current through the cable because that's constant through the cable, because it's one long series circuit. So because V isn't a constant factor in the cable, we can't use that in the equation, but we can use current. So we use P equals I squared R. The next question says, calculate the length of the copper wire that has a diameter of 1.6 times 10 to the minus 3 meters and a resistance of 25 ohms. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters. Then the resistance of copper wire is not zero. Explain why this fact leads to the use of the alternating current rather than the direct current when transmitting electrical energy. So pause the video now, then unpause the video when you want to go through your answers. Right, so this one is revision from paper 1 again. So we know that resistance equals resistivity times by length over area. Now again, that equation is given to you on your sheet. So L equals RA over rho. Pop in all the values. Now remember, area is pi r squared. So we take our diameter and we half it before we square it. So we work it through, the area to be 2 times 10 to the minus 6 meters squared. Pop in all the values and the length is 3,000 meters. Now again, the resistance, okay, will lead to energy loss, power loss, energy dissipated squared of the surroundings. So therefore we know that because the power loss is I squared R, so the bigger the value of R, the bigger the loss of power loss. So therefore you can also say that you want to use alternating current because that will lower the current, which will lower the loss of heat or energy or power and reduces that voltage drop. And that happens because alternating current can be used, it can be transformed in a transformer, but direct cannot, because it needs a change in magnetic flux linkage, which doesn't occur if you're using a direct current. So thank you very much. Have a look at thermal physics. So the first question say, describe a liquid in terms of its arrangements of particles, the bond between them and their motion. Then use the kinetic model of matter to explain the following. If you leave a pan of water on the hob for a long time, it will not all boil away as soon as the temperature reaches 100 degrees Celsius. It takes less time to melt 1 kilogram block of ice at 0 degrees Celsius than to boil away 1 kilogram of water at 100 degrees Celsius, and then when a dog overheats, it pants. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you know that the bonding and links of particles are that for a liquid, bonds are relatively strong. They're stronger than a gas, but weaker than a solid, and the molecules are free to move through the body of the liquid. Now in the second one, 2.1, it's the idea that the energy has to be supplied to convert the liquid into a vapor, which takes time to do this. It takes time to break away those bonds. In the third one, when ice is converted into liquid water, only a few intermolecular bonds will be broken to go from a solid to a liquid, whilst when you go from a liquid to a gas to a vapor, all the molecules are completely separated, all the intermolecular bonds are broken. That requires more energy. And then finally, a dog doesn't actually sweat through his skin like humans do. Instead, they sweat from their tongues. The sweat then evaporates and cools the dog. Now, panting blows air across the tongue, which will increase the rate of evaporation. The next question says, a solid is heated until it melts. The heating continues until the liquid metal boils. Compare the similarities and differences between melting and boiling for a metal. Your answers refer to the energy of the metal, the separation between the atoms of a metal, and the forces between the atoms of a metal. So pause the video now, then unpause the video when you want to go through your answer. Right. What's similar about the solid and the liquid metal? Well, the first thing is, in similarities, energy has to be supplied in both melting and boiling. So it means that both melting and boiling will increase the overall internal energy of the atoms in the metal. Now, in terms of the melting and boiling, it's a change of state. So we know during a change of state, there'll be no change in temperature because there's no change to the kinetic energy store of the substance, only the potential energy store. Now, what are the differences? Now, boiling results in a larger separation between the atoms. So in boiling, the particles are separated so far apart that almost no force will exist between the atoms. Okay, whilst in melting, the atoms are separated sufficiently to slide over each other, but not completely. So we can say that in boiling, the atoms have become pretty much independent of each other and all the intermolecular forces of attraction or intermolecular bonds have been removed. That's not the case when they're melting. Now we also know that boiling occurs at a higher temperature. Temperature is proportional to the kinetic energy store of the object, so therefore the atoms will be moving faster or have a greater kinetic energy during boiling than there would be during melting. And then we also know, as stated previously, more energy is needed to be separating the molecules in boiling compared to when it would be in melting. The next question says, use the first law of thermodynamics to answer the following. A gas is heated by supplying with 250 kilojoules of energy. At the same time, it is compressed so that 500 kilojoules of work is done on the gas. Calculate the change in internal energy of the gas. Then the same gas is heated as before with 250 kilojoules of energy. This time the gas is allowed to expand so that it does 200 kilojoules of work on its surroundings. Calculate the change in the internal energy of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, what do we know? Well, we know that in the first law of thermodynamics, the change in internal energy is equal to the energy supplied by heating the object plus the energy supplied by doing work on the object as well. Now, you do work on the gas when it is compressed. You do not do work is done by the gas when it's expanding. So we know that there's 250 kilojoules supplied by heating. There's 500 kilojoules supplied when it's compressed in the gas. So overall, it's plus 750 kilojoules. kilojoules, so work is going into the gas. In the second one, again, change in internal energy is equal to the energy supplied by the heating plus the energy supplied by doing work on the gas. Now we know here that the gas is expanding, so therefore it's 200 kilojoules out of the gas, so therefore it is minus 200. So it is plus 250 minus 200, so therefore it's 50 kilojoules. The next question says, convert each of the following temperatures from the Celsius scale to the thermodynamic scale, which is the Kelvin scale. So 0 degrees Celsius, 20 degrees Celsius, 120 degrees Celsius, 500 degrees Celsius, minus 23 degrees Celsius, and minus 200 degrees Celsius. Then convert the following temperatures from the thermodynamic or Kelvin scale to the Celsius scale. 0 Kelvin, 20 Kelvin, 100 Kelvin, 300 Kelvin, 373 Kelvin, and 500 Kelvin. And then give one word for each of the following. Adding a scale to a thermometer. All the temperatures from lowest to highest which a thermometer can measure. The extent to which equal rise in temperature give equal changes in a thermometer's output. And then how big a change in output is produced by a given temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, we need to know the difference between the temperature in Kelvin and the temperature in degrees Celsius. So temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. So we get 273, 293, 393, 773, 250 and 73 Kelvin. It's the other way around for the next one. So the temperature in degrees Celsius is the temperature in Kelvin minus 273.15. So it's minus 273 degrees Celsius, minus 253 degrees Celsius, minus 173 degrees Celsius, plus 27 degrees Celsius, plus 100 degrees Celsius, and plus 227 degrees Celsius. Adding a scale to a measuring device is called calibration. The values from highest to lowest a measuring device can measure is the range. The extent to which the equal change in temperature given equal change in the output is called linearity, and then how big a change in output is produced by a given change in temperature is the sensitivity of the device. The next question says, a block of paraffin wax was heated gently at a steady rate. The heating was continued after the wax had completely melted. The graph shows how the material's temperature varied during the experiment. For each section of the graph, describe the state of the material. For each section, explain whether the material's internal energy was increasing, decreasing, or remaining the same. Then consider the two sloping sections of the graph. State whether the material's specific heat capacity is greater when it is a solid or when it is a liquid. Justify your answer. So pause the video now, unpause the video when you want to go through your answer. Right, so AB is going to be a solid. BC is when it's melted, so it's a solid and a liquid. And then CD is there when it's fully become a liquid. Now in each part, AB, BC and CD, you are putting energy into the substance by heating it up, so the internal energy is going up in all three sections. Now in the next one, in the two sloping sections, the specific heat capacity is greater when it's a solid, because the specific heat capacity is the energy needed to change the temperature by 1 degree Celsius when you have 1 kilogram. Now the gradient is greater when it's a liquid, so it takes less time to raise the temperature by the same amount when you transfer the same amount of energy, so therefore the less energy is needed. The next question says, calculate the energy which must be supplied to raise the temperature of 5 kilograms of water from 20 degrees to 100 degrees. Then which requires more energy, heating a 2 kilogram block of lead by 30 Kelvin or heating a 4 kilogram block of copper by 5 Kelvin. Then a well insulated 1.2 kilogram block of iron is heated using a 50 watt heater for 4 minutes. The temperature of the block rises from 22 degrees Celsius to 45 degrees Celsius. Find the experimental value for the specific heat capacity of iron. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that to work out the energy supplied when you've got a change in temperature, it's E equals MC, change in temperature. So you can do for each one, and there you get 1.7 megajoules when you pop in all the values. The next one, here again, you work out each one with E equals MC, change in temperature. So for the lead, you'll get 7.56 kilojoules. For the copper, you get 7.60 kilojoules. So the copper block requires more energy. Now, in this instance, it's a bit harder because we haven't got energy, but we all have got power and time. So energy is power times time, where time is given in seconds, so therefore our energy will be 12 kilojoules. We can then say C equals E over M change in temperature. So therefore when we work it all through, we get about 435 or 440 joules per kilogram per Kelvin. The next question says, At higher temperatures, the graph shown deviates increasingly from a straight line, suggests an explanation for this. Then in measurements of the specific capacity of a metal, energy losses to the surroundings are a source of error. Is this a systematic error or a random error? And justify your answer. Then, in an experiment to measure the specific heat capacity of water, a student used an electrical heater to heat up some water. His results are shown below. Calculate a value for the heat capacity of water. Comment on any likely sources of error. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to remember at higher temperatures that the object will be a greater radiator of energy. So therefore the rate of energy loss to the surroundings is greater, so the temperature rise of the substance will be lower. Now, energy loss to the surroundings is a systematic error because it can be theoretically removed by perfect insulation, which is what we define systematic error to be, an error that can be removed from the experiment by taking away the value of the error. Now, in this next one, the first thing we can do is work out the mass of the water by doing the mass of the beaker taken away from the mass of the beaker and the water. So we therefore get 0.522 when you work through your answer of grams, which they convert into kilograms afterwards. We can then say power is P equals VI because we've got current, we've got potential difference, so it's 44.5 watts. In 30 minutes, you can work out the energy supply by doing E equals power times by time. Convert our 13 minutes into seconds, so we get 34.7 kilojoules. We can work out our change in temperature. We can then say C equals E over M times by change in temperature. We then work it all through and we get 5,700 joules per kilogram per Kelvin. Now, the biggest source of error, as mentioned before, will be the energy loss due to the surroundings. Now, this could also include the energy being given to the beaker itself, so therefore we can reduce that by insulating the entire substance. The next question says, a student measured the temperature of some oil in a beaker. The temperature of the oil is 20 degrees Celsius. Give this temperature in Kelvin. Then the student heats 600 grams of oil using an immersion heater. The temperature of the oil increased from 300 Kelvin to 350 Kelvin. Show that the minimum amount of energy supplied to the oil is approximately 63,000 joules. The specific heat capacity of the oil is 2,090 joules per kilogram per Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, so we can convert from degrees Celsius into Kelvin by adding 273.15, that's 293.15 Kelvin. Here we know E equals MC triangle T. We convert our grams into kilograms. We then work out our change in temperature to be 50. We pop in all the values and we get 62,700 joules. The next question says, describe the changes to the kinetic energy, the potential energy, and the total internal energy of the molecules of a block of ice as it melts at 0 degrees Celsius and as the temperature of the water rises from 0 degrees Celsius to room temperature. Then explain in terms of kinetic energy why the temperature of a stone increases when it falls from a cliff and lands on a beach. Explain why the barrel of a bicycle pump gets very hot as it's used to pump up a bicycle tyre. And then the zeroth law of thermodynamics states that if a temperature of a body A is equal to the temperature of body B, and the temperature of body B is the same as body C, then the temperature of body C equals that of the temperature of body A. Explain in terms of energy flow why the concept of temperature will be meaningless if this law was not obeyed. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, because we're changing state, the kinetic energy remains constant, the potential energy will increase because we are changing state by heating it up, so therefore the overall internal energy increases. In this next one, the kinetic energy will increase as the temperature increases, the potential energy remains constant, so therefore the overall internal energy will increase. Now in this next one, just before the stone hits the ground, it has kinetic energy. So all the molecules moving together in the same direction. When it hits the ground, the unidirectional movement of the molecules is converted into the movement of individual molecules in random direction. So therefore the kinetic energy from movement in random directions is the internal energy, and therefore the temperature will rise. In the next one, the air is being compressed, so work is being done on it. So from the first law of thermodynamics, the change in the internal energy of a body is equal to the energy supplied by heating plus the energy supplied by doing work. So therefore there's no energy supplied by heating, but work is being done by compressing that gas, by compressing the air. Now in this last one, if two bodies are the same temperature, no energy flow will happen from one body to another. So therefore if no energy flows from A to B and none flows from B to C, but if energy did flow from C to B, it would mean that A and B were the the same temperature and A and C have the same temperature, but C will be hotter than B, which is clearly not correct, which is a fundamental law in thermodynamics. The next question says, the specific latent heat of vaporization of water is 2.26 megajoules per kilogram. Calculate the energy needed to change 2 grams of water into steam at 100 degrees Celsius. The specific latent heat of fusion of water is 330 kilojoules per kilogram. Calculate the energy needed to change 2 grams of ice into water at 0 degrees Celsius. Suggest why the answer is much smaller than the amount calculated in 1.1. Then a sample of alcohol is heated with a 40 watt heater until it boils. As it boils, the mass of liquid decreases at a rate of 2.25 grams per minute. Assuming that 80% of the energy supplied by the heater is transferred to the alcohol, estimate the specific latent heat of vaporization of the alcohol, given your answer in kilojoules per kilogram. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know E equals ml, that's the equation for latent heat, so therefore we can pop in the values. Remember to convert grams into kilograms, convert the megajoules per kilogram into joules per kilogram, so therefore it's 4,520 joules. In this next question, E equals ml again, convert our grams into kilograms and our kilojoules per kilogram into joules per kilogram. So when you multiply them together, we get 660 joules. Now when a solid melts, only about 1 bond per atom or molecule is broken in the melting process. But in boiling, all of the bonds are broken, so it needs more energy to do this. Now in this next question, we know that the rate of loss of mass is 2.25 grams per minute, so we can work that into seconds and say it's therefore 3.75 times 10 to the minus 5 kilograms per second. Now the energy supplied to the alcohol is 80% of the energy supplied by the heater, so 40 times by 0.8 is 32 watts, so therefore the latent heat L is going to be equal to E over M, or the rate of energy supplied divided by the rate of mass loss, so therefore it's the power over the rate of mass loss, so we can pop those values in and we get 850 kilojoules per kilogram. The next question says, a cylinder contains 0.80 decimeters cubed of nitrogen gas at a pressure of 1.2 atmospheres. A piston slowly compresses the gas to a pressure of 6 atmospheres. The temperature remains constant. Calculate the final volume of the gas. Then a balloon contains 0.04 meters cubed of air at a pressure of 120 kilopascals. Calculate the pressure required to reduce its volume to 0.025 meters cubed at a constant temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, here we've got to remember that Boyle's law, that P1V1 equals P2V2. You don't need to change units because it's a ratio, so you pop in the values, so you get 0.16 decimeters cubed. Do the same for the next one. We can work it all through. Here we can then change it into pascals just to make it easier and work out our value. So we work it through and we get 1.9 times 10 to the 5 pascals. The next question says, a sealed container contains 60 moles of gas at a temperature of 250 Kelvin and a pressure of 60,000 pascals. Calculate the volume of the container. State the effect on the pressure of a fixed mass of gas at constant temperature if the volume of the gas is doubled or reduced to a third of its original value. Then a fixed mass and volume of gas initially at a temperature of 20 degrees Celsius and a pressure of 300 kilopascals is heated to 100 degrees Celsius. Calculate the change in pressure. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got moles, we've got temperature in Kelvin, we've got pressure. So we can say PV equals nRT, the ideal gas equation. So V equals nRT over P. R is the molar gas constant given to your new equation sheet. Pop in all the values, 2.1 meters cubed. We can say here, if you remember for Boyle's law, that P and V are inversely proportional to each other. So therefore, if the volume is doubled, the pressure will halve. And if the volume is reduced to a third, well then P would increase by 3 or would triple. Now in this next one, we know from the second law, from Charles's gas law, that P over T is a constant. So we can work out what that constant is from the initial values given. So it's 300,000 over 293. We converted our temperature into Kelvin and our pressure into pascals, so we get 1020. So therefore afterwards we can say pressure is that constant times by the new temperature, again in Kelvin, so therefore we work out the new pressure is 401,000 pascals, and it asks for the change in pressure, so find the difference between that and the starting pressure of 300,000, so it's 101,000 pascals. The next question says, Figure 4 shows an example of a Carnot cycle engine. The cylinder contains a fixed mass of gas. The piston moves in the direction as shown. Explain what happens to the internal energy of the gas, refer to the motion of the gas molecules and the gas temperature. A cylinder contains some gas at a temperature of 400 Kelvin. The pressure of the gas in the cylinder is 201,400 pascals. The cylinder and the gas inside the cylinder cool to 293 Kelvin with no change in volume. Calculate the pressure of the gas when its temperature is 293 Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that the internal energy of the gas will increase. Why is that? Well, the gas is being compressed, so therefore work must be being done onto the gas. So therefore energy is being placed into the gas. This will cause the temperature to increase because in theory there's no potential energy in the gas, because therefore the molecules will have a high kinetic energy. In this next one, again we use P1V1 equals P2V2. We work it all through, remember popping all the values in, and we get 148,000 pascals. The next question says, consider a smoke particle of mass m and speed v. It is constantly buffeted by air molecules. The mass of a single air molecule is m and its speed is v. It is reasonable to assume that on average the smoke particle will have a kinetic energy approximately equal to the kinetic energy of a single air molecule. So that big M is much greater than small m, and it follows that the air molecules must be moving much faster than the smoke grain. Then if equal numbers of air molecules hit a smoke particle from all directions, the smoke particle does not move. State 3 ways in which the random movement of molecules of air causes the smoke particle to move. Describe and explain what you would see through a microscope observing Brownian motion when the temperature increases. Then an oxygen molecule is moving around inside a spherical container of diameter 0.10 meters. The molecule speed is 400 meters per second. Estimate the number of times each second the molecule collides with the container's walls. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the time taken to cross the diameter of the container once is distance over time, which you can work through with the values roughly to be about 2.5 times 10 to the minus 4 seconds. So if you assume a molecule speed is constant and therefore each collision is including like that, okay, well therefore you can say the number of collisions is 1 over time, so it's 1 over 2.5 times 10 to the minus 4, so it's about 400 collisions every second. Now, it's different because the different number of molecules hit one side than the other. The number of molecules striking any area per second will vary. The speed of the molecules hitting will vary, and the angle that the molecules hit the smoke detector will also vary. The next one, you'll see with Brownian motion, the smoke particles will move faster and more erratically because at a higher temperature, the molecules of air will be moving faster because temperature links to the kinetic energy of the molecule. So therefore, the impact will cause a greater change in the momentum of the smoke particle. Okay, and then finally, okay, as we said before, the answer is going to be 400 times per second. Now the next question says, state and explain in terms of the kinetic model what happens to the pressure inside a tyre when more molecules at the same temperature are pumped into the tyre. Then explain using the kinetic model why a can containing air may explode if the temperature rises. So pause the video now, then unpause the video when you want to go through your answer. Right, remember that pressure is caused by the change in momentum that the particles have on the side of a container. So the pressure increases because more particles are hitting a unit area of the tyre every single second. The frequency of collisions has gone up. So the molecules have the same speed because they've got the same temperature, and temperature links to kinetic energy. So each collision will cause the same impulse or change in momentum. Now since more molecules hit per second, the rate of change of momentum, which is the force, will increase, which increases the pressure. Now in the next one, at higher temperatures, the molecules have higher internal energy and therefore move faster because the only internal energy they have is kinetic energy. So the number of collisions per second will increase, and the change in momentum of each collision will also increase because they're hitting harder. So for both these reasons, the rate of change of momentum of the molecules increases. Now the force on the wall is equal and opposite to the rate of change of the momentum of the molecules. So as the force increases, the pressure inside the can will also increase, which may cause it to explode. In the next question, it says, check that the units on the left hand side of the equation, P equals a third, nm over v times by c squared, are the same as those on the right hand side. Then the quantity nm is the total mass of the molecules of the gas. So the mass of the gas. At room temperature, the density of air is about 1.29 kilograms per meters cubed at a pressure of 10 to the 5 pascals. Use these figures to deduce the value of c squared for air molecules at room temperature, and then find a typical value for the speed of a molecule in air by calculating the root of c squared. How does this compare with the speed of sound in air? So pause the video now, then unpause the video when you want to go through your answer. Right, let's look at some dimensional analysis. So the units of pressure is P equals F over A, so therefore it's MA over A, which we can therefore say is kg ms to the minus 2 over m squared. So therefore the overall units of pressure are kg m to the minus 1 s to the minus 2. Whilst on the right hand side, we can say it's nm times by c squared over v, so therefore it's going to be kilograms, because n is just a number, so it'll have no values. So it'll be kg, there'll be ms to the minus 1 squared, because it's going to be speed squared, divided by the volume, which is meters cubed, which goes to be kg m to the minus 1 s to the minus 2, which is the same units on each side. In this next one, we can rearrange the equation to say P equals nm times by c squared over 3v. So therefore c squared is equal to 3pv over nm. Pop in all the values, we can work it through. Now remember, density is mass over volume, so therefore you can link it to be divided by the density, because it's going to be m over v. So therefore it's 3 times 10 to the 5 times by 1 over 1.29, 2.3 times 10 to the 5 meters squared seconds to the minus 2. Then we can work out our answer by square rooting this value to be 480 meters per second, which is about 50% greater than the speed of sound and air, 330 meters per second. The next question says the Boltzmann constant K is equal to R over NA. From the values of R and NA, show that K has a value of 1.38 times 10 to the minus 23 joules per Kelvin. Then write down an equation linking the Boltzmann constant, the thermodynamic temperature, and the average kinetic energy of a molecule. Calculate the mean kinetic energy of atoms in an ideal gas at 27 degrees Celsius. The atoms in a gas have a mean kinetic energy equal to 5 times 10 to the minus 21 joules. Calculate the temperature of the gas in Kelvin and then in degrees Celsius. And then show that if the mean speed of the molecules in an ideal gas is doubled, well then the thermodynamic or Kelvin absolute temperature in Kelvin of a gas is increased by a factor of 4. So pause the video now, then unpause the video when you want to go through your answer. Right, we can work out the Boltzmann constant because K is equal to R over NA. You're given R, you're given NA on the equation sheet, so you get 1.38 times 10 to the minus 23 joules per Kelvin. The next one we know from the equation sheet that the kinetic energy of one molecule is 3 over 2 kT, where T is in Kelvin. So therefore we work it through by saying, well, 3 over 2 kT or 3 over 2 RT over NA. Pop in all the values, convert the temperature into Kelvin. So we get 300, and then we work it through to be 6.2 times 10 to the minus 21 joules. In this next one again, we can say, well, kinetic energy is equal to 3 over 2 kT or is equal to a half mc squared, so half mv squared. Pop in all the values, remember to make T the subject, which is 242 Kelvin or minus 31 degrees Celsius. Then we can see that temperature from the previous equation is going to be proportional to the average speed squared. So therefore, if the speed doubles, well then the temperature will increase by a factor of 2 squared, which is 4. The next question says, a fixed mass of gas expands to twice its original volume at a constant temperature. How do the following change? The pressure of the gas and the mean kinetic energy of the gas molecules. Air consists of oxygen, molar mass 32 grams per mole, and nitrogen, molar mass 28 grams per mole. Calculate the mean kinetic energy of these molecules in air at 20 degrees, then estimate the typical speed for each type of molecule, and then show that the change in internal energy of 1 mole of an ideal gas per unit change in temperature is always constant, and what is this constant going to be? So pause the video now, then unpause the video when you want to go through your answer. Right, we can see that, like we said before, PV equals to a constant. So therefore, if we can work it through to say that if it's now twice its original volume, well, therefore the pressure will half. Now the kinetic energy will remain the same because E equals 3 over 2 kT. K and T are constant, so therefore the kinetic energy will be constant. We can work out the kinetic energy for each one by doing 3 over 2 kT, or we could be doing a half mv squared. Now m is the mass of one molecule, so you can work that through by doing, well, the molar mass is divided by Avogadro's constant is going to therefore give you the mass of one molecule, because the molar mass is the mass of one mole. The Avogadro's constant is the number of molecules in one mole, so therefore you can work it through that way. So when you work it all through, make v the subject to work out the average speed of the molecules. Oxygen comes out to be 480 meters per second, and nitrogen comes out to be 510 meters per second. Now, like we said before, we can say that the internal energy is going to be the kinetic energy store, because in a gas there's no potential energy in that gas, so it's only kinetic energy being the internal energy store. So therefore it's the kinetic energy of one molecule, 3 over 2 kT, times by the number of molecules in that gas, which is 1 mole, so therefore it is Avogadro's constant. We know that, therefore we can say that Na, okay, then in that point divided by K at that point, so times by K will equal R, so therefore it's 3 over 2 RT, so therefore the change per Kelvin is 3 over 2R. The next question says, describe what happens to the absolute temperature of a gas if the RMS speed of the particles in the gas firstly increases, then doubles, then increases by a factor of 5. Then the gas canister has a volume of 0.50 meters cubed. The pressure inside the canister is 450 kilopascals and the temperature is 18 degrees Celsius. Calculate the number of particles of the gas and the number of moles inside the canister. Then explain why doubling the temperature of a real gas does not double the internal energy. So pause the video now, then unpause the video when you want to go through your answer. Right, well, firstly, we know that temperature links into speed because they're proportional to each other. Okay, so therefore as the temperature increases, well, therefore the speed will also increase. Okay, next one, we know that temperature is actually proportional. Okay, so it links to the speed squared. So if the speed doubles, well then the kinetic energy will quadruple as the temperature will also quadruple. And then once again, if the speed increases by a factor of 5, the kinetic energy and the temperature will increase by a factor of 25 because it's proportional to 5 squared. Now in the next question, we can work out the value here by saying PV equals big N kT. That's another ideal gas equation. So N equals PV over kT. Remember, P is in pascals, not kilopascals, so you can pop in all those values, convert 18 degrees Celsius into Kelvin, so you get 5.6 times 10 to the 25 particles. Divide that then by Avogadro's constant, the number of particles in 1 mole, to work out the number of moles, so you get 93.1 moles. Now in the last question, double the temperature of a gas in the real world doesn't actually double the internal energy. It will double the kinetic energy of the atoms in the gas, but the atoms and molecules in a real gas will also have potential energies, which we don't assume in an ideal gas. So in a real gas, the internal energy is equal to the sum of the kinetic and the potential energies of the atoms within the gas. So doubling the kinetic energy won't equal the doubling the internal energy, because there's potential energy there as well. The next question says, an oxygen molecule has a mass of 5.3 times 10 to the minus 26 kilograms. Calculate the RMS speed of an oxygen molecule at room temperature. Then compare the kinetic energy and RMS speed of room temperature of a helium atom of mass 6.6 times 10 to the minus 27 kilograms with the answer to the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, we can say, well, a half mv squared or half mc squared is equal to 3 over 2 kT. Rearrange it, make the speed the subject, pop in all the values, change the temperature into Kelvin, so therefore we get 480 meters per second. Now we should know that kinetic energy is 3 over 2 kT, so because they're at the same temperature, room temperature, they'll have the same kinetic energy, but the speed of the helium atom will be greater because the oxygen molecule has 8 times as much mass as the helium one does. So therefore, to have the same kinetic energy, the helium must be travelling at 2.8 times, or square root 8, because a half mv squared, faster, so they link in like that. The next question says, wax is heated until the temperature is melted above the melt point of the wax. The hot wax is poured into a bowl and allowed to cool. The graph shows how the temperature of the wax varies with time as it cools. Describe how the internal energy of the wax changes as the wax cools. You should refer to the energy of the wax molecules as the liquid cools and becomes a solid, and the solid wax cools. Times x and y have been included to help refer to the graph. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the internal energy of the wax decreases during cooling because energy is leaving the substance. So the internal energy is the sum of the potential and the kinetic energy of the molecules. As the temperature decreases, then the kinetic energy store of the molecules will decrease. So between times x and y, as it's solidifying, the potential energy store decreases because it's changing state. Between times x and y, the temperature is constant because there's no change in the kinetic energy store. At time y, the wax is finished solidifying and the temperature then starts to drop. The next question says, a 500 watt kettle contains 300 grams of water at 20 degrees Celsius. Calculate the minimum time it would take to raise the temperature of the water to boiling point. Then the kettle is allowed to boil for 2 minutes. Calculate the mass of the water that remains in the kettle, stating any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see E equals MC triangle T, or change in temperature, because there's a change in temperature here. Convert our grams into kilograms, and we work it through to be equal to 100,320 joules. Time is energy over power. We know it takes 500 seconds, because we work in, 500 watts there. So we get our answer out to be 201 seconds. Now we're assuming no energy goes into heating the element, or the kettle, or is being lost to the surroundings. Now in this next one, again, we say E equals power times by time, so it's 500 times by 120. Minutes go into seconds, so we get 60,000 joules. The mass of water boiled away, because it's a change in energy, a change in state, is going to be E over the specific latent heat. So it's 60,000 over 2.26 times 10 to the 6, which is 0.027 kilograms. So therefore that's 27 grams. So therefore the mass left over is going to be 300 grams, the starting mass, which is told you the previous part of the question, minus 27. So it's about 270 grams. Now assuming here that no energy is lost to the surroundings and all the vapor will escape the kettle. The next question says, explain what is meant by the specific heat capacity of a substance. Now the figure shows the apparatus used to measure the specific heat capacity of a copper block of mass 850 grams. The block is initially at 12 degrees Celsius. The heater is switched on and the time taken for the temperature to rise to 30 degrees is recorded. The block is cooled to the original temperature and the potential difference across the heater is increased and the experiment is repeated. The results are shown below. Explain why a thermocouple thermometer is suitable for this experiment. Explain why the experiment is repeated using a different power input and calculate the specific heat capacity of the copper. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one's a definition. So it is the energy required to raise the temperature of 1 kilogram or a unit mass of a substance by 1 degree Celsius. Now a thermocouple thermometer is used because it has a very small heat capacity and it can quickly act and will quickly record the temperature. The next one, we will use different power inputs to allow for energy losses to the surroundings. So to work out the heat capacity, you'll do the input of the energy, which is 40 times by 190, so 7,600 joules. The experiment one is the energy input is MC triangle T plus the energy losses. So you can work that through to be 7,600 equals 15.3 C plus Q1. Same for experiment 2, and you get 6,840 equals 15.3 plus Q2. You can then subtract the equations 1 and 2 to get 7,600 minus 6,840 equals Q1 minus Q2. We can then sub that into the previous equations, and therefore we can work out Q1 to be 1,900 joules. So therefore when you pop it into the equation for 1, we will say 7,600 equals 15.3 C plus 1,900, we get 372 joules per kilogram per degree Celsius. The next question says, an electric shower runs at 230 volts and 46 amps. In the summer, it increases the water temperature from 22 degrees Celsius to 39 degrees Celsius. Calculate the thermal energy used to increase the temperature of 1 kilogram of the water. Now, the heat capacity of the water is 4,200 joules per kilogram per Kelvin. Calculate the time it will take the heater to deliver this amount of thermal energy. In winter, the inlet water temperature drops to 5 degrees Celsius, but the final temperature remains at 39 degrees Celsius. State and explain the change to the water flow rate for this shower in winter compared to summer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, E equals MC triangle T, or change in temperature. So it's 4,200 times by 1 times by 17, 71.4 kilojoules. Now we can say T equals this energy, okay, divided by IV, or the power. So therefore it's 71.4 times 10 to the 3 over the power, which is 230 times by 46, is 6.75 seconds. And we can say in this next one, the change in temperature is doubled, so therefore the flow rate, or the change in mass per time, is going to have to half to keep that constant value for C, because we can see that C is going to equal to be delta E over MC triangle T, or delta phi, so therefore it's going to have to half for when the change in temperature is doubled. The next question says cocoa powder, milk and hot water are mixed together to produce a hot chocolate. The mass of the drink is 275 grams and its initial temperature is 71.5 degrees Celsius. The ice at 0.0 degrees Celsius is added to the drink to reduce its temperature. Research indicates that the maximum serving temperature of any hot drink should be 58.0 degrees Celsius. Deduce whether 4 grams of ice would be enough to bring the temperature below 58.0 degrees Celsius. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we can say that the energy transfer from the hot liquid is the energy transferred to the ice plus the energy transferred to the cold water. So we can say that E is going to equal MC, change in temperature, so 0.275 times by 3,750 times by 71.5 minus 58, which will equal those two other energies, so M times by L plus by M times by C times by change in temperature. So we can work that through, and we've got M coming out as a constant term. So as you can see here, M is going to equal 1.39 times 10 to the 4 over 5.77 times 10 to the 5, which equals about 24 grams. So adding 4 grams wouldn't bring the temperature below the ideal serving temperature. You would in fact need 24 grams for this to work. The next question says, lead shot contains a small lead spheres. Originally, lead shot was made by dripping molten lead through copper sieve from the top of a shot tower. The lead cooled as it fell before landing in the water and producing solid lead spheres. Figure 1 shows a shot tower and Figure 2 shows the process of a lead shot in the shot tower. Now, to avoid producing steam, the temperature of the lead was below 100 degrees Celsius as it reached the cold water. As the lead sphere falls through the distance of 41.5 meters, so it takes 3 seconds for the lead sphere to fall this distance, assuming that resistive forces are negligible. The lead sphere has a radius of 1.2 millimeters. As it falls, it cools from 615 to 370 Kelvin. The molten lead solidifies at 601 Kelvin. Calculate the mean rate at which the energy is transferred from the lead sphere to the surroundings. You should assume that the sphere heat capacity of liquid lead and the solid lead are the same. So pause the video now, then unpause the video when you want to go through your answer. Right, we can just use suvat in this question because it's going to be constant acceleration. So S equals ut plus a half at squared. Remember, A is minus 9.81 and S is minus 41.5. So therefore T will equal 2.91 seconds. In this next one, we work out what the volume is going to be by doing 4 over 3 pi r cubed. So we get our volume out. We can then say the mass is the density times by the volume. So we get our mass to be 8.18 times 10 to the minus 5 kilograms. We can then say, well, what's the energy change going to be when it changes temperature? Well, you do E equals MC change in temperature. Pop in all those values and you get 2.61 joules. We can then look at E equals ML as it changes state, as it solidifies, by doing mass times by the latent heat capacity, which is 2.02 joules. So add the two together, that's the energy change, divided by the time will give you the power, so you get 1.60 watts. The next question says, a student learns that the energy required to heat water for a bath can be 10 times the energy required to heat water for a shower. The student uses the shower for 9 minutes and the water comes out of the shower at 38 degrees at a flow rate of 1.8 times 10 to the minus 5 meters cubed per second. The student usually fills the bath with 160 kilograms of water at 32 degrees Celsius. Deduce whether the bath uses 10 times more energy than the shower. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can do is work out the energy change for each one. So in the let's have a look at the bath first. So E equals MC triangle T, or change in temperature. So you can pop in all the values and then we pop out, we get 1.14 times 10 to the 7 joules. Now look for the shower. What's the mass going to be? Well, in 1 second the mass is going to be the flow rate for that 1 second. So it's going to be 1 times 10 to the 3 kilograms per meters cubed times by 1.8 times 10 to the minus 5, because we're saying mass is density times by volume. So therefore it's going to be 0.018 kilograms. So therefore we can then work out what it's going to be for 60 seconds. So say they're in the shower for 9 minutes, so do 60 seconds times by 9, so it's 0.018 times by 9 times by 60 is 9.72 kilograms. So therefore E equals MC change in temperature for this one. We'll say it's 38 to 15, so there's your difference there. So it's 9.34 times 10 to the 5. Find the ratio of the two, and it's 12.2 times, so actually it is more than 10 times. The next question says, ice cubes can be made in an ice cube tray. One type of ice cube is shown. Each compartment in the ice cube tray has dimensions of 2.5 centimeters by 2.5 centimeters by 3.5 centimeters. Show that the mass of the water needed to fill one compartment is about 0.02 kilograms. Then all 6 compartments in the ice cube tray are filled with the water to a depth of 3.5 centimeters. The ice cube tray is placed in a freezer. The initial temperature of the water is 22.5 degrees Celsius. It takes 12 minutes for all the water to become ice at 0 degrees Celsius. The manufacturer of the freezer states that the freezer can transfer energy at a rate of 110 watts. Evaluate whether energy is transferred from the water in the tray at a rate of 110 watts. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know density is mass over volume, so therefore volume is going to work out to be the mass, okay, divided by, so you can work out what the volume is going to be by doing 2.5 times 10 to the minus 2 times by 2.5 times 10 to the minus 2 times by 3.5 times 10 to the minus 2, turning centimeters into meters, so we get 2.19 times 10 to the minus 5. We can therefore say that the mass is going to be working it through to be the density times by the volume. So we've got the density, we've got the volume, multiply them together, we get 0.0219 kilograms. In this next one, we can say that the change in energy is MC change in temperature. Pop it all through. Now again, remember, it is going to be 22.5 because it starts at 0 and goes to 20, or starts at 22.5 and goes to 0. Pop in all the values. Remember, there's 6 of them when you're working out the mass, so it's 1.24 times 10 to the 4 joules. We can therefore say E equals ml because it's also freezing, a change in state. Remember, the mass is 6 of them. Then multiply by the latent heat of fusion, and we get 4.41 times 10 to the 4. Add the two together to get the total energy change, divided by the time, which is going to be in seconds, not minutes. So we work it through to be 78.5 watts. So therefore, it is not at a rate of 110 watts. The next question says, a cylinder holds 140 decimeters cubed of nitrogen at room temperature and pressure. Moving slowly so that there's no change in temperature, a piston is pushed to reduce the volume of nitrogen to 42 decimeters cubed. Calculate the pressure of the nitrogen after compression. Explain the effect on the temperature and pressure of the nitrogen if the piston was pushed in very quickly. Then the atmospheric pressure is 100 kilopascals, equivalent to the pressure exerted by a column of water 10 meters high. A ball of oxygen of volume 0.42 centimeters cubed is released by a water plant at a depth of 25 meters. Calculate the volume of the bubble when it reaches the surface. State any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one again, we're using Boyle's law. So P1V1 equals P2V2. So P2 is going to be equal to 3.4 times 10 to 5 pascals. Remember, you don't have to change the units because it's just a ratio. Now we know that PV equals a constant, so therefore, what else do we know about that? That in the other way around, we can link in pressure and temperature as well. So when the temperature of the gas increases, that will cause the pressure to be higher than the previous question. Again, we can also now use Boyle's law again to work out what V2 is going to be. Again, you don't need to change units as long as it's in the same unit. So therefore, the answer is going to be 1.5 centimeters cubed. Again, this assumes that the temperature at a 25 meter depth is equal to the temperature of the surface of the water for it to work through, because we can only work if it's a constant temperature. So we get 1.5 centimeters cubed. The next question says, this question is about an investigation into the relationship between pressure and volume of a gas. This is often referred to as Boyle's law. A student sets up the apparatus as shown in the picture. Identify a variable that needs to be controlled in the investigation. Then before setting up the apparatus, the student took measurements of the vernier calipers of the internal diameter of the tube containing the gas. The student created a dot plot of the cross-sectional area as shown. Taking into consideration any outliers, calculate the value for the mean and percentage uncertainty of the cross-sectional area of the tube, giving your answers to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to know that for Boyle's law, it only works if the temperature is constant, so that's the control. Now, if you look at the information given in the previous question, you can identify there's an outlier or anomalous result, it's 79. So therefore, you can calculate the mean correctly. So the range, work out the uncertainty by doing half the range. So therefore, you can work out the percentage uncertainty by doing the uncertainty value, which you've worked it through from working out absolute uncertainty's range divided by 2. You then divide it by the mean value, you times it by 100, and you should be getting out about 4 or 5%. The next question says, the pressure of a gas is changed and the values for absolute pressure and height of a column of gas are recorded. The data is shown in the table below. The student plots a graph to show how the relationship between the height of the column of the gas and 1 over pressure are shown. Suggest with reasons how the presentation of the graph could be improved and identify any anomalous points. The student also calculates the gradient to be 25 times 10 to the minus 6 kilonewtons per meter. Explain the physical significance of the gradient, state the assumptions and estimate n, the number of molecules of the gas that will be present at a temperature of 298 Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, how could you work this all through? So the presentation, looking at it, the x-axis scale could go with a more appropriate scale. The y-axis should be made larger so that more plotted points cover over half the grid. You should have the plotted points growing in precisely with crosses. The line of best fit's probably too steep. The third data point is anomalous. You have to have error bars onto the plots, and you should have units on your y-axis. If you think of the equations PV equals nRT, well therefore 1 over P equals V over nRT. We know volume is area times by height, and the gradient therefore of the line is area over nRT. So therefore we can rearrange it to work out that the number of moles is going to be equal to A over RT times by the gradient. That allows you to work it through to be 1.4 times 10 to the minus 3 moles. Our assumptions are the gas is ideal, it is monoatomic, it is no interactions between each other, the particles have a negligible volume, they have perfectly elastic collisions, and the time taken for any collisions is considered to be negligible or extremely small. The next question says, the escape velocity is the minimum speed needed for an object to escape the gravitational field of a planet. An object travelling at the escape velocity has a kinetic energy equal to the magnitude of its gravitational potential energy at the surface of the planet. Show that the escape velocity v for a planet of mass m in radius r is given by the expression v equals the square root of 2gm over r. Then show that the escape velocity for a mass of the Earth's surface is about 1.1 times 10 to the 4 meters per second. Then when the Earth formed, a large proportion of the gas in the Earth's atmosphere was hydrogen. Explain why the hydrogen gas is no longer a large proportion of the Earth's atmosphere. At 20 degrees, the root mean square speed is 1900 meters per second for hydrogen. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can say is we can say that the energy is equal to m times by the change in potential, which is equal to gmm over r. We can therefore say a half mv squared, which is the change in energy, is equal to gmm over r. So therefore v is equal to 2gm over r. So therefore v equals the square root of 2gm over r. You can pop in all your values given in the previous question. You work it all through. G is given on the equation sheet and we get 1.12 times 10 to the 4 meters per second. Now, you've got to understand that even though you've got a root mean square speed, that's actually a range of molecular speeds. Some molecules will travel much faster than 1900 meters per second, while some will be traveling a lot slower. It's just an average speed. So there'll be some molecules that will have a greater speed than the escape velocity, which is 1.12 times 10 to the 4 meters per second, and therefore there'll be some molecules with a high enough kinetic energy to escape, which is why lots of that hydrogen gas has left the Earth's atmosphere. The next question says, a cylinder contains 40 decimeters cubed of carbon dioxide at a pressure of 4.8 times 10 to 5 pascals at room temperature. Calculate the number of moles of carbon dioxide, the mass of carbon dioxide, then calculate the volume of 1 mole of ideal gas at a pressure of 1.01 times 10 to 5 pascals at a temperature of 0 degrees Celsius. Then a vessel of volume 200 decimeters cubed contains 3 times 10 to 26 molecules of a gas at a room temperature of 127 degrees Celsius. Calculate the pressure exerted by the gas on the vessel walls. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we can say N equals PV over RT, the ideal gas equation. Remember to change to work out what the room temperature is. It's 20 degrees Celsius or 293 Kelvin. Pop it all through, 7.9 moles. We can work out when you work it all through here, we can say, well, we can work it through by saying N equals PV equals nRT, and we can work out what that value is going to be, 7.9 moles. We can then work that through by saying it's 350 grams by using our relative molecular mass, because mass equals moles over mR. Now the next question, we can say, well, V equals nRT over P, pop in all the values, work it through, 22.4 decimeters cubed. Here again, P equals big N KT over V, pop in all the values, because now you've got N, which is the number of molecules in the question, pop it all through, and then you get your answer. Remember, temperature is going to be in Kelvin, not degrees Celsius, 8.31 times 10 to the 6 pascals. The next question says, explain what is meant by an ideal gas. Then a cylinder contains 500 grams of helium at a pressure of 5 times 10 to the 5 pascals and a temperature of 27 degrees Celsius. You may assume that helium acts as an ideal gas. So the number of molecules of calculate the number of moles of helium the cylinder holds, the number of atoms of helium the cylinder holds, calculate the volume of the cylinder. When the tap of the cylinder is open for a short time, a small amount of helium escapes into the atmosphere. As it does so, the temperature of helium drops significantly. Explain why the temperature drops, then describe what happens to the average speed of the atoms of the escaped helium. So pause the video now, then unpause the video when you want to go through your answer. Right, definition of an ideal gas, you've got to learn it. It's a gas that obeys the ideal gas laws at all temperatures and all pressures. In this next one, it's 125 moles, because we've got the, we know the mass of the helium is 500 grams, and we know what the MR of helium is, it's 2. So moles is mass over MR, 500 divided by 2 is therefore going to be 125 moles. Multiply that by Avogadro's constant, the number of molecules in 1 mole, to get the number of molecules, 7.53 times 10 to the 25 molecules. We can then work out the volume, because V equals nRT over P, pop in all the values, and we get 0.62 times 10 meters cubed. Remember, temperature is in Kelvin, not in degrees Celsius. The temperature drops because what happens is the helium does work on the atmosphere, because it's going to expand into the atmosphere, so energy is taken from the helium as it expands out, so therefore its temperature will drop. Remember, that work is done when it compresses, and work is done out of it when it expands. And then as the temperature goes down, well, therefore the kinetic energy goes down, so the average speed of the particles will drop. The next question says, a hot air balloon is basket and passengers have a total mass of 540 kilograms. The inflated balloon holds 3,000 meters cubed of air. Calculate the minimum force needed to lift the balloon off the ground. Atmospheric pressure is 1.03 times 10 to the 5 pascals, and the density of air at this pressure is 1.23 kilograms per meter cubed. Calculate the mass of 3,000 meters cubed of air. Calculate the number of moles of air in the balloon. You may consider the air of this pressure to act as an ideal gas with a relative molecular mass of 29. As the air is heated, it expands. Some of it is expelled through a vent at the top of the balloon. Calculate the maximum mass of the air that can remain in the balloon to give sufficient upthrust for the balloon to just leave the ground. And then calculate the minimum temperature that the air inside the balloon must be heated for the balloon to just lift off the ground. So pause the video now, then unpause the video when you want to go through your answers. Right, in this next one, what's the minimum force required? Well, it's going to be equal to the weight of the object. So 540 times by 9.81 is 4,410 newtons. In this next one, we can work out what the mass is going to be by doing mass is therefore going to be equal to density times by volume. We've got the pressure, and we can work it all through. We've got the density there. We've got the volume. We can work it out. So therefore, it's going to be 3,690 kilograms. Now, the number of moles is therefore going to be mass over the MR. So you can work it through that way. That gives you the number of moles to work it through. And then the next bit here is to achieve the lift, a minimum of 450 kilograms of air must leave the balloon. So therefore, the maximum mass of the air remain to be 3,690, which we've worked out as the mass of the air, minus 450, which is 3,240 kilograms. And then the remaining air is therefore going to be divided therefore by 29 times 10 to the minus 3 to work out our number of moles. PV equals nRT, so therefore T is going to be equal to PV over nR. We've got all those values, so it's 332 Kelvin, which is 59 degrees Celsius. The next question says 0.24 moles of gas is contained in a cylinder as represented. The gas is trapped by a disc of negligible mass so that the pressure in the cylinder is equal to the atmospheric pressure outside the cylinder. The disc can move up and down the cylinder without friction. Use the data to show that the length is approximately 1.2 meters, assume ideal gas behavior, and explain your reasoning. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, how do you work it through? Well, we can work out what the volume is because it's 5 times 10 to the minus 3, which is going to give you your area times by the length. We know PV equals nRT, so therefore we can substitute that volume into that equation of PV equals nRT. Pop it in, and then you got your values for N, R, and T. Remember, temperature is in Kelvin, okay? And then we've got pressure given as well, so you can pop them all through to get L to be equal 1.19 meters. The next question says, an airbag is a safety feature used in cars. Nitrogen gas is released into an airbag. The airbag inflates to a volume of 7.08 times 10 to the minus 2 meters cubed. The pressure of the gases of the inflated airbag is 1.24 times 10 to the 5 pascals. Show that the number of molecules of nitrogen gas released into the airbag is about 2 times 10 to the 24. Nitrogen gas escapes from small holes in the inflated airbag. The pressure is decreased to 3.45 times 10 to the 4 pascals. Calculate the number of nitrogen molecules that escape from this airbag. The volume and temperature remain constant. So pause the video now, then unpause the video when you want to go through your answer. Right, we know PV equals big N KT, so therefore N is going to be equal to PV over KT. Pop in all the values. Now again, remember that we work our temperature out in Kelvin, not degrees Celsius. So pop on all the values and you get 2.13 times 10 to the 24. We can therefore say for this next question that because we know the volume and temperature remain constant, well then the pressure is directly proportional to the number of nitrogen molecules in the bag. So therefore P2 over P1 equals N2 over N1. So you can work out what N2 is, pop in all the values, and we get N2 to be 5.93 times 10 to the 23 is the number of molecules. But it wants to know how many molecules have left the bag. So you do the start number, 2.13 times 10 to the 24, minus the final number, 5.93 times 10 to the 23. So 1.54 times 10 to the 24 molecules have left the bag. In the next question, a toy rocket is made from a 1.5 litre plastic bottles with fins attached for stability. The bottle initially contains 0.30 litres of water, leaving 1.2 litres of trapped air at temperature 70 degrees Celsius. A pump is used to increase the pressure of the air within the plastic bottle to 2.4 times 10 to the 5 pascals at the start of liftoff. Figure 1 shows the rocket at the start of the liftoff. Calculate in moles the number of trapped air amount of trapped air in the bottle at the start of liftoff. The trapped air pushes the water downwards out of the hole, causing the rockets to rise. The temperature of this air remains constant. Calculate the final pressure of the trapped air just before all the water has been released. Use the data on the toy rocket to show that the upwards force on the rocket at the start of liftoff is about 15 meters, and then hence the initial vertical acceleration of the rocket. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know N equals PV over RT. Pop in all the values. Remember, T is in Kelvin, so it's 0.12 moles. We also know from Boyle's law that PV equals a constant, or P1V1 equals P2V2. Pop in all the values, and P equals 1.92 times 10 to the 5 pascals. Now also we can know that the change in pressure is going to be equal to 2.4 times 10 to the 5 minus 1 times 10 to the 5, so it's 1.4 times 10 to the 5 pascals from the information given. We know that force is equal to the change in pressure times by the area, because pressure equals force over area. So you can work that through. You've got the area, so you get 15 newtons. And then finally, what's the initial vertical acceleration of the rocket? Well, the total mass of the rocket is 0.35 kilograms. F equals ma, where F is going to be the resultant force, which is the upwards force minus the weight downwards. So you can work it all through and you get A to be 34 meters per second squared. The next question says, calculate the average speed of the helium molecules at room temperature and pressure. Comment on how this speed compares to the average speed of air molecules at the same temperature and pressure. Then a sample of neon is contained in a cylinder at 27 degrees Celsius. Its temperature is raised to 243 degrees Celsius. Calculate the kinetic energy of the neon atoms at 27 degrees Celsius, 243 degrees Celsius, and compare the speeds of the molecules at the two temperatures. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that P equals 1/3 P times by C squared, so you can pop in all the values and you get the speed out to be 1.69 times 10 to the 6, which when square rooted is 1,350 meters per second. Now, that's considerably faster than air molecules at the same pressure, because helium has this much smaller mass, so to have the same kinetic energy, which is the same for the same temperature, they've got to have a much greater speed. Now, in this next one, we know that the kinetic energy is 3/2 kT, so we do do 3 over 2 times by K times by 300, the temperature in Kelvin, so it's 6.2 times 10 to the minus 21 joules. Do the same at 243, but remember now we convert our temperature into Kelvin, so it's 1.0 times 10 to the minus 20 joules. Now the ratio of speeds is going to be 1.07 over 0.62 by looking at the two values given before, so therefore the ratio of energies is 1.72. We know that speed links into energy by a square root because it's a half mv squared, so therefore it's going to be 1.31 to 1. The next question says, a truck is used to cross the Sahara Desert. The journey begins just before dawn when the temperature is 3 degrees. The volume of air held in the tyre is 1.50. It exerts a pressure on the tyre walls. Calculate the number of moles of air in the tyre. By midday, the temperature has risen to 42 degrees Celsius. Calculate the pressure in the tyre at this new temperature. You may assume that no air escapes and the volume of the tyre is unchanged. Calculate the increase in the average kinetic energy of an air molecule due to this temperature rise. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question, how do you answer it? Well, in this first one, you can see that it exerts a pressure by the kinetic theory as the molecules hit the wall and rebound from the wall. Each impact causes a small force or change in momentum and impulse on the wall. So the molecules are in random motion, so the more impacts will smear the force over the whole wall. Now the number of moles, we can say, well, ideal gas equation, PV equals nRT, N equals PV over RT. Again, remember, temperature should be in Kelvin, not in degrees Celsius, so we get 224 moles. Again, we can use PV equals nRT, so P equals nRT over V. Pop in all the values. T is in Kelvin, not in degrees Celsius, so it's 3.91 times 10 to the 5 pascals. We also know that a kinetic energy is 3 over 2 kT, where the change in energy will be the change in temperature, so therefore you can pop it all through, and remember it's the change in the kinetic, the temperature in Kelvin, so therefore it's 8.01 times by 10 to the minus 22 joules. The next question says, explain what is meant by Brownian motion and how it provides evidence for the existence of molecules. The density of air at room temperature and pressure is 1.21 kilograms per meter cubed. Calculate the average speed of air molecules at this room temperature. State and explain the effect on the average speed of the air molecules of raising the temperature of the air but going to a higher altitude but keeping the temperature constant. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, Brownian motion is the random zigzag motion of larger particles. So the air or water molecules will collide with these bigger particles. Each collision gives the larger particle a change in momentum or an impulse which will make it move in a different direction. This next one we can do P equals 1/3 PV c squared, so you can pop in all the values and you get 2.55 times 10 to the 5 as your c squared, so therefore c is equal to 505 meters per second. If you raise the temperature, well, temperature is directly proportional to the kinetic energy, so the speed will increase. Now going to a higher altitude, the speed will be unchanged because you're not actually changing the energy of the particles when you have a higher altitude because the temperature is remaining constant. The next question says, a student placed a metal block of mass 220 grams in boiling water at 100 degrees Celsius for several minutes. The student then transferred the metal block into 300 grams of water at 90 degrees Celsius inside a glass container of mass 50 grams. The final temperature of the water was 23 degrees Celsius. The table shows specific heat capacity values for copper and tin. Deduce whether the metal block was made from copper or tin. So pause the video now, then unpause the video when you want to go through your answer. Right, so the energy lost by the block is the energy gained by the water in the glass. So E equals mc times by change in temperature. So it's the mass, which is 0.22 kilograms, going from grams into kilograms, times by C, times by that change in temperature. So you can work it all through, and then you can see that actually you can then link it into the energy gained by the water and by the glass. So it's 0.05 times by 840 times by 4 plus 0.3 times by 4,200 times by 4. So we can write an equation out and say 16.94 C is going to be equal to 5,208 joules, so therefore C is going to equal to 307 joules per kilogram per Kelvin. So as you can see from the previous table, as it is 307, the answer is going to be copper. The next question says, an electric kettle contains 4.25 times 10 to the minus 4 meters cubed of water. The temperature of the water is 22 degrees Celsius. The kettle is switched on. The water takes 85 seconds to reach a temperature of 100 degrees Celsius. Show that the power of the kettle is about 1600 watts. Then the water boils at 100 degrees Celsius. Calculate the time now taken for 75% of the water to boil away. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out the mass because we've got the density, we've got the volume. So mass equals volume times by density, so it's 0.424 kilograms. We know that the change in energy, because it's change in temperature, is mc times by change in temperature. So therefore it's 0.44 times by 4,190 times by the change in temperature, which is going to be 78. So we get 1.386 times by 10 to the 5 joules. Power is change in energy over change in time. We know the time is 85 seconds, so it's 1,631 watts. In this next one, because we're boiling, we're changing state, so now we say the change in energy is equal to the change in mass times by the latent heat capacity. So you pop in all the values and you get energy to be equal to 7.19 times 10 to the 5 joules. Now again, you can remember that it's taking the time for 75% of the water to boil away. So if you noticed, okay, we can work it through that way because we've taken 75% of the water from the previous question. So we've done 0.75 times by 0.424. Now time is the change in energy over the power, so you pop it all through and you get 441 seconds. The next question says, a student investigated the relationship between the pressure and the volume of a fixed mass of gas at a constant temperature. He used his data to plot the following graph. The student stated his graph demonstrated that the pressure exerted by the gas was inversely proportional to the volume occupied by the gas. Assess the validity of the student's statement. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you want to do is, if they are in fact inversely proportional, you should be multiplying the values of the y-axis and the x-axis, so find the points where they intersect the coordinates of the line, and then they should all equal the same value. So again, when p equals 110, v equals 0.006, so you can times together 660. Next, further down, when p equals 60, v equals 0.011, so therefore it's 660 again. And then when p equals 51, v equals 0.013, multiply them together, 663. So the value of the two numbers as a product is constant, so therefore inversely proportionality is proven. That again, you should be doing at least 3 values to show that. The next question says, a steel container contains n moles of an ideal gas. The gas has a pressure P, an absolute temperature T, and occupies a volume V. The mass of 1 mole of the gas is big M. Use the ideal gas equation to show that the density of the gas is given by the expression ρ equals Pm over RT. An airship has a cabin suspended underneath a gas bag inflated with helium. The airship is floating above the ground and is stationary. The volume of the gas bag is 12,000 meters cubed. The temperature of helium in the surrounding air is 20 degrees Celsius. The atmospheric pressure is 1 times 10 to 5 pascals. The molar mass of air is 0.029 kilograms per mole. The volume of the cabin is negligible compared to the volume of the gas bag. Show that the density of air under the conditions described is about 1.2 kilograms per meter cubed. Calculate the weight of air displaced by the airship. Explain why the weight of the air displaced by the airship has the same magnitude as the weight of the airship and its contents. And the pressure of helium in the gas bag is maintained at a value only slightly greater than the atmospheric pressure. Suggests why a larger pressure is not used. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we can say ideal gas equation, PV equals nRT. The mass is the number of molecules times by, so the number of moles times by the number of molecules in there. So therefore, we can substitute in the equation, cancel them all through, and we'll get ρ equals PM over RT. In the next one, we can then work it through using the equation. So we can say 100,000, because we're converting kilopascals into pascals, times by 0.029, which is the molar mass. Okay, then divide by 8.31 times by 293. Temperature goes into Kelvin, so 1.12 kilograms per meter cubed. The mass of the air is going to be the density times by the volume, so you can work it through that way, as you can see in there. And then you can change that into a weight by times and by G, 9.81, so therefore we get 140,000 newtons. In the next one, we know that when something is floating in the air, the upthrust will equal to the weight of the fluid or the air that are displaced. So therefore the airship is in equilibrium. We can tell that from the information given in the question. So therefore the resultant force is 0. So the upthrust must equal the weight of the airship. And then finally, in the last one, the greater pressure would increase the density or the weight of the helium. And increased pressure but no change in volume would therefore have no more upthrust. So if the volume does go up, then the upthrust would increase. Now the pressure only does need to be large enough to inflate the gas bag, and an increased pressure may then cause a structural failure in the actual component with that increased pressure. So that brings an end to our. So let's have a look at some questions for nuclear physics. The first question says, in the early 20th century, a series of experiments was carried out in which alpha particles were directed at thin metal foils. A simplified version of the apparatus used is shown. Describe the observations from these experiments and the conclusions that were made from these observations. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, what should you be aware about for the alpha particle scattering experiment? That most alpha particles went straight through or were undeviated, so therefore the atom is mostly empty space. A few alpha particles were deflected by small angles, so therefore very few alpha particles came straight back. So therefore that told us that there's a concentration of charge in the atom, and that's where the concentration of the mass of the atom is as well. The next question says, Rutherford's scattering experiment was done in an evacuated container. Explain why this is necessary. Then in the Rutherford's experiment, alpha particles were directed at thin gold foil. A small fraction of the alpha particles were backscattered through 180 degrees. Describe and explain how the fraction backscatter changes if the following changes are separately made. A thicker foil is used. Faster alpha particles are used. A silver foil is used. Now a silver nucleus has less positive charge but roughly the same volume as a gold nucleus. So pause the video now, then unpause the video when you want to go through your answer. Right, we needed to use an evacuated container as if there were air molecules in the container, the alpha particles would scatter off them and then distort the results, and the alpha particles could also be distorted by 6 centimeters of air. If a thicker foil was used, you get more backscattering because there's a greater chance of a closer approach to a gold nucleus. So therefore you get more than reflecting backwards. If faster alpha particles are used, fewer will get backscattered because their inertia, because they've got a higher velocity, so therefore greater inertia, will tend to carry them forwards even if they are interacting with the gold nuclei. And if a silver foil is used, fewer will get backscattered because the positive charge of the nucleus is smaller, so therefore the repulsive force between the alpha particle and the nucleus would be smaller. The next question says, before Rutherford's model, scientists believed that the atom was made from negatively charged electrons embedded in a plum pudding of positive charge that was spread throughout the atom. Explain how the alpha particle experiment proved that this old model of the atom was incorrect. Then Geiger and Marsden carried out an experiment to investigate the structure of the atom. In this experiment, alpha particles were scattered by a thin film of gold. When Rutherford analysed their results, what conclusion did he draw about the distribution of mass and charge in the atom? Then describe and explain how the experimental observations that led to these conclusions. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, the plum pudding model predicts that there'll be no large angle scattering events. An alpha particle is more massive than an electron and won't be deviated by an electron. Now, the actual experiment shows that a few alpha particles will be scattered by more than 90 degrees. Now, alpha particles must have interacted with a charged object much more massive than an electron. This object contained most of the mass of the atom, so therefore was called a nucleus. Now, in the next one, what conclusions did he draw? Well, he concluded that most of the mass was concentrated in a small space, that this space, or the nucleus, was positive and surrounded by negatively charged electrons. Now, this was shown because most alpha particles passed through undeviated through the gold, so most of the atom was empty space. Some alpha particles were deflected through large angles, showing that part of the atom is much heavier than the alpha particle and positive, and the electrons were known to exist from J.J. Thomson's experiments, so other particles in the nucleus must have been positive and heavier, and the relative number of large deflections shows the size of the nucleus. The next question says, in Rutherford's alpha scattering experiment, most of the alpha particles were not scattered. What can you conclude about the nature of the atoms? State the approximate radii of the atom and of the nucleus. In a visual model of the atom, the nucleus is represented by an apple of diameter 8 centimeters. Estimate the diameter of the atom in this model. And the figure below shows the path of an alpha particle close to the nucleus of lead. Draw arrows to represent the force on the alpha particle at A, at B, and at C. So pause the video now, then unpause the video when you want to go through your answer. Right, it shows us firstly that most of the atom is empty space because they move through undeviated. You've got to know the facts that the atom is 10 to the minus 10 metres and the nucleus is 10 to the minus 15 metres in terms of radii. So using this idea of the fact that the difference between the two of them is 10 to the 5 metres, therefore the diameter is going to be 8 centimetres times by 10 to the 5, that's the difference, so therefore it's 8,000 metres. And then this next one, you'll show that in each case the force arrows are always pointed towards the alpha particle from this, because the force on the alpha particle, and then the magnitude of the force is the largest to B, so you've got the longest arrow because they are the closest at that point. The next question says, alpha particles of kinetic energy 8.8 mega electron volts are fired at lead atoms. The charge of the nucleus and the lead is 82 E. Calculate the minimum distance the alpha particle approaches to the nucleus of the lead, the maximum electrostatic force experienced by the alpha particle, and then a tiny droplet of oil diameter 1 millimeter is placed on water. The oil spreads out as a circular disc of thickness approximately 1 atom thick. Estimate the radius of this oil disc. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say that you can work through that the force is equal to QQ times by 4 pi epsilon 0 r squared. That is, in fact, that's the electrical force equation learned in electrical fields. Now you can see that the value is going to be of the overall, sorry, the energy, not the force. Okay, that's the gravity. That's going to be the electrostatic potential energy. My apologies. So you can work out what that energy is because it's the kinetic energy of the alpha particle. Because the alpha particle's kinetic energy goes into the electrical potential energy when it gets close to the nucleus. So you can work that by doing 8.8 times 10 to the 6, so mega electron volts into electron volts, times by 1.6 times 10 to the minus 19. So therefore that is then electron volts into joules. That's going to be equal to the electrical potential energy, so it's 1.4 times 10 to the minus 12. That equals QQ over 4 pi epsilon 0 r squared. You make r the subject because you know what Q and Q are. Remember again that Q for the alpha particle is 2 because there's 2 protons, 2 neutrons, and then the value of charge for the nucleus is 82. It tells you there, times both by 1.6 times 10 to the minus 19. Work it all through, and D is equal to 2.68 times 10 to the minus 14 meters. Now we know the electrostatic force from the electrical field unit is going to be equal to QQ over 4 pi epsilon 0 r as working it through. So you pop all the values in, work it all out, and then you get your answer to be 53 newtons. Now again, we can see here that the initial volume is going to be equal to the final volume, so you can work that as 4 over 3 pi r cubed is therefore equal to, again, 10 times 10 to the minus 10 pi times by r squared. Work it all through, and r is equal to 1.3 meters. The next question says, the radioactive decay of nuclei is both random and spontaneous. Explain what is meant by radioactive decay, random decay, and spontaneous decay. So pause the video now, then unpause the video when you want to go through your answer. Right, what's radioactive decay's definition? It's the emission of alpha, beta, or gamma particles from an unstable nucleus, trying to become more stable. Random decay indicates that it's impossible to predict which particular nucleus will decay. The rate of decay of many nuclei varies above and below the average value. And spontaneous decay means it's not affected by other nuclei or any other factors around it. So it's not affected by external conditions such as temperature. Now radioactive decay, as we said, is both random and spontaneous. The next question says, explain why you would expect beta minus particles to travel further through the air than alpha particles. Explain why you would expect beta minus particles to travel further through the air through air than through metal. Then explain why the most strongly ionizing radiation, alpha particles, is the least penetrating, whilst the least ionizing, gamma rays, is the most penetrating. A smoke detector uses a source of alpha radiation to detect the presence of smoke in air. How does a smoke detector work, and suggest why an alpha source is more suitable for this than a beta minus or gamma source? So pause the video now, then unpause the video when you want to go through your answer. Right, so in the first one, a beta minus particle has less charge, it's smaller and it travels faster, so it's less likely to cause ionization of an atom, so therefore it'll travel further before it loses energy from this ionization process. It'll travel much further through air than through metal because air is much less dense than metal, so there's less ionization caused because there's less interactions with the atoms of the object. Now, more strongly implies that more strongly ionized implies that the radiation will have more collisions with the particles. So therefore there's a greater loss of momentum in each collision, so therefore will not travel as far, so there'll be less penetration. Now for a smoke detector, alpha particles pass between two plates connected to electrical power supplies. The alpha particles cause ionization in the air between the plates, and therefore a small current will flow. When the smoke enters the device, the alpha particles are absorbed and there's less ionization of the air, and there's a smaller current in the external circuit. The circuit then switches on the alarm. Alpha radiation is most suitable because it's most strongly ionized. It causes a greater current to flow, and also alpha particles are more likely to be absorbed by the smoke. Also, the range of the alpha particles is so small that it's unlikely to constitute a hazard to the user. The next question says, a radioactive source emits beta minus particles. It has an activity of 2.8 times 10 to the 7 becquerels. Estimate the number of beta minus particles emitted in a time interval of 2 minutes. State one assumption made. Then a sample of 1,000 undecayed nuclei of a nuclide whose decay constant is 0.20 seconds to the minus 1. Determine the initial activity of the sample. Estimate the activity of the sample after 1 second. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the number of particles is equal to A, the activity, times by the change in time. So therefore it's 2.8 times 10 to the 7 times by 120 seconds, minutes into seconds, so we get 3.4 times 10 to the 9 beta particles, and that's assuming that the activity remains constant. Now, in this next one, we also know activity is equal to the negative of the decay constant times by n. So it's 0.20 times by 1,000 is equal to 200 seconds to the minus 1, or 200 becquerels. So therefore, after 1 second, 200 of those nuclei will decay, so 800 will be left. So the activity after 1 second is going to be A times by the change in time, so therefore so the decay constant times by the number, my apologies, so the decay constant 0.2, the number is now 800 because 200 have decayed from 1,000, so we get 160 or seconds to the minus 1, or 160 becquerels. The next question says, a sample of carbon-15 initially contains 500,000 undecayed nuclei. The decay constant for this isotope of carbon is 0.3 seconds to the minus 1. Determine the initial activity of the sample. A small sample of radium gives a received count rate of 20 counts per minute in the detector. It is known that the counter detects only 10% of the decays from the sample. The sample contains 1.5 times 10 to the 9 undecayed nuclei. Determine the decay constant of this form of radium. Then a radioactive sample is known to emit alpha, beta and gamma radiations. Suggest 4 reasons why the count rate measured by a Geiger counter placed next to the sample will be lower than the activity of the sample. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in this first one, activity is the decay constant times by the number of nuclei, so 0.3 times by 500,000, 150,000 per second. Next one, activity is equal to 10 times by the count rate of the detector, because it's going to be 10 times by the number you got there, so it'll be 10 times by 20 per minute, so therefore it's going to be 200 per minute, so therefore in seconds it's going to be 200 divided by 60, so therefore work it all through, it's going to be approximately 10 over 3 when you work it through, so therefore decay constant is A times by N, which we looked at previously, so therefore, so A over N, my apologies, so you work it all through and you get 2.2 times 10 to the minus 9 seconds to the minus 1. Now the activity is always higher than the count rate because gamma rays are not always detected because they're very weakly ionizing. The counter will always have some inefficiencies. Some radiation will be absorbed within the sample before it actually gets out and reaches the detector, and the detector is directional, so some radiation will move away from the detector rather than towards it because it won't completely surround the source. The next question says, suppose that we start an experiment with 1 times 10 to the 15 undecayed nuclei of an isotope for which the decay constant is equal to 0.02 seconds to the minus 1. Determine the number of undecayed nuclei after 20 seconds. The isotope nitrogen-13 has a half-life of 10 minutes. The sample initially contained an 8 times 10 to the 10 undecayed nuclei. Write down an equation to show how the number undecayed, n, depends on the time. Determine how many nuclei will remain after 10 minutes, then after 20 minutes. Determine how many nuclei will decay decay during the first 30 minutes, and then a sample of an isotope for which the decay constant is 0.10 seconds to the minus 1 contains 5 times 10 to the 9 undecayed nuclei at the start of an experiment. Determine the number of undecayed nuclei after 50 seconds and its activity after 50 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that n is equal to n0 e to the minus lambda t. So therefore, it's 1 times 10 to the 15 times by e to the power minus 0.02 times by 20 the time. So therefore, you get 6.7 times 10 to the 14 nuclei. So again, our equation is n equals n0 e to the minus lambda t. So after 10 seconds, you know that half the nuclei will decay because it's got a half-life of 10 minutes. So therefore, it's 8 times 10 to the 10, half. So it's 4 times 10 to the 10. After a further 10 minutes, the next half will decay. So you've got a quarter left. So 2 times 10 to the 10. After 30 minutes, 3 half-lives have elapsed. So therefore, it's halved 3 times. So therefore, what you can say is the number of original nuclei decaying will be a half, then a quarter, then an eighth. So therefore 7/8 will have decayed and an eighth will be left. So 7/8 of 3 times 10, so 8 times 10 to the 10 is 7 times 10 to the 10. The next one, you would say n equals n0 e to the minus lambda t. Pop in all the values, you get 3.4 times 10 to the 7. And then again, activity is lambda times by n. We know 0.10 is lambda. We've got n from the previous question, so we get 3.4 times 10 to the 6 becquerels. The next question says, below shows the decay of a radioactive isotope of cesium. Use the graph to determine the half-life of this nuclide in years and then find the decay constant in years to the minus 1. The decay constant of a particular isotope is known to be 3 times 10 to the minus 4 seconds to the minus 1. Determine how long it would take the activity of a sample of this substance to decrease to 1/8 of its initial value. So pause the video now and unpause the video if you want to go through your answer. Right, we can tell from the graph the half-life is the time it takes to half, so go from 400 to 200. So therefore, that's 2.4 years. Decay constant is natural log 2 over the half-life, so therefore it's 0.29 years to the minus 1. Now you can see here how long it will take to go to 1/8 of its value. So 1/8 if its value is 3 half-lives, because 1 half-life to a half, second half-life to a quarter, third half-life to an eighth. So that's a very important idea. So therefore, what is 3 half-lives? Well, it's 3 times by the half-life, which we can say to be 2.4 years. So we can work it all through. So it's 6.9 times 10 to the 3 seconds. In our next question, an isotope of N decays with a half-life of 7.4 seconds. Calculate the decay constant for this nuclide. Then a sample of N contains 5,000 nuclei. Determine how they remain after a time of 14.8 seconds and then 20 seconds. Then a sample contains an isotope of half-life T to a half. Show that the fraction of the nuclei in the sample which remain undecayed after time T is given by the equation F is equal to a half to the power N, where N equals T over half-life. Calculate the fraction F after the following times: 1 half-life, 2 half-lives, 2.5 half-lives, and 8.3 half-lives. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, how do you work it through? Well, in the first one, we know that the decay constant is going to be equal, okay, so when we're working it through, it's going to be equal to log 2 over the value. So it's log 2 over 7.4, 0.94 seconds to the minus 1. Then the next one, n equals n0 e to the minus lambda t. So it's 5 times 10 to the 3 times by e to the power minus 0.094 times by 14.8 is 1,250. After 20 seconds, same thing, 760. Now in the next one, we can say we can find an expression for the decay constant which we can sub into the decay equation. So the quantity F is going to be the ratio of the atoms remaining to decay to the original atoms of the sample. So we can say F equals N over N0, where T equals a half-life. So therefore F is therefore going to be equal to a half equals e to the minus lambda T over the lambda T, which T is a half-life. So take natural logs of both sides. So therefore we can say F is therefore equal to e to the power log a half times by T over the half-life. We can then work it all through, so F equals a half to T to the power, the half to the power of T over the half-life. So after 1 half-life, a half is remaining. After 2 half-lives, a quarter is remaining. After 2.5 half-lives, 0.18 are remaining. And then finally, after 8.3 half-lives, 0.032 is remaining. The next question says, the initial activity of a sample of 1 mole of radon-220 is 8.02 times 10 to the 21 seconds to the minus 1. Calculate the decay constant for this isotope and the half-life for this isotope. The figure below shows the count rate recorded when the sample of the isotope indium-116 decays. Use the graph to find the half-life of the isotope and calculate the decay constant. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that A equals a decay constant times by N. So decay constant is A over N. We've got A, we've got N, because we've got 1 mole, so it's 6 times 10 to the 23 particles in 1 mole, so it's 1.33 times 10 to the minus 2 seconds to the minus 1. Half-life is log 2, or 0.693, divided by the decay constant, which just worked out, so it's 52 seconds. In this next question, from the graph, a half-life is the time it takes to go from 160 to 120, so that's 28 seconds. So therefore, so you can work it through, okay, to find the half-life, it's going to be 14 seconds. Now in this next one here, okay, we'll consider the decay constant is going to be the half-life times equals log 2 over the decay constant, so that's log 2 over 14, which we just worked through, so it's 4.95 times 10 to the minus 2. The next question says, the proportion of different isotopes in rocks can be used to date the rocks. The half-life of uranium-238 is 4.9 times 10 to the 9 years. A sample has 99.2% of the proportionless isotope compared with the newly formed rock. Calculate the decay constant for this isotope of uranium and calculate the age of the rock. Then the figure below shows how the randomness affects count rate. State and explain what happens if the experiment is performed using the same amount of radioactive material but at a higher temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that the half-life is equal to log 2 over the decay constant. We've got the half-life, so we can work it through, so it's 1.4 times 10 to the minus 10 years to the minus 1. The age of the rock is going to be equal to n is equal to n0 e to the minus lambda t. So we can rearrange that and say log n over n0 equals minus lambda t. So therefore we can work through t with all the values. Remember, 99.2% means n over n0 is 0.992. So therefore time is equal to 5.7 times 10 to the 7 years. Now in this next one, there'll be no change in count rate because radioactive decay is spontaneous, so temperature does not affect the count rate or the radioactive decay of the substance. The next question says, an isotope of carbon-14 emits a beta minus particle and changes to an isotope of nitrogen. What are beta minus particles? Write a nuclear decay equation for this decay. Draw a graph with the y-axis representing the nucleon numbers between 10 and 16 and the x-axis representing the proton numbers between 4 and 10. And on the graph, mark the isotope for carbon and then the daughter nucleus that this decay will produce. So pause the video now, then unpause the video when you want to go through your answer. Right, beta minus particles are fast moving electrons, and this is important for every nuclear decay that they come from the nucleus themselves. So you can see the decay equation here. Remember, the antineutrino is needed to conserve the lepton number in this decay. Then here you can see our graph here, and you can see firstly the carbon isotope. Now you can see that it turns into nitrogen. Now you can see straight away the proton number goes up by 1, turn it into nitrogen, but the overall number stays the same because, as you can tell, in the beta minus decay, that a neutron turns into a proton, so the overall number of protons and neutrons, the nuclear number, stays constant. The next question says the nuclide of lead-210 decays into three separate stages by alpha and beta minus emission to another nuclide, 206 Pb. So describe the structure of 210 Pb, and then alpha minus and beta minus particles. So alpha and beta minus particles are known as ionizing radiation. State and explain why such radiations can be described as ionizing. And then the two lead nuclides are shown in the graph of nucleon number A against proton number Z. Copy the graph and draw 3 arrows to represent one possible route for the 3 decays between the 2 isotopes of lead. Label each arrow to show whether it's an alpha particle or a beta minus particle emitted. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that the number of protons is 82 because it's the lower number, and the number of neutrons is 128 because it's 210 minus 82. Now in this next one, they are ionizing radiations because the particles are charged. So when they collide with or they pass close to other atoms, they'll knock electrons from the atoms and leave them behind those charged atoms or ions, so ionization. In this next one, you can see a possible path here. So you can see you could either have beta minus, and then you could have alpha, or you could go with alpha, beta minus, and you can see the path that it shows. Number one, alpha decay will lose the nucleon number of 4. Okay, but then if you actually look on the value for Z, it'll go down by 2. And then whilst when you here you've got beta minus, it'll stay constant for the nucleon number, but then the Z number, the proton number, will go down by 1 each time. So the next question says, calculate the nuclear radii in femtometers of the following: helium, lithium, iron and uranium. Then how does the nuclear density for uranium compare to that of helium? And then the neutron star of mass 4 times 10 to 30 kilograms has a radius of 12 kilometers. Calculate its mean density and comment on the answer. So pause the video now, then unpause the video when you want to go through your answer. Right, the equation to work out the nuclear radius is R0 a to the power of a third. So you can do R0 as 1.2 in terms of femtometers. So therefore it's 1.2 times by 6 to the power of a third, which is the nucleon number. So it's 2.2 femtometers. The next one 2.5 femtometers. The next one 4.6 femtometers. And the next one 7.4 femtometers. Now you can work out density by doing mass over volume. So you can work out the mass by multiplying the nucleon number by 1.661 times 10 to the minus 27, which is converting the nucleon number into kilograms. Then you can divide it by the volume, which is 4 over 3 pi r cubed. So you can work out the radius of each one from the femtometers given previously. Remember, femtometers is 10 to the minus 15. So you can work it out from the previous information, and you get 2.3 times 10 to 17 for both densities. And that's an important idea, that the nuclear densities for every nucleus of every element is the same. Now in this next one, density is mass over volume. So you've got your mass there, you've got your radius of 12 kilometers, turn that into meters and do 4 over 3 pi r cubed. Work it through and you get 5.5 times 10 to 17, which is similar to the density of a nucleus. The next question says gold has a density of 19,700 kilograms per meter cubed. A mass of 193 grams of gold contains 6.02 times 10 to 23 atoms. Use this information to estimate the volume of a gold atom and hence its radius, and state any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we know that density is mass over volume. So 193 grams of gold occupy a volume of mass over density. So you can work that through to be equal to be 9.8 times 10 to the minus 6 meters cubed. Remember, we turned out grams into kilograms in this question. So the volume occupied by one atom is therefore the volume of 193 grams divided by the number of atoms in 193 grams. So therefore we can work it through with Avogadro. So we've got the idea of working this idea to be 1.6 times 10 to the minus 29 meters cubed. So therefore the volume of one atom is going to be 4 over 3 pi r cubed. So therefore we can rearrange that, make r the subject, and so therefore it's going to be equal to 1.6 times 10 to the minus 10 meters. And our assumption is that there's very little space between those atoms, okay, in that mass. The next question says that this question is about the nucleus of uranium-235, which has a mass of 3.89 times 10 to the minus 25 kilograms. In its information, state the number of protons and neutrons in the nucleus. The radius of a nucleus is given by the equation R equals 1.41 times 10 to the minus 15 times by a to the power of a third. Determine the density of the uranium nucleus, then explain why the total mass of the nucleons is different from the mass of a uranium nucleus, and then without calculation explain why you can determine the binding energy per nucleon for uranium-235 from its mass and the masses of a proton and a neutron. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the number of protons is 92, it's the lower number. Number of neutrons is 143, 235 minus 92. In this next one, we can work out the volume. The volume is 4 over 3 pi r cubed. So therefore, what is our volume going to be? Well, we can work it all through and we can see that it's going to be equal to 2.76 times 10 to the minus 42 meters cubed. Therefore, we can use that to then work out what r is going to be by looking at the idea of linking in volume into what we're linking it into the mass as such like that. So we get 1.4 times 10 to the 17 kilograms per meter cubed. Now the mass is going to be different because when the nucleons are combined in a nucleus, they have less energy than when they're separated. Now less energy means less mass because energy has mass, so therefore the mass will be lower when they are in a nucleus. In the next one, if you sum the total mass of the separate protons and neutrons, then you subtract that from the mass of the overall uranium nuclide, you can then work out what what the energy is when it goes into a nucleus by doing the energy is equal to the change in the mass between the separate protons and neutrons and the nucleus times by c squared, and this change of energy is known as the binding energy. Now the next question says approximate values for the radius of a gold atom and the radius of a gold nucleus are 10 to the minus 10 meters and 10 to the minus 15 meters respectively. Estimate the ratio of the volume of a gold atom to the volume of a gold nucleus. And then the density of gold was 19,000 kilograms per meter cubed. Estimate the density of a gold nucleus and state any assumptions that you make in your answer. So let's have a go, see if we can work it through. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know the volume of a sphere, which we assume an atom to be, and a nucleus to be 4/3 pi r cubed. So therefore the ratio of the volumes is 10 to the minus 10 cubed over 10 to the minus 15 cubed, which leads us to a ratio of 10 to the 15. Now the next question is 10 to the 5 cubed, which is 10 to the 15. Now in this next one, if we assume that most of the mass of the atom is contrary to the nucleus, then 19,000 kilograms of gold has a volume of 1 meter cubed. From A1, the volume of a nucleus has with this mass is 1 times 10 to the minus 15 meters cubed. So therefore, the density of gold is going to be 1.9 times 10 to the 4, divided by, of the nucleus, 1.9 times 10 to the 4, which is given in the previous information, divided by 10 to the minus 15, so therefore it's 1.9 times 10 to the 19 kilograms per meter cubed. The next question says the sun releases vast amounts of energy. Its power output is 4 times 10 to 26 watts. Estimate how much its mass decreases each second because of this energy loss. Then calculate the energy released if a helium nucleus is formed from separate protons and neutrons. The masses are given in the table below. Calculate the energy released per nucleon. Then a golf ball has a mass of 150 grams. Calculate its increase in mass when it's travelling at 50 meters per second. What is its percentage of its rest mass? So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, E equals mc squared. So this gives us the mass decrease per second. So m equals E over c squared. We know E per second is 4 times 10 to the 26 because what's our energy per second? Divided by c squared, 3 times 10 to the 8 squared. So it's 4.4 times 10 to the 9 kilograms. We know helium nuclei are formed from 2 protons and 2 neutrons. The energy released is the difference in mass between the 4 separate nucleons and the helium nucleus. So if you work out this difference in the masses, it's going to be 5.04 times 10 to the minus 29 kilograms. E equals mc squared. So pop that into the E equals mc squared equations, and our energy is 4.5 times 10 to the minus 12 joules. So what's the energy released per nucleon? Well, there's 4 of them, and there's 4.5 times 10 to the 12 over 4 of them, so therefore it's 1.1 times 10 to the minus 12 joules. In this next question, the kinetic energy of a golf ball is a half mv squared, so it's a half times by the mass in kilograms, 0.150, times by 50 squared is 187.5 joules. The mass energy equivalent of the ball is going to be equal to m equals E over c squared, so it's 187.5 over c squared, 2.1 times 10 to the minus 15 kilograms. So find the difference as a percentage of its rest mass, which is 0.150 kilograms. So it's 1.4 times 10 to the minus 12%, which is about right for an object on the real world scale. The next question says the mass of an atom of iron is 55.934937 U. Calculate its mass in kilograms. Then the mass of an atom of oxygen is 2.656015 times 10 to the minus 26 kilograms. Calculate its mass in U. The table below gives the mass in U of several nuclides. Determine the mass excess of helium, and then one nuclide has a negative mass excess. Name the nuclide and determine its mass excess. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, how can you convert from U into kilograms? Multiply by 1.661 times 10 to the minus 27, so it's 9.2880 times 10 to the minus 26 kilograms. We can reverse it by dividing by 1.661 times 10 to the minus 27, so it's 15.995 U. In this next one, the mass excess is the mass of the helium nucleus minus the mass of the 4 separate nuclides, so it's 0.002602. The mass excess of potassium is a negative, so therefore it's 0.036002. The next question says a nucleus of beryllium decays into an isotope of boron by beta minus emission. The chemical symbol for boron is B. Write a nuclear decay equation for the nucleus of beryllium-10 and then calculate the energy released in this decay and state its form. So pause the video now, then unpause the video when you want to go through your answer. Right, the nuclear decay equation is beryllium will go into boron, and you'll have an electron because you notice the proton number is going up by 1, the nucleon numbers stay constant, so the only thing that can conserve those numbers is an electron. The next one, the mass difference, is the difference in mass between the beryllium at the start and then the boron and the electron. So you can find the difference to be 9.89044 times 10 to the minus 31 kilograms. So therefore the energy release is E equals mc squared. So you get 8.9 times 10 to the minus 14 joules. And this tends to be released as the kinetic energy of the products in this particular decay. The next question says, in a nuclear reactor, the mass of uranium and the fission fragments fall to a rate of 70 micrograms per second. Calculate the maximum power output from the reactor, assuming it's 100% efficient. The equation below shows the radioactive decay of radon-222. Calculate the total energy output from this decay and state what forms of energy are produced. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know E equals mc squared, so 70 times 10 to the minus 6 times by 3 times 10 to the 8, so every second you've got an energy being released of 6.3 times 10 to the 9 joules. The energy per second is the power, so that is the answer, so it's 6.3 gigawatts. In the next one, we know the mass deficit is going to be equal to the mass of the radon minus the mass of the plutonium, the alpha particle, and the gamma, but obviously there's no mass for the gamma. So you can work that through, and you get your difference to be 0.005 U. We can convert that into kilograms by multiplying by 1.661 times 10 to the minus 27. So it's 8.3 times 10 to the minus 30 kilograms. Energy released E equals mc squared. Pop it through, and you get 7.47 times 10 to the minus 13 joules, and that'll be kinetic energy of the alpha particle, and because you've got a gamma ray, some of the energy will go as the gamma ray as well. The next question says, calculate the binding energy per nucleon for the nuclide ion, and then the mass of beryllium nucleus is 1.33 times 10 to the minus 26 kilograms. A proton and a neutron have a mass of about 1.67 times 10 to the minus 27 kilograms. For the nucleus of beryllium, determine the mass defect in kilograms, the binding energy, and the binding energy per nucleon. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, the mass of the neutrons is going to be 56 minus 23, so it's 30 for the ion. So find the mass defect by doing the mass of the protons and the mass of the neutrons, and then subtract it from the overall mass of the nucleus. So you get 8.680 times 10 to the minus 28 kilograms. Binding energy is E equals mc squared. Pop all the values in, and you get 7.812 times 10 to the minus 11 joules. We can then divide it by the total number of nucleons, the large number on the symbol, so 56, so it's 14 times 10 to the minus 13 joules. In the next question, the mass defect is going to be the number of protons and the number of neutrons in beryllium, which is 4 and 4, minus the mass of the beryllium, so it's 6 times 10 to the minus 29 kilograms. The binding energy, so you multiply that by c squared, so you get 5.4 times 10 to the minus 12. You can divide that by 1.6 times 10 to the minus 19 to get into EV, so it's 3.4 times 10 to the 7 EV. So the binding energy per nucleon is then that value divided by the number of nucleons, which is 56, which is going to be 8. So therefore it's 6.8 times 10 to the minus 13 joules, or 4.2 times 10 to the 6 EV. The next question says, explain why hydrogen does not appear on the graph below, and then using the binding energy graph below, suggest why fission is unlikely to occur with light nuclei and why fusion is unlikely to occur for heavier nuclei. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that hydrogen is a single nucleon, so therefore it can't have a binding energy, because the binding energy is the energy lost by the nucleons as they go into a nucleus. And then the second one, fission for lighter nuclei is unlikely because the products of the fission have a smaller binding energy per nucleon, so be less stable, and then the reaction therefore would require an input of external energy, and then for fusion it's unlikely for the same reason as well. The next question says, a carbon-12 atom consists of 6 protons, 6 neutrons, 6 electrons. The unified atomic mass unit U is defined as 1/12 of the mass of a carbon-12 atom. Calculate the mass defect in kilograms, the binding energy, and the binding energy per nucleon. So pause the video now, then unpause the video when you want to go through your answer. Right, so the mass defect is going to be the mass of the individual components minus the mass of the nucleus, so you get 0.098934 U. Multiply that by 1.661 times 10 to the minus 27 to get it in kilograms to be 1.64 times 10 to the minus 28 kilograms. Multiply that by C squared to get defined energy, so it's 1.48 times 10 to the minus 11 joules. Divide that then by the number of nucleons, which is 12, because you've got 6 protons and 6 neutrons. Electrons are nucleons. So you get 1.23 times 10 to the minus 12 joules. The next question says the fusion reaction which holds the most promise for the generation is the fusion of tritium and deuterium. The equation below shows the process. So calculate the change in mass in this reaction, the energy released in this reaction, and the energy released if 1 mole of deuterium reacted with 1 mole of tritium. So pause the video now, then unpause the video when you want to go through your answers. Right, the change in mass is going to be equal to the mass of the things at the start, so it'll be tritium and deuterium, minus the mass of the helium and the mass of the hydrogen after the end. So we get our difference to be 0.020271 U. Multiply that by 1.661 times 10 to the minus 27 to get into kilograms to be 3.365 times 10 to the minus 29 kilograms. Multiply by C squared to get the energy release, so it's 3.028 times 10 to the minus 12 joules. And then if we want, that's the energy released per atoms, the energy released per mole, with that multiplied by Avogadro's constant, the number of molecules in 1 mole. So we multiply that by Avogadro and we get 1.823 times 10 to 12 joules. The next question says, a student supervised by their teacher carries out an experiment with 3 unlabeled radioactive sources. The student is told that each source emits only one type of radiation. One emits gamma, one emits beta minus, one emits beta plus particles. The student has the following equipment: a selection of materials of different thicknesses, a strong magnet, and a radiation counter. Explain how the student can use this equipment to determine safely which radiation each source emits. So pause the video now, then unpause the video when you want to go through your answer. Right, so what method would you use? So you'd measure the background count and subtract from your source count, very important in any radioactive experiment. You'd clamp the source pointing away from you. You'd have safety precautions, so like handle the source with tongs, limit the time of exposure. You'd record the count over a fixed period and then investigate how the count rate varies with the range. You could place aluminium sheets between the source and radiation counter. You could then set up magnetic fields at right angles to emission direction to investigate if they deflect as charged particles, or you can move the radiation counter to find the direction of the deflection. Now you should note that gamma has the longest range in air, beta minus and beta plus have a similar range. Gamma will penetrate aluminium, which is a few millimeters thick, but beta will not. Gamma is undeflected by a magnet because it's neutral, but beta radiation is deflected by a magnet because they are charged. Beta plus and beta minus, as they're oppositely charged, will deflect in opposite directions in a magnetic field. And then you can use Fleming's left-hand law to actually determine the charge on whether it is a positron, the beta plus, or the electron, the beta minus particle. And then also remember as well, with beta plus, the current is in the same direction as the motion because it's a positively charged particle, so you can see it as if it was conventional current. The next question says, in beta plus decay, a proton decays into 3 other particles. Write the nuclear equation for this process, and then a student supervised by a teacher carries an experiment with the 3 unlabeled radioactive sources as indicated before. So, explain how you can use this equipment safely to determine the radiation emission. So in this first one, it is going to be a proton will go to a neutron, and then you're also going to have your neutrino will be present as well, okay, and also your positron will work also. Now the next question says the student gathers the following data and plots the following graph of data. The half thickness value X for a particular shielded material and type of radiation is often used in industry, and the value of the thickness of the shielding required to reduce the incident of the radiation by half. The student thinks that the relationship shown by the data of the corrected count versus the shielding is exponential. Use the information provided and describe a form of mathematical test to support this conclusion. Calculate the half thickness, describing also the method you would ensure a reliable value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how could you use the data? So the data from the table could be used to find the constant reduction factor between the successive points. So you should do multiple data points and find that you've got a constant value. Or you could do a natural log value for each count rate, and then the difference between the successive values is calculated and found to be constant. So that's how you can determine exponentiality, either with using natural logs or from taking the values and finding the rate of change, and the rate of change should be constant. In terms of using the graph, the count rate decreases with increase in thickness. The relationship does show exponential decrease of count rate, and there because it shows the count rate halves at regular intervals with that of shielding. The thickness for the count rate should be dropped by the same fraction as it changes each amount of time, and the gradient of the curve at different thicknesses shows it halves at roughly regular values. You should find from the graph that the half thickness is at about 2 centimeters. You can use the graph to take measurements of values of half thickness. You should take multiple measurements to take an average value, so you can work it all through with your precision to be about 2.1 centimeters. The next question says, the cesium is a radioactive isotope produced during the fission of uranium. State what is meant by fission, then cesium decays by emitting beta radiation. Complete the nuclear decay for cesium. Explain why the emission of an antineutrino in the decay leads to a range of energies for the beta minus particle. Cesium is a major source of radiation from radioactive waste. A nuclear fission reactor produces about 24 kilograms of cesium each year. A website states that 24 kilograms of cesium has the same activity as 2,000 kilograms of radium. Assess whether this statement is correct, and then cesium may enter plants grown in a contaminated area. The radiation from 100 grams of plant material grown in a contaminated area can have a count rate as high as 500 becquerels. As a count rate of 150 per minute is considered safe, determine the time taken for the count rate from 25 grams of plant material grown in a contaminated to fall to a safe level. So pause the video now, then unpause the video when you want to go through your answer. Right, so what is meant by fission? That is when a massive nucleus splits into two or more smaller fragments of roughly equal mass, and you'll also produce some neutrons as well. Now in this particular equation, you can see that the cesium is 13555, the barium's gone up by 1 proton, so it's 56, you then got your beta minus is 0 minus 1, and your antineutrino is 0 0, it has no charge, so that all the values are conserved. Why do you get a decay? Well, because the momentum is therefore conserved, the energy released is shared between the beta minus and the antineutrino, and therefore it's shared between a multiple number of particles in the decay, so it varies it out. In this next one, we know that the number of particles is 24 over 136.9 times by 1.66 times 10 to the minus 27. That's the mass of one particle. So therefore, it's 1.0 times 10 to 06 times 10 to the 26 particles. We know that the decay constant is log 2 over the activity, which is therefore going to be, so the half-life, my apologies, which is 30.2 times by 3.15 times 10 to the 7, because we work in seconds, not years, so it's 7.29 times 10 to the minus 10 seconds to the minus 1. So activity is lambda n, so therefore we've got lambda, we've got n, multiply the two together, and we get 7.73 times 10 to 16 becquerels, which is not equal to 7.3 times 10 to 16 becquerels, so it's not correct. In the next question, we know A is equal to a quarter of the initial, because if we look down, we can see how long it's taken to drop there. So time taken to drop is going to be, it's quartered, so therefore it's going to be a quarter of the initial, so 125 becquerels. So therefore, in terms of in seconds, that's therefore going to be 2.5 in your activity, because you know it's 150 count rate per minute, so therefore per second is 2.5 becquerels. So therefore we can do A equals A0 e to the power minus lambda t, pop in all the values, we can then use that to work out what lambda is, and therefore t is going to be, so t is going to be 5.37 times 10 to the 9 seconds. The next question says, radon is a radioactive gas and emits alpha particles. Explain what is meant by the activity of a radioactive source and give its unit. The half-life of radon is 3.3 times 10 to the 5 seconds. Determine the time it takes for a sample of radon to decay to 20% of its initial activity, and then discuss the extent to which alpha particles are a risk to the human body. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, The definition of activity is the rate of decay or the number of decays per second of the nucleus, and it's measured in becquerels. We know for the next one that the decay constant is log 2 over the half-life. So we've got the half-life in seconds, so we've got the decay constant to be 2.1 times 10 to the minus 6 seconds to the minus 1. We can say that A equals A0 e to the minus lambda t, so therefore e to the lambda t is A over A0, so you can work out what t is to therefore be 7.7 times 10 to the 5 seconds, or 8.9 days. Now, alpha particles are safe outside the body because they're stopped by skin. They're only dangerous if inhaled or swallowed, but they are highly ionizing, so if they are swallowed they can damage DNA, kill cells, cause cancer and cause radiation poisoning. The next question says, potassium-40 is a radioactive isotope and can decay by beta minus emission. Complete the nuclear decay, so the equation for the decay of potassium by beta minus emission, and then occasionally potassium decays by emitting a beta plus particle. Give two similarities between the beta minus and the beta plus particle. A fertilizer contains potassium chloride. The activity of a sample of the fertilizer used to radioactive potassium is 48.6 becquerels. It's claimed that the time t for the activity of a sample to fall below the background count rate will be more than 9 times 10 to the 9 years. To deduce whether this claim is correct, the background count is 0.42 becquerels and the half-life of potassium is 1.25 times 10 to the 9 years. So pause the video now, then unpause the video when you want to go through your answer. Right, we should know that if in this next one we know that calcium has 20 and by beta minus emission it's gained a proton, so potassium must be 19, but the overall nuclear number stays the same, so calcium has 40, and we also know that beta minus particle is always 0 minus 1. Now we know that beta minus and beta plus are particles and antiparticles, they'll have the same mass, they're both leptons, they're both fundamental particles, they'll have the same magnitude of charge, they'll both be deflected in electrical magnetic fields, and they'll both have the same ionizing power. Now in this next one we know the decay constant is log 2 over the half-life, so the decay constant is 5.55 times 10 to the minus 9 years to the minus 1. We can then work out what time is going to be by saying A equals A0 e to the minus lambda t, rearrange that, make t the subject, and we get 8.56 times 10 to the 9 years. The next question says that cesium-137 is a common product of uranium fission. Very small samples of cesium can be used to calibrate radiation detector equipment. Cesium decays to an isotope of barium by emitting a beta minus particle. Complete the nuclear equation for the decay of cesium. Then a sample of pure cesium has an activity of 7,400 becquerels. Calculate the mass in kilograms of the sample. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one again, we know that by this decay, that cesium has lost a proton, so therefore it's going to be 55, the same number of nucleons, 137, beta minus, 0 minus 1, and again it's the same process going through here, except now we're looking for mass, so how we could work it through is do decay constants log 2 over the half-life, so we work out the half-life in seconds, so 7.29 times 10 to the minus 10 seconds to the minus 1. We know that n is going to be equal to the activity over the decay, over the half-life, so therefore you can work it, sorry, not the half-life, the decay constant, so therefore it's going to be 7,400 over the decay constant, it's 1.02 times 10 to 13. Then we can work out what the mass is, because we know the mass is going to be the number of particles times by the number of nucleons that we have, multiplied by 1.661 times 10 to the minus 27 kilograms, so it's 2.31 times 10 to the minus 12 kilograms. The next question says, a nucleus of thorium-230 is unstable and decays to a nucleus of radium-226 by emitting an alpha particle. The table shows the masses of the particles involved. Determine the energy in joules released when a nucleus of thorium-230 emits an alpha particle. Then determine the time taken in years for 90% of the thorium in the sample to decay to radium. The half-life of thorium is 75,400 years. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can say, right, E equals mc squared. Now, mass is going to be the difference in the mass between the thorium and the radium. Okay, and also you can see that the alpha particle is also produced. So therefore, it's 5.1 times 10 to the minus 3u. Multiply that by the conversion factor to turn that into kilograms, 8.47 times 10 to the minus 30. So E equals mc squared. So 7.62 times 10 to the minus 13 joules. We know that the decay constant is log 2 over the half-life. so we can see that's 9.19 times 10 to the minus 6 years to the minus 1. We can then say A equals A0 e to the minus lambda t, but we can go A over A0 and equals e to the minus lambda t. Now, because it's lost 90% of it, therefore what's left is 10%, so therefore A over A0 is 0.1. Pop in all the values, we get out t to be 2.51 times 10 to 5 years. In the next question, in 1935, Irene and Frédéric Joliot-Curie were awarded a Nobel Prize for the discovery of artificial radioactivity. They bombarded an aluminium sheet with alpha particles to produce a radioactive isotope of phosphorus as in the nuclear equation below. Identify particle X, calculate the energy released in joules of this nuclear reaction, and then radioactive phosphorus was one of the first artificially produced isotopes to be used in the diagnosis of cancerous tumours. The isotope of potassium is injected into the body and collects in the tumour. Radiation is detected outside the person's body. It is a positron emitter with a half-life of almost 15 days. Explain why it's suitable for this procedure. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see that X is going to be a neutron. Because it's got a nucleon number of 1, but a proton number of 0, it must be a neutron. In this next one, we work out the change in mass between the particles before and the particles afterwards. So the change in mass, given in the units, is 5 times 10 to the minus 4 gigaelectron volts per c squared. So therefore, the energy, E equals mc squared, so therefore the c squared cancels through. The energy is 5 times 10 to the minus 4 gigaelectron volts. We can then turn that into joules by multiplying it by 10 to the 9 to get into electron volts, then by 1.6 times 10 to the minus 19 to get into joules, so it's 8 times 10 to the minus 14 joules. In this next one, positrons will annihilate with electrons in the body to produce gamma radiation. Now, gamma radiation from annihilation can penetrate out the body. Now, the half-life is long enough to allow the procedure to perform, but not too long to not give a large radiation dose to the person. The next question says, radium-226 decays into radon. Assume that 98% of the energy released in this process is converted to the kinetic energy of the alpha particle. Use the data below to determine the speed of the alpha particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, we can work out the change in mass by doing the mass before and the two masses afterwards and find the difference. So therefore, we find it to be 0.005229 U. We convert this into mega electron volts by using a bit of a cheat, multiplying by 931.5. We can then convert this into then joules by multiplying by 1.6 times 10 to the minus 13 because it's mega electron volts. So therefore, it's 7.8 times 10 to the minus 13 joules. So V therefore is going to be, well, E equals a half mv squared. So therefore, V is equal to the square root of 2 times by 0.98 E because it's 98% of the energy. So divided by the mass, so therefore it's 1.52 times 10 to the 7 meters per second. The next question says the bismuth isotope decays by alpha decay to an isotope of thallium. Fill in the missing numbers for this decay. Then determine whether or not a kinetic energy of 3.6 mega electron volts, the alpha particle in the above reaction, is consistent with the data below. The half-life of bismuth is 1.9 times 10 to the 19 years. Calculate the activity of 1 gram of bismuth. Then determine the number of nuclei in 1 gram of bismuth which will decay in 5 years. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one we know that alpha is going to be 42 on the right hand side, therefore thallium to balance must be 205 on the top and 81 on the bottom. In this next one, what's the values going to be? Well, you find the masses of 83 protons and 126 neutrons for bismuth to be 210.7021 U. So therefore the binding energy, we can then work it through by then finding the difference. So therefore you get 164.83. Then subtract the mass defect for the bismuth mass. So therefore you can find the difference and you get 0.0039 U. Multiply that by 231.5 to get 3.63 mega electron volts. Then this next one, how do you work it through? Well, the half-life is log 2 over the decay constant, so pop in the values and you get 1.16 times 10 to the minus 27. The mass of one atom we know is going to be 209 times by the conversion factor into kilograms, so 1.6 times 10 to the minus 27. The number of nuclei is therefore going to be 2.88 times 10 to 21, so therefore her answer is going to be 3.3 times 10 to the minus 6 becquerels, and therefore we can work out how many decay in 5 years by using the values working through to be 525. In the next question, in the core of a main sequence star, nuclear fusion is converting hydrogen into helium. Explain the conditions required to bring about and maintain fusion in a main sequence star. A helium nucleus is a particularly stable nucleus containing 2 protons and 2 neutrons. Calculate the binding energy per nucleon in joules of a helium nucleus. Then the binding energy per nucleon of a helium is relatively large. Explain why this makes the helium nucleus particularly stable. So pause the video now, then unpause the video when you want to go through your answer. Right, fusion happens when there's a high enough temperature in the core, because this gives the protons a large enough kinetic energy, so the protons can get large enough to fuse because there's an electrostatic repulsion between the nuclei because they've got the same charge. You also need a very high density to maintain a high collision rate to maintain this fusion process, and that also leads to the high temperature. In the next one, find the mass difference before and afterwards. So you find the mass difference before and afterwards to be 28.1 megaelectron volts per c squared. So when we say E equals mc squared, the c squared cancels through, so the binding energy is 28.1 MeV. So therefore we can turn that into electron volts by times by 10 to the 6, then times into joules by times by 1.6 times 10 to the minus 19. So it's 4.496 times 10 to the minus 12 joules. So divided by the number of nucleons that are in the helium, 4, so it's 1.124 times 10 to the minus 12 joules. Now the large binding energy per nucleon means that the energy required to remove the one nucleon from the nucleus is very large, so therefore it's very large to break apart it's very large energies are needed to break apart this helium nucleus, so therefore it's very stable. Now the decay products have a lower binding energy per nucleon, which means that it's less stable because you need less energy to separate it apart. The next question says, a nucleus of polonium-210 decays to lead-206 by emitting an alpha particle. The masses are shown in the table. Show that the energy released in the decay is about 9 times 10 to the minus 13 joules. 98% of the energy from the decay is released as kinetic energy of an alpha particle. Calculate the velocity of the alpha particle immediately after the decay, and explain why all the energy from the decay is released as kinetic energy of the alpha particle. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what's the difference in mass? So you find the mass before, the mass afterwards, and it's 9.63 times 10 to the minus 30 kilograms is the difference. E equals mc squared, pop it through, 8.67 times 10 to the minus 1 joules. The next one, when you work it out, what happens through, so you'll take this value and you'll times by 0.98. That is therefore equal to the kinetic energy of the alpha particle, which is a half mv squared. You know the mass of the alpha particle from the information given, so you can say that therefore that equals a half mv squared. You can say v therefore is equal to the square root of 2 times by this energy over the mass, so it's 1.60 times 10 to the 7 meters per second. Now, why does not all of it get released as kinetic energy? Well, momentum must be conserved in this decay, so if the alpha particle has a movement, well, the lead nucleus must recoil to also counteract that, obviously in much slower speed because it's a much higher mass, so therefore it must take up some of the energy of the kinetic energy of the reaction in that process. The next question says, alpha particle scattering led Rutherford to propose the nuclear model of the atom. Alpha particles were directed towards a thin gold foil. Describe how evidence from these experiments supports the nuclear model of the atom. So pause the video now, then unpause the video when you want to go through your answer. Right, it tells us that most of the particles are not deflected because they pass straight through the gold foil, which indicates that most of the gold atom is empty space. Some particles were deflected from their path by small angles. This indicates that there's a charge center to the atom with the same charge as the alpha particles. Then a small proportion were deflected through 90 degrees, they were backscattered, so most of the mass must be concentrated in this small point, which we call the nucleus. The next question says, radiographers commonly use molecules containing fluorine as traces in positron emission tomography scanning. Fluorine has a proton number of 9 and decays into oxygen by beta plus decay. Write the equation for the decay of a nucleus of fluorine using nuclear notation. The beta plus particle produced travels only a short distance in the patient before it meets an electron is annihilated. Calculate the wavelength of the gamma photons produced. Then X-rays and gamma rays are produced by different physical processes. Briefly describe both processes, and then fluorine has a half-life of 109.7 minutes. Explain the advantage that this has for the patient, but the disadvantage it has for the radiographers. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the fluorine turns into the oxygen, and you've got your beta plus particle, and you've got your neutrino there to conserve lepton number. We know the nucleon number and the proton number are conserved before and afterwards. In this next one, E equals mc squared. So you've got the mass of the particle. It is the same as the mass of an electron because it's the antiparticle. So it's 8.2 times 10 to the minus 14 joules. E equals hc over lambda. So we know that from de Broglie and from and then you work it through to say, well, E equals hc over lambda, pop it all through and you get the value there, and then lambda therefore is 3 times 10 to the 8 over 1.2367 times 10 to the 20, so it's 2.42 times 10 to the minus 12 meters. Now X-rays are formed when electrons de-excite and then release via gamma emission, whilst gamma rays come from the decay of the nuclei in the atom itself. Now, the advantage of having this half-life is that the half-life is short, so the exposure to the patient for ionizing radiation is kept low as possible, but the disadvantage is for the radiographers, they have a very short time to diagnose the patient from the information. The next question says, in 2023, a small capsule of cesium was lost from being transported from a mine in Western Australia. The activity of the cesium in the capsule was 19 gigabecquerels. Show that the decay constant for cesium is about 7.3 times 10 to the minus 10 seconds to the minus 1. Calculate the mass of the cesium in this capsule. Calculate the activity of the cesium in the capsule after 2 years. The capsule was found after 14 days. Calculate the total energy in joules released from the capsule in 14 days. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the decay constant is log 2 over the half-life. Pop it all through. Half-life needs to be in seconds though, so therefore it's 7.31 times 10 to the minus 10 seconds to the minus 1. The mass we know well. Activity is equal to minus decay constant times by n. We know that for that n is therefore going to be the activity, which we know is to be 19 gigabecquerels, which is 19 times 10 to the 9, over the number of particles. Sorry, over the decay constant, which is 7.31 times 10 to the minus 10, which is 2.60 times 10 to the 19. So therefore, the mass is therefore going to be the number of molecules which you have times by 1.661 times 10 to the minus 27, because that turns into kilograms, so therefore it's 5.91 times 10 to the minus 6 kilograms. The activity after 2 years, well, we use the decay equation, A equals A0 e to the minus lambda t. We know the initial activity is 19 gigabecquerels, or 19 times 10 to the 9. We know what the decay constant is, and we know the time. Remember, after this, it has to be in seconds though, not years. So we work it through to be 1.81 times 10 to the 10 becquerels. And then this last one, we know that the energy is going to be equal to the activity multiplied by the time in seconds. So it'll be 14 times 86,400, because we're turning our days into seconds. Then we multiply by the energy released in one decay, which is 1.17 megaelectron volts. So we get 6.96 times 10 to the 16 MeV. We can then convert that into joules by multiplying by 1.61 times 10 to the minus 19 times, get the mega up by times by 10 to the 6. So you get 4.30 times 10 to the 3 joules. The next question says, radium is a radioactive element. The most common isotope of radium has a half-life of almost 2,000 years. A sample of radium can remain at higher temperature than a surrounding for a long period of time. Explain how a sample of radium is able to release significant amounts of energy over a long period of time. So pause the video now, and then unpause the video when you want to go through your answer. Right, in this one, the rate of decay depends upon the number of unstable nuclei in the sample, because A equals minus decay constant times by n. Radium has a large half-life, so the unstable nuclei present are there for a long time. So when a nucleus decays, there's going to be a small decrease in the mass, and therefore when that happens, energy is released from the binding energy equation, E equals mc squared. Now, because the change in mass is small, C, 3 times 10 to the 8 squared, is still large, so a significant amount of energy is released. This energy released becomes the kinetic energy of the atoms in the sample, so therefore that links into the temperature of the sample, so the temperature is much higher of the sample compared to the surroundings. The next question says, in the early part of the 20th century, Rutherford made the first observation of an element being changed into a different element. Alpha particles were fired at nitrogen atoms. The nuclear equation for this reaction is shown. Calculate the minimum energy in MeV required for this reaction to take place, then calculate the minimum energy in MeV for this reaction to take place. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know that the change in mass will be given by doing the mass of the products of this reactants before, subtracted the products of the decay afterwards. So we get 2.07 times 10 to the minus 30 kilograms from the information given. We know that the binding energy is mc squared, so we can then multiply that by c squared, so it's 1.863 times by 10 to the minus 13 joules. We can therefore say we can convert that into EV by dividing by 1.6 times 10 to the minus 19. So therefore it's 1.16 times 10 to the 6 EV, or 1.16 mega electron volts. Now therefore we know that the momentum and energy must be conserved in a decay, so the products must have the kinetic energy after the reaction, so therefore it must be the same as it was before, so therefore you can work it through that way as well. So